So attach tires, attach same. ये देखते हैं check it sir. ये date positions. नहीं नहीं हाँ वीडियो
Hello. Hello. Which is on. Take some time. Turn it off. Take it. Find it. बंद कर दीजिए बात करते हुए देख सोने का ही कंटेंट है और टीवी है और दोनों को तो वो बच्चे जैसे रेडी है तो पैर तक कर लेंगे पैर रहेंगे मैं तो पता नहीं टाइम का
Any age happen. Actually, generally we try to stick as much as possible. It's always because we are notoriously famous for not maintaining the time schedule. They being pop up, you don't you have to immediately provide. You take.
That's okay, sir.
You take this.
Okay. Yeah. अभी यहाँ पे पहले क्या करना बताओ करने Let's start from here.
I speak on this.
yeah
Oh, that's working? No. We'll share, no? Okay. Yeah. Sure. Yeah. Okay. Now, shall I start? Yeah, better? Sir, I'm starting. Good morning, all. I welcome you all to the second day of the symposium. Today, on the first session, we have generation of electron beam for thermal applications. And we have 4 speakers in this session, 2 innovator talks and 2 oral contributory papers. This session will be chaired by Dr. Raghavendra Tiwari, Head, Material Science Division, Baba Atomic Research Center. I'll hand over the session to Dr. Tiwari.
Yeah, good morning to all of you. And we have a little longer session and it will have the 4 talks. The first talk is by Professor Fukuyama, who is going to talk about on the operating principle of fundamental circuits to produce high voltage. High voltage for the development of the beam accelerator. Professor Takao, I'll just give a very brief introduction about Professor. That he received his PhD from the Kyushu University And then he has gone to Planck's Institute, Germany, under JSPS scheme. And later on, he came back to AMA University for a few years, and now he's in the Nagasaki as an associate professor in the physics. His research interest includes the plasma physics, non-linear science, and fundamental science. Currently, Professor Fuchs is working on the non-linear wave of plasma. So now I will give it over to Professor Fukuyama. Professor, you have 25 minutes of presentation and 5 minutes we will reserve for the question answer. Over to you, sir.
Okay, thank you very much. So I will share my PowerPoint. Thank you very much. Okay, so thank you very much for giving me this opportunity to make a presentation. My name is Takao Fukuyama of Nagasaki University, Japan. I have been working on basic plasma physics, and in this symposium, I would like to present my research on the title of this presentation. That is basic research on the basic circuit to generate the high voltage required for beam acceleration. My presentation may be a bit out of the scope of this symposium, but I would appropriate it if you would take a moment to listen to it. Now I would like to start my presentation. Before a presentation, I would like to introduce Nagasaki and Nagasaki University shortly. Nagasaki locates in southern part of Japan. Maybe the name of Nagasaki and Hiroshima is well known in the world. These are typical photographs of Nagasaki. This is Peace Park memorialized by atomic bomb. This is Dejima. Before 150 years ago, Japan closed the country, and only here in Dejima, there were connections to overseas countries. This is night scope of Nagasaki city. Nagasaki University has 11 faculties. Almost all fields are covered, and about 10,000 students are studying in Nagasaki University. As shown, Chairman shows, these are my recent work. I am studying basic research of plasma physics, especially chaos and synchronization waves in plasma. Okay, I will be back to my research presentation. We focus on operating principle of Cock-Croft-Walton circuit to produce high voltage for development of beam acceleration. The Cock-Croft-Walton circuit was proposed by these two Nobel Prize-winning scientists and is a major development in physics such as beam acceleration. The circuit is very simple, consisting of several capacitors, several diodes, and an AC power supply, and we can see a large model of circuit in museum. Now, I would like to present the contest in this order. The Cock-Croft-Walton circuit is a voltage booster circuit consisting of power supply, a capacitor, and a diode, which has been applied to particle accelerators and has contributed to the development of nuclear physics, such as the collisional destruction of nuclei. However, while much attention is paid to the output voltage of Cockcroft-Walton circuit, it is difficult to say that the voltage boosting process is sufficiently understood. With this as a background of our research, we focused on voltage boosting process in this research. In particular, we developed a method of expressing the voltage boost in a general equation, and then determined the values of capacitors and diodes required for the voltage boost to be successful. So now let's move on to the explanation of the Cock-Croft-Walton circuit. This is a circuit diagram, K-steps circuit. This one. The K-steps Cock-Croft-Walton circuit consists of one AC power supply, 2K capacitors and diodes, which are combined in a ladder shape like this. The equations are for the following elements: AC power supply, capacitor replacement current, a Shockley model of diode, and output voltage. The final output voltage is expressed as 2K times the maximum voltage of the AC source. And the potential difference between the capacitors, the replacement current of capacitors, and the electric potential can be expressed by these equations. By inserting these equations into a single equation, such a circuit equation can be obtained. Now, let's move on to the circuit analysis. This is an analysis of circuit. The number of steps is increased in this way to predict the behavior of a typical K-steps circuit. 1 step, 2 steps, 3 steps, and then we predict K-steps circuit. The slide shows graphs of such physical values for a 3-steps circuit, and we discuss the voltage boosting process. This shows 3-steps Cock-Croft-Walton circuit, Cock-Croft-Walton circuit diagram, 3 steps. This shows electric potential. Yellow-green is the oscillation of power supply. As the graph shows, the voltage rises and falls repeatedly, oscillating and rising as a whole. We can see that the oscillations of the odd-numbered potentials do not converge, while the even-numbered ones converge to a certain value. This shows potential difference between diodes, like this. This shows potential difference between capacitors, like this. This shows current in diodes. The current flows through each diode in this order. While oscillating, the current converges to 0 ampere as time passes, like this. This shows displacement current in capacitors. The voltage increased process of circuit is divided into 6 stages. Please watch current flow in circuit and stored charge in capacitors. One stage shows like this. Two stage shows like this. Three stage shows like this. This one and this one. Four stage shows like this. Five stage shows like this. It is spread like this. And then 6 stage shows like this. Okay. So the formula for the amount of charge stored in a capacitor can be expressed by these equations. Little bit complicated. From the above equation, the amount of charge stored in each capacitor show like this. Like this. The green area shows the conservation of charge. It shows that the charge is transferred to the capacitors at the higher level. In other words, the voltage is actually boosted by a process in which a part of a charge remains in the capacitor and is gradually transferred to the higher level. Next, I'd like to show gradual expression display of output voltage. In order to display the output voltage as a gradual expression, we focus on the potential difference between the capacitors, like this. So, as concrete example, let's take the potential difference between capacitors in a 3-step circuit. The gradual equations and the voltage multiplier for a single step set can be expressed by the following equations. This is a graph comparing in gradual equations and the voltage boost ratio of the output voltage obtained by the simulator. From this graph, we can see that two are in good agreement. The gradual equation of the 3 steps set and the voltage boost ratio can be expressed by the following equation. From this graph, we can see that the two are in agreement. The following equation can be used to express the k-steps incremental equation and the boost factor. This is a bit complicated, but it gives us the gradual formula shown here. Here is a graph of the result of the calculation using the asymptotic formula. Sorry. From the graph, we can see that the higher the number of steps in the circuit, the longer the time required to boost the voltage. Next, I would like to show that combination of AC power frequency F and electrical capacitance C. Now, in order for the voltage to be successfully boosted in circuit, it is necessary to select an appropriate combination of the frequency of power supply and capacitance of capacitor. The graph shows how the voltage is boosted when power frequency is fixed. From the graph, it can be read that the voltage is raised normally when the capacitance is 1 nanofarad and 1 microfarad, but not when the capacitor is 1 millifarad too big and 1 picofarad it's too small. The following graph shows the range of power frequency and the capacitance pair for 1 steps and 10 steps sets. This one. This result shows that the capacitance of the capacitor moves in the direction of decreasing as the number of steps increases, like this. Okay. Here is one example of calculation for such a case. First, make sure that the combination of the power supply frequency and the capacitor capacitance is within the region where the voltage is normally boosted, like this here. Inside this circle, we confirm. Next, substitute each physical quantities into the equation obtained earlier and use such as spreadsheet software to calculate and graph the output voltage and the time required to boost the voltage, like this. We can predict output voltage and boost time. So finally, we summarize this study. By focusing on voltage boosting process of Koch-Cross-Walton circuit, the following points were clarified. First, the output voltage of K-step circuit can be expressed as a gradual equation, and it is necessary to select an appropriate power frequency and capacitor capacitance. That's all. Thank you very much for listening to my presentation. Thank you.
Now, session is open for the questions. So if anybody has question, kindly, you can type it also in case you don't want to speak on. Okay. Professor, I have one question.
Yeah.
See, generally in high voltage, one of the critical issue is about the ripple.
Mm-hmm.
Generally, we want to keep the ripple as low as possible. Now, when you're changing the capacitors from pico to millifarad, how this ripple is changing?
I just change capacitor.
Mm-hmm. So because your number of steps are increasing with depending on your selection of capacitors.
Yeah.
So, but what about the ripple?
Sorry, I cannot catch English because I don't.
Generally, there is a fluctuation in the voltage.
Yeah. Mm-hmm.
These fluctuations within the standard values are very important, particularly for very high voltage systems.
Yeah.
Because they make the system unstable. So, do you have any comment on that?
No. I don't think deeply about this. So I should think this fluctuation. Sorry.
Sir, I have one more questions.
Yeah.
But let us say for 15 stages Cockcroft-Walton,
Mhm.
if we provide a input voltage, but output voltage is not coming just as because just is the multiplication of number of stages. So what could be the reason? And to get that exact value of n's, what we should do?
So, sorry. One more. Please speak slowly.
Basically, in the Cockcroft-Walton, their
Mhm.
output equation is about
Mhm.
proportional to the number of stages.
Mhm.
But let us say it is 15 stages.
Mhm.
So in actual condition, we are not getting that number of stages output voltages. So what could be the reason? And to get that exact amount of voltages, what should be done?
Mhm. Ah, so, sorry. I don't have answer about it now. Yeah.
If there is no more question, let me thank Professor for giving such a very illicit talks, which can be understood by a person like me who is not from the electrical field. So thank you very much, and for your time, we appreciate. And as a token of appreciation, we want to give you the this certificate from our side.
Thank you very much. Thank you very much.
Okay, thank you, Professor.
Thank you.
So no. Otherwise, we can go switch over. That's it. So who's the person? Okay. In the session, the next talk, we are not able to connect to Dr. Gigi Roy because of some reason. So what we will do, we'll probably reschedule our presentation sequence that now Dr. Viswajit Jana will be going to present in the place of Dr. Gigi Roy. So there are only 5 more minutes are there. So he will start around 10 o'clock. So we will just wait for 2-3 minutes. If in case we can restore the connection with Dr. Roy, then maybe we stick to the schedule. Otherwise, Dr. Biswa Jana will take over. Thank you.
फोन कर दो फोन स्लाइड फर्स्ट स्लाइड में जाओ
So we will start the session again with Dr. Biswas Jana, who is from BRC, that is Baba Chan itself. So he joined in 2005 after completing his master degree from IIT Mumbai. And he received his PhD in 2016 from the Institute, Homi Baba National Institute, that is again the part of DAE. Dr. Jana is working on the laser and plasma technology division, where he is working on the enrichment of the ytterbium-176, Lu-176 isotopes through atom vapor laser isotope separation process. And today he is presenting on the electron bombardment heating furnace of the vapors in the laser isotope separation process. So over to Dr. Jana. You will have 15 minutes to speak.
Okay, good morning to all. Thank you for Dr. Triwari for nice introduction. And I would like to thank the convener of the symposium for giving an opportunity to present our work in this prestigious platform. So I'll be talking on the electron bombardment heating furnace for evaporation of lutetium vapor in laser isotope separation process. It's basically the thermal application of electron bombardment in evaporation of lutetium vapor. Let's start with some motivation of our work. As a mouse, sorry. So, as you know today, the lutetium-177 radionuclide promising an important role as a radiopharmaceutical isotope in cancer therapy. It has half-life approximately 6.6 days, and it is produced in the nuclear research reactor by irradiation of neutron by target material either 176 ytterbium or 176 lutetium. Both route has the advantage and disadvantage. In the ytterbium 176, it has natural abundance of 13%. It has very less cross section. So it's required few milligram with enrichment of 95%, more than 95%. In the other way, lutetium 176, it's very less abundance, 2.6%, but it has a large cross section, approximately 700 times than the ytterbium. So we require only few milligram, but enrichment of more than 75% to get the desired specific activity. So this lutetium 176 enrichment can be achieved through atomic vapor laser isotope separation process. This process basically consists of evaporation of lutetium in the range of 1820 to 1850 degrees centigrade, collimation of vapor to form an atomic beam, selective excitation and ionization of targeted 176 atoms, and extraction of this ionized atom from this trace to the product collector with a minimal non-selective pickup of the 175 lutetium. So basically, I will just talk on this region where the evaporation of lutetium vapor and its collimation to form an atomic beam. If you see, the lutetium has the melting point nearly 1663 degrees centigrade. At the laser atom interaction region, the density of the lutetium is decided by the charge exchange cross section between the selected 176 ions and non-selected 175 atoms. So if you calculate from this charge exchange cross section at the interaction volume, the density approximately coming order of 2 into 10 raised to 11. So from that, we can estimate the source density at the source. So it is approximately order of 14. And from the vapor pressure equation, we can estimate the temperature, required temperature is 1820 degrees centigrade. So our aim is to achieve this temperature using electron bombardment furnace. So I will discuss the design development of the electron bombardment furnace and its characterization, evaporation of lutetium vapor, and measurement of density at interaction region. So to heating the lutetium vapor cells, there are two techniques. One is resistively heated furnace, another is electron bombardment furnace. In resistively heated furnace, what happens? The entire volume enclosed by the thermal shield is heated. The crucible gets heated by radiation indirectly. It's a very little bit slow process. So generally, to get temperature less than 1500 degrees centigrade, we generally use this resistively heated furnace. And for higher temperature, the required input power significantly increases. Whereas in the electron bombardment furnace, the electrons emitted from the filament, which is resistively heated at low power, they are accelerated between the filament and crucible and hit the crucible with high kinetic energy. So crucible is heated directly, so it's a very fast process, and power requirement is relatively less compared to the resistively heated furnace. So for the lutetium evaporation, we have chosen the electron bombardment furnace. This AC power supply is used to heat the filament, and the regulated DC power supply is used to extract the electrons and draw the electron bombardment current. Here, the entire furnace is inside the vacuum chamber. Vacuum order of 10⁻⁻5 is required in the heating zone to avoid the high voltage discharge. Even at the interaction zone, better vacuum is required for less scattering. So for this experiment, we need water-cooled base plate between heating zone and the laser atom interaction zone, such that good electrical insulation in the ion extractor assembly can be maintained, as well as water-cooled vacuum chamber for dissipating the input power supply. So our group, though, is doing some thermal simulation, detailed thermal simulation, but here I will briefly discuss the design parameter, how we have decided for the electron bombardment furnace based on some hand calculation. So as you know, at thermal equilibrium, the incident power on the crucible equal to the heat loss from due to its radiation. This is the equation. So this is our crucible. This is crucible along with the collimator slit. The lutetium is just bottom of this crucible. So it is made of tungsten, surface area of only 0.03 meters square. From this calculation, if you just put the surface area and temperature 1800 degrees centigrade, this temperature is in Kelvin. So we can approximately estimate the power, estimated power is 10 kilowatt. To get this 10 kilowatt, if we apply the 2 kV voltage, the electron bombardment current is nearly 5 ampere. You just see this filament of 2 meter and 1 millimeter diameter. This is the current, thermionic current from Richards-Dushman's law. This is equation that to get this 5 ampere current, we can just operate the filament at 1900 degrees centigrade. So it looks easy that we can get easily temperature, but it's not so easy. At the operation point of view, there is a difficulty. When the lutetium vapor evaporates, a small amount of vapor also deposit on the inner seal of the inner seal of the molybdenum sheet, thermal sheet. So what happened? Since the lutetium has a low work function compared to the molybdenum, a huge amount of electrons emit from the surface, and it's basically get the instability or thermal runaway. To overcome this thermal runaway, heat seal are placed away from the crucible, nearly 60 to 70 mm from all sides of the crucible. It reduces the inner heat seal temperature to 1050 degrees centigrade, which significantly decrease the thermionic emission from the current. That here we can see that the total current emitted from the lutetium deposited heat seal, entire heat seal is deposited. So in 1050 degrees centigrade is less. So it also reduces, since the distance is large, so electron bombardment current, contribution of electron bombardment current from the surface to the crucible. And filament are placed close to the crucible, and electron emitted from the crucible, they hit with kinetic and high kinetic energy. So here I will just characterize this our furnace by measuring the different parameter, different various location. The crucible temperature, surface temperature is measured by the pyrometer. The inner seal temperature measured by the K-type thermocouple. Electron bombardment power is measured by the estimated voltage and current in the power supply.
as well as the filament current, AC voltage and current in the filament circuit. You have observed that nearly 2.4 kilowatt power is applied to the filament to attain the measured 1950 temperature of the filament. So at that filament, so here I have shown the crucible surface temperature, measured crucible surface temperature with the electron bombardment power. We can see that as the bombardment power is increases, the temperature is also increases. Here at the lower power, it's the pyrometer shows some wrong data, because at the lower power, what happened, the crucible is not heated too much. So what happened, the light emitted from the filament, they are reflected to the pyrometer. So as the temperature increases, it gets heated and the intensity of the light from the crucible increases. So we get the actual temperature of the crucible surface temperature. At the same time, we also measure the inertial temperature at the input power. So to get this temperature of at the 10 kilowatt power, bombardment power, we can see the measured temperature is 1820, inner heat shield temperature is approximately 1050. And we have seen no thermal runaway observed during its operation, except few trips like 1 or 2 trips in hour. So we have measured our lutation evaporation and measured the density of atom at the different at laser atom interaction region using the deposition technique. Here, as I discussed, this is the furnace. So here, this is the furnace, and the Doppler width is relatively large. To get the reduced Doppler width, we have just used one structure which is known as Doppler reducer. If you see along the length, this is the collimator, and along this is the one Doppler reducer structure. It is a fin-like structure. So the atom which has the largest component, the larger component along the left direction, they are stuck in these plates. So only the narrow Doppler line with atoms, they will pass through the atoms at the interaction zone. So at the interaction zone, we have measured the density using the vapor deposition method, use a series of tokens. At source, you can estimate the temperature of 1820 degrees centigrade. The pressure is 0.1 millibar, density order of 14, velocity 500 meter per second, and Doppler with approximately 1.3 gigahertz. So this is the lutetium atom density at the interaction region with position. So it is approximately, we are getting 2 into 10 raised to 11 density at the interaction region, and full width of half maximum of the beam approximately 110 mm. And we have also just inferred the reduced Doppler width approximately 350 gigahertz. We can see that this is crucible after the evaporation. There is no clogging in this collimator. So here I have shown some few snapshots of our experimental subsystem. This is basically our experimental vacuum chamber. It is approximately volume of 1,000 liter. So it is vacuumed or pumped by the diffusion pump backed by the rotary pump. This is the pyrometer. This is ammeter and voltmeter to measure the filament current. This is the quartz crystal monitor to measure the flux. So this is our crucible. This crucible is isolated by 4 vertical rod crucible supporting system, and they are insulated by the insulator, which is kept at the lower temperature. And this is the Doppler reducer I showed and the token arrangement. After deposition, we are getting the deposition at the tokens. So we have just discussed characterization of the vapor source. So we just cross over one milestone that we have achieved the temperature and characterize our source. I will just briefly just say what are the next challenge for the high enrichment of lutetium-176. You can see that at the source, your temperature is, your source is abundance is 2.6%. We get, it's not working. Okay, at the product, we are getting, we want to get the product of 75%. 75%. So what happened? Here the product is diluted because of the non-selective pickup of the 175 isotope from this interaction region to the collector plate. Here I have just shown the enrichment of lutetium-176 on the collector plate with the photoionization yield for a different parameter of the scattering fraction. Here we can see to get the 75% of the atom, your ionization yield should be greater than 30%. That depends on the laser system and available laser power. And non-selective scattering fraction should be less than 0.05% of the vapor that enter into the interaction zone. It is approximately 1 lutetium-175 in 2000 atoms. It's a very challenging. So on, I should conclude my talk that we have carried out the electron bombardment and heating furnace has been designed and developed. Characterization of the furnace and lutetium vapor source has been carried out. Lutetium vapor evaporation and atomic beam formation have been studied. So I thank to all our team members, RIS team members, Mr. Dharmendra Sarasat, Mr. Tarang Garg, Dr. Borua, Dr. Sahu, Dr. Dixit, and I also thank to Dr. Archana Sharma for her encouragement. Thank you all. Thank you very much.
Now, session is open for questions. Anybody has that questions? Okay, just one small
Yes,
question.
yes.
Your selectivity, how accurate your selectivity is there in this
At
electron?
the interaction zone. Actually, the selectivity depends on the laser parameters, laser line width, and the Doppler line width, and the isotope shift of between the two isotopes. So we are getting in the mass spectrometer, we are getting more than 99% abundance we are getting at the interaction region.
Okay, thank you.
Okay.
And as our token of appreciation, kindly just come here so we can give you,
Okay.
let's say, a small memento from our side.
Okay. Thank you very much, sir.
Professor Roy is now, we could connect to him. So we will go back to our original schedule that the second talk will be by Dr. Roy. So he is going to
Okay. Yes, yes.
Yeah, so he is going to speak on some research work on the electron beam welding on the reactive and the refractory metals. So Dr. Roy is the head of department of the metallurgical and material engineering from 2014 to 17, and now as associate dean for sponsored research and industrial consultancy, that is short form is SRIC at IIT Kharagpur. Dr. Roy is also recipient of the Metallurgist IM Metallurgist of the Year Award in 2015. This was bestowed upon him by the Ministry of Steel, Government of India. His research work includes the alternative routes for the iron making, clean steel, electron beam welding, modeling, and simulation. He is author of more than 100 publications in the refereed journals. And Dr. Roy is currently holding the position of professor at IIT Department of Metallurgical and Materials Engineering at IIT Kharagpur. Now, over to you, Professor.
Okay.
You had 25 minutes to speak on. 5 minutes we are reserving for the question and answer session.
Okay. Thank you very much. Can I share?
Please go ahead.
Okay. Okay. Is it visible, my screen in slideshow mode?
Yeah, it is visible.
Okay, okay. Thank you very much. Thank you, Chairman, for kind introduction. And I would like to talk, I understand this conference is for science and technology of vacuum technology and this application. I will basically talk on application of vacuum, that is the electron beam welding. And I'm very, at the onset, I'd like to express my gratitude for inviting me for this invited talk. I'm very happy from that point of view also because the electron beam machine that I'm using at IIT Kharagpur is designed, fabricated by Bhava Atomic Research Center BAR and installed by them at IIT Kharagpur based on AMU. I'll just talk about that. So, yeah, it's done. So application of vacuum in electron beam welding, because vacuum is essential for electron beam generation, because otherwise in open atmosphere, the electrons are get scattered. And you can see near 1 atmospheric pressure, that is around 750 torr, the scatter is significant. And when I have a pressure of 5 torr pressure, then the beam is much more concentrated. So vacuum plays an essential role in electron beam welding and electron beam welding setup. So being in the vacuum, it also produces very unique opportunities to weld some reactive metal like titanium, niobium, okay, and any metal, even aluminum, those are very prone to oxidation. So, and also the reflective material, that means that is the material, most of the metals are very reflective with respect to the laser light source. And while in case of the electron beam, since electron beam get absorbed on the surface and then kinetic energy transported to the heating and melting and all these things, the efficiency of electron beam welding is much greater even for any metal system, and it may be around 90%, where laser beam welding gives only around 20% absorption of the light that converts to the heat. So that way, electron beam welding is very unique. And one that is the topic that is I'm very fascinated with beam oscillation during electron beam welding. Since it is in vacuum, with the help of electromagnetic, that is the lens, we can deflect the beam, and then we can have different pattern on the beam oscillation. And presently at our IIT Kharagpur, we can have only the circular oscillation, and thanks to the BARC people who generate this, that is the beam oscillation system in our electron beam welding. And we have used it, and we have successfully welded some difficult to dissimilar dissimilar metals, and that we will discuss. And my primary focus will be on the beam oscillation and why beam oscillation gives some very good property of the weld joint. Okay, it does some miracle, I will say, because it is known that beam oscillation produces a churning action, but how this churning action is generated, that is my focus. Actually, I will talk about that thing also. And I'll definitely give you some example how the beam oscillation improve the weld properties. Okay, before I go, just like I'd like to say the genesis of VW setup at IIT Kharagpur. There is a part IIT Kharagpur had proposed establishment of advanced research facility for electron beam welding and process development for the program of interest of DAE, and it dates back to 2006 when the first MOU was signed between BRNS, BARC, and IIT Kharagpur. And BARC wanted to donate a electron beam welding setup at IIT Kharagpur. And this MOU, when it was generated, then there was Professor G.L. Dattu in mechanical engineering at IIT Kharagpur. He was the main person, and also I was involved from that time itself, but Professor Manna was also there at the time. And then anyway, and then finally, the Professor G.L. Dattu had to leave after retirement, and he went to as a VC in Guntur University, and then Professor Manna took up as the PI of this project, and then also Professor Manna left IIT Kharagpur to take up the job of directorship at Calcutta. See where that is, and then Glass and Ceramic Institute, Calcutta, and then I took over as the PI. And in my time only, the BARC, that is the complete setup, was came into picture, and the BARC responsibility was to design, fabricate, installation of 80 kV, 12 kilowatt electron beam setup at IIT Kharagpur, and final installation was done in April 2012. And most important personalities, those who are involved, I should not, they should be, I always remember them, otherwise electron beam setup shouldn't be here at IIT Kharagpur. First, I would like to remember Dr. Shikumar Banerjee, late Dr. Shikumar Banerjee. He was one of the prime movers for this machine to set up at IIT Kharagpur. Dr. A.K. Roy, BARC, he basically bring this proposal to Professor G.L. Dattu, and then Professor G.L. Dattu, Professor Manna, and Dr. A.V. Bappert. He was from the beginning involved with this project, and he was the ex-head of PVD spark, and he was very dynamic and he was very involved from the beginning with her. And I will just give him a lot of impetus to Professor Dr. Babar. And Martin M., who is also presently at BARC, Martin G. also was there, and he worked basically from the ground state. Actually, he looked after all the electronics at there, and along with him, Dr. Kandaswamy, Mr. Kandaswamy, and Mr. Dr. Jha also associated. Okay, so these are the names I must remember. Okay, so this is the EBW setup at anti-ferrochromatotic at a glance. This is the setup set up by the BARC people, and this is the vacuum. As I say, vacuum is an essential part. So is the vacuum system that is there in place, and this is a whole picture from the side with the power supply. This was a new power supply. Initially started with the old power supply in 2009, and then 2012 the new power supply came, when actually the machine could operate with 60, 80 kV and 12 kilowatt mode. Okay, so I'll just start with my talk is basically show you the effect of beam oscillation, right? So some example I should give how the beam oscillation improve the weld properties, and then I will go to the explanation. Okay, so this is one very nice paper from from literature. I am showing you one paper, and they basically showed that is how the beam oscillation can produce. You can see there is the without beam oscillation with the circular beam oscillation, how the beams, that is the grain size has changed. You can see the grains become more spherical, that is the more equiaxed in case of the beam oscillation. In case without beam oscillation, it is mostly columnar type of. And also you can see grain size distribution. Also you can see the grains become more uniform in case of beam oscillation. So this is one of our work. My PhD student Jyotirmoy worked on it. That is the copper SS joined by electron beam welding with beam oscillation. Here you can see at high temperature tensile state we have done tensile test we have done for the welded sample, and what we find that there is a significant increase in the ductility of the weld. You can see, so ductility has increased. You can see from the data also. So without oscillation, the elongation is 7%. With oscillation, it is 40%. There is a 14%, just double. And copper, obviously, base metal ductility is much higher. But if you consider the weld without oscillation and with oscillation, it basically doubles the your ductility. That's it. And impact property thereby increases significantly. Okay. Then I will show you that is the copper, this joint. I am just showing you to microstructure. You can see what happens is that in case this is without oscillation, this is with oscillation. And with oscillation, we can find there is a dispersion of the globular copper particles in the weld zone. Okay, and this copper basically backfill the crack in the welds. Okay, that is clearly seen. But in case of non-oscillated beam, we do not find, and we find there is a big crack inside this thing. So basically, oscillation is the charging action is very evident, and that is the copper particles also get dispersed into the weld zone very nicely with the beam oscillation. That is not seen in case of without beam oscillation. And this is another work by one of my PhD students, that is Soumitra Dinda. He tried to join the DP600 steel to the 6061 aluminum alloys. And this type of joint is very difficult because iron and aluminum, you know, because they form a lot of intermetallics. That is the major bottleneck. But still, you can see here in this dissimilar joint, again, you can see that if you consider this is the steel, this is the aluminum side, this is the weld joint. And what you can find is that gate orientation, if you see, this is the EVDS, that is the, so you can find here that the grain orientation is only one type. Here you can find the grain orientation. Basically, it is called the copper texture, the blue. And in case of here, you can find this texture as well as brass texture also there. So there is a grain. Basically, what happens is the grains become oriented randomly in case of beam oscillation. In case of non-oscillating beam, the grains are directed in a particular orientation. Okay, so that is the grain orientation become more diverse with the beam oscillation. That is also seen there. And this is another work by my recent PhD student Lord, who basically worked on the jerk alloy. And you can see with and without beam oscillation. Without beam oscillation, he get a parallel plate with statement structure. Basically, you can get the parallel plates of alpha that is produced on the beta grain. And in this case, you can get a basket weave type structure. Basically, when we can get the basket weave structure, when we have the more random orientation of the grains, so they basically produce it. So basically, beam oscillation make the grain orientation more random. This is also seen here. And we have seen some porosity distribution also in the jerk alloy. One of my MTech students did that long back. So there also we can find that basically what happens with the beam oscillation, it reduces the number of your pores and sizes become small and spherical. That is the thing. More spherical, smaller size, well distributed, and count-wise also less. So beam oscillation also produces this thing. Okay, why beam oscillation enhance the weld properties? So thing is, the literature says that beam oscillation produces a churning action in the weld sheen that produces more uniform microstructure and enhanced weld properties. But why churning action? No clarity is there. That is why the beam oscillation will produce a churning action. Some literature say it produces more stable keyhole, but I am not very, I cannot find it more clearly. So we came up with a certain hypothesis, and that explained also some of the phenomena. Does churning action represent fluid mixing and convection in the weld? Possibly yes, that we'll see. And I will present some cases which reveals there's the power of liquid convection in the tiny weld pool. Because when the weld pool is formed, it is very tiny. In case of the arc welding, it may be some 3-4 millimeters. In case of the high energy density welding, the electron beam welding, laser welding, it will be less than 1 millimeter. It is so tiny, but the convection strength is very significant within that. I will just give you some example. You can see, so then I will come to the beam oscillation again. I will just go use some example where I show that is the how the liquid convection and the convective heat transfer can shape the weld pool shape. So you can see that is the hemispherical shape in case of the aluminum welding. And this is basically concave at the center. In case of the sodium nitride, some results are there. In case of the steel, you can have a convex shape in the weld center. Okay, so different type of things are there. Now, all this shape can be explained by basically the your convection phenomena. That is the fluid convection as well as the convective heat transfer. So Marangoni number is usually defined by the surface tension force to the viscous force. Okay, it has been found when the Marangoni number is less than 26,000, then you can usually get a hemispherical shape. And when Marangoni number is greater than 30,000, you start getting a complex shape of the weld joint, right? There is the non-hemispherical shape. And it is better if you add also the Prandtl number. Basically, all the shape can be explained into a two-dimensional Marangoni number, Prandtl number diagram. So here you can find when the Marangoni number is less than 26,000, as I said, always you'll get hemispherical one, irrespective of Prandtl number. But in case of when the Marangoni number is greater than 26,000, then you can get this type of different shape. And depending on the Prandtl number, you can give either the concave at the center, concave surface at the center, or if the Prandtl number is less, you can get a convex surface at the center. So that is the way. Basically, so this Marangoni number is basically gives you the liquid convection because of surface tension gradient. You produce a convection, and so liquid convection plays a great role. You can find it here. And again, another very classical example is the effect of the surface active element like sulfur. It has been found that sulfur can change the shape of the weld pool. right? So, but it always does not do that thing, because when the power is very high, you can find there is a definitely change in the shape. A presence of the surface active element make the pool much deeper, and in case of less sulfur, you can find that it is shallower pool. But it doesn't happen in, you can see always, because you can see here also there is no effect, because here the power input is less, only it is 1900 watt welding, and in this case 5000, that is the 5 kilowatt weld. So in this case, when the energy input is high, then only you can see the difference. But when energy input is less, you cannot see any difference. Because you can see, if you see the Marangoni convection in the iron and iron sulfide melt, in the iron melt, you can paint it will be like this, because when that is that is called the surface tension coefficient, that is the coefficient of surface tension, that is the d sigma dt. When it is negative, it is usually the case in in most of the metals, it is negative. And dt dx is always negative, so the product is positive, the shear stress is positive in case of the metal system. If shear stress is positive, that means the liquid will pull from the center to the surface, and then you will have this type of generation. With the surface active element, the situation becomes different, because d sigma dt become negative, become positive. D sigma dt become positive means that is your shear stress in this case will be negative. That means the liquid will flow in this direction. Because at high temperature, the surface tension become high, and low temperature surface tension low. So that's why the liquid is pulled in this direction. So you will have this type of pull in case the FES melt. In case of the pure iron melt, you will have this type of pull, right? And you can see that in this case, it makes a difference. This, when the pool is moving in this direction, so the pool is shallower. When the liquid is moving downward, it is digging the pool, then obviously it becomes bigger. So when the convection in the downward direction, there is a heat is convected towards the depth, obviously it becomes bigger. But it doesn't happen at the low power input. And because it doesn't happen, you can see that there is a fluid motion is like this only. If you melt, it is positive, and in case of the FES melt, it is in the downward direction. But it doesn't show any effect because of velocity. You can see the velocity is of the order of centimeter per second, and in this case, the velocity is of the order of 20, 20 times, or you can say 10 to 20 times higher when the power input is high. So convective strength is also very important. When the convective strength is high and the fluid is moving in the depth direction, then you can dig a bigger pool. That is the idea here. So another example I'll give, that we have seen, that is the heat conduction model always overpredicts the cooling rate, especially for high density welding. So you can see there is the two symbols are there. That is this symbol represent when the cooling load is calculated from heat conduction model, and square symbol when the cooling rate is calculated from the convective model. Okay, and this gives a ratio between the calculated value divided by the experimental value. So you can find that obviously in case of the conduction model overpredicts the your what is that? That is the aspect ratio. You can see cooling rate. That is the cooling rate, right? This cooling rate is overpredicts the cooling rate, especially at your aspect ratio when the aspect ratio is very small. That means aspect ratio is defined as W by D. That is the width versus depth. So width versus depth is less basically for high density welding when the penetration become high and the width become less. So in that case only disparity is more. So because in that case when the pool is very tiny, but your velocity gradient, that the temperature gradient is also very strong. As a result, Marangoni convection become very strong because surface tension gradient also become high. Marangoni convection also become high. So we should not ignore the convection even in a very, very tiny pool where convection plays a significant role. So this is what my idea, that is this convection. From there, I have tried to give a hypothesis for better mixing with the oscillated beam. So you can see that in case of the electron beam welding, the high energy density welding, that is the energy densities of the order of 1 gigawatt per meter square, compared to the arc welding when it is of the order of only kilowatt per meter square. Similarly, heat input, if you say, in case of the arc welding, it can be 20 gigajoule per centimeter. For electron beam welding, it may be less than 2 kilojoule per centimeter. So heat input also very less. So as the heat input is less, the cooling rate also becomes very fast. So in that case, what happens, what I was thinking is that when the beam moves away, when the beam, where is the beam, a liquid pool will form. Okay, as the beam moves away from that place, immediately that region will solidify because of higher cooling rate. So you can, there's a high energy density welding, you can conceive of a series of spot welds that are made one by one with a significant overlapping. So that was the thing. So weld seam may be considered as a collection of tiny weld spots severely overlapped with each other. So let's see that. So when I do without oscillation, just the beam is moving in a particular direction, then what happens is that because of Marangoni convection, and it is only in the pure weld, it is not, subsusceptible element is not there. So Marangoni convection is radially outward. So you can see the liquid is flowing radially outward in each pool. And so there are several weld pools are formed, they are severely overlapped. So you can find that is the, you can find that it will going radially outward. So what will happen? It will carry the heat from the central line towards the periphery. That is that towards the width direction, in the width direction. So your heat transfer is from the fusion zone to the hedge region like this. So as a result, your columnar grain flow from the hedge toward the center because the unidirectional heat flow is there. So basically that makes the columnar grain very prominent in case of the without beam oscillation. So with beam oscillation, what happens? You can see this is the picture I'm trying to give you. That is, this is the locus through which the beam oscillates during the circular beam oscillation like this way. So there is a one spot is formed. Then when the source move here, another weld spot is formed. This gets solidified. But when they are doing it, they get number of, there is a lot of overlapping is there into this thing. There is a very complex overlapping. And in this complex overlapping, how the heat can flow, I'm just trying to show here. Suppose you have 1, 2, 3, 4 overlapped heats are there. And in every weld pool, the liquid tries to pull off from the center to the radially outward. So heat will flow. So for if you consider the one, heat will flow from its center towards its periphery. So when the heat reaches here at the periphery, and it is basically the center of the weld spot 2. So then the heat from the weld spot 2 again moves from center to its periphery, and that becomes the center of the, say, weld spot 3. And from there, the heat moves from the center to the periphery. And that is, say, another weld spot 4 where center it is going there. So this is the way the heat can move in a very zigzag way between these weld spot, And that will basically give a mixing in the heat mixing in the weld spot. When there is a heat mixing, obviously, it reduces the temperature gradient with the weld seam. As a result, the grain cannot grow in a particular direction. It moves in a different direction. So that's why you will get random grains, and also you will get a more uniform properties throughout the grain. So that's why this is the again example I'm trying to show. So the columnar grain has been grown in case of the non-oscillating beam. In case of the oscillating beam, it is the fine grain structure. And that is the aqueous grain, and more uniform distribution of grain has appeared there. So with this, I will conclude my lecture. If you have any queries, you can ask. Thank you very much.
Thank you very much, Professor.
Yeah.
There is one question which appeared in the chat is about does beam oscillation affect the weld depth and time taken for welding of a sample?
Yeah, oscillation, because when you do the oscillation, then that is the heat input per unit length decreases because it traverses more distance per unit time. As a result, heat input decreases significantly. and as a result, your cooling rate will become very fast. Okay, so as the heat input decreases, that will mainly affect your heat affected zone, and everything will be much less. What is the question? There is the depth of the pool will be high or not?
Yeah.
Yeah,
Who
obviously
is
that.
going to?
Yeah, depth will may be affected. Yeah, depth may be affected because depth will be little less. Because here the heat input, that is the per unit length, that is the heat input is less. But it is a very concentrated beam. So if it is not a very thick shape, then it will not be affected that much. Cooling rate will be very high.
Yeah. Another question? I have one small question. See,
Yeah.
one of the shortcoming of the electron beam, welding is always a very high quality surface finish is the prerequisite for having a very sound bond. Okay. Now, when you are having this oscillation concept, probably that surface finish is not so much of the requirement. Do you have any comment on that?
No, we have seen that when we do the beam oscillation, the surface becomes much smoother. That is the hump and all these things is reduced and it becomes much smoother, and possibly because of this churning action that it produces, that we have found also. That is the surface becomes much smoother with oscillation and rather than without oscillation case.
Yeah. One more question from audience.
Thank you, sir.
Yeah.
I have one question. What is the beam radius and beam current?
Beam radius, that is electron beam characteristic of electron beam. What is there? That is the beam radius. Our case maybe 500 to 200 micrometer. That is the thing beam radius that we have. That is the characteristic that we don't vary with this thing. Maybe 200 micrometer like that.
Yeah. Another question now.
Good morning, sir.
Yeah.
Sir, I'm Prabhanjan.
Yeah.
Sir, my question is that how can I decide the oscillation frequency and the oscillation amplitude? Does
Yeah.
it have effect on weld width?
Yeah. That is there. Frequency we have not varied too much because we do not have option. And amplitude also have definitely be a problem because we do not have much option here in this electron beam. That is the amplitude and oscillation whether we can change. But what we can change is that oscillation diameter. That we have an option to change the oscillation diameter. That we have seen what is the effect of oscillation diameter. We have found that a optimum oscillation diameter is the most important one. That is, if you have a very high oscillation diameter, then also poverty enhancement is not very good. Sometimes we melt too much of copper, you have seen, and then copper dispersion do not become very good. Okay, and if it is very small also, then also it is not advantageous. Okay, so amplitude-wise, amplitude and we do not have much experience with that thing, amplitude as well as frequency, because in our system we cannot change that. That is fixed. Oscillation diameter we could change, and we have done it, and that has significant effect. Because without experiment we cannot do that. That was the problem. Yeah.
Now the last question.
Yeah.
Okay. Yeah.
Hello.
Yes.
Yes, I have a question that whenever we do EV welding, then a convex part is formed along the weld. So is this related with oscillation, or we can reduce that convex projection by manipulating the oscillation?
Yeah. I think that is very important. That is that thing basically occurs, that convex portion, because of shrinkage and all this thing. Because when you are doing, and oscillation has a very great role to play. We have found that when you do the beam oscillation, when there is the liquid churning action is there, and then you do not have too much of convex thing that will form. Okay, because during solidification, what happens? Because you do very fast cooling, na? So you have a solidification also very fast. As a result, because of lack of material, sometimes convex is formed. So if you have a good churning action, then that convection, that is that shrinkage effect will not be localized. It can be uniform. As a result, that convex portion will be less. You can try it with the beam oscillation. I think the convex effect and the convex formation will be less, much less. We have found that it become much smoother.
Okay, thank you, Professor.
Okay.
Being very illuminating talk, and a token of appreciation from our side, we are going to send you a plaque. We just wanted to show you the image, so kindly
Okay.
accept from our side.
Okay.
Yeah.
Yes.
Yeah.
So
Thank you very much.
Thank you very much. So I'll de-share this thing now.
Yeah, please do that.
Yeah, 1 minute. I think it has been done or not.
Now we will go to the last talk of the session. It is by Dr. L.J. Nayak, and he received his ME from the heat transfer from the BITM at Jharkhand in 2014, and before that he finished his mechanical engineering in BTech from the Biju Patnaik University of Technology at Odisha in 2008. He has worked as a senior research fellow in the Department of MME at IIT Kharagpur from 2015 to 19, and currently is pursuing his PhD at IIT Kharagpur. And he is on the verge of completion that. So now over to Dr. L.J. Nayak. Kindly start your talk now. You have 15 minutes. So try to finish in the 13 minutes. 2 minutes we'll keep for the question answers.
Yes, thank you.
Thank you. You can share your screen.
Yes, sir. Yes, sir. Is it visible, sir?
Yeah, it is visible now. Please
Okay.
go ahead.
Yes. So, myself, Lord Jagishan Nayak, and I'm a research scholar of Metallurgy and Materials Engineering Department, IIT Kharagpur. And today I
You have
present my...
probably
Yes.
unshared your screen. You share again.
Okay. Is it visible, sir?
Yes, it is visible now.
Okay. Visible, sir?
No, it is coming out in the sense. So you just stick
okay.
to
Okay.
the old one. Don't
Okay.
worry.
Okay. Understand. Now, okay, fine.
Yeah. Just
Okay.
go ahead with this mode.
Okay. So, myself, Lord Jagishan Nayak, and I'm a research scholar of Metallurgy and Materials Department, IIT Kharagpur. And today I present a topic on electrobeam welding of zircon 4 of dissimilar thickness. Before going to that, I have discussed some about the introduction of this my presentation. That zircon 4 is widely used in the nuclear industry as a structural material due to its low neutral absorption cross section, its stability, good mechanical properties, high corrosion resistance in elevated temperature. Electron beam welding method has a characteristics of high energy density, high efficiency, and low heat damage, reduced contamination under vacuum in comparison to other welding methods. So why are we doing dissimilar thick welding of zircon 4? Because it had advantages of reduction cost and weight and improve the structural performance of the weld. In our analysis, we have done some temperature measurement, and this temperature measurement during electron beam welding is a valuable parameter to assess the evolution of microstructure and mechanical properties in the weld. This is a schematic view of electron beam welding of the pressurized water reactors of parts of cladding to end flow that can be joined by electron beam welding. And now go for our experimental details. We have done some 6 experiments. We have done dissimilar weld of different plate thickness. In the joint 1 to joint 4, you see that voltage, current, and the speed are all constant, and heat input is also constant. So plate of different thickness are kind of welded, like in joint 1, 1.5 to 2.6, Similarly, joint 2 for 2.6 and 2.6, another 3.2 to 2.6, 4 to 2.6. That means one side plate is constant thickness, another side plate is a different thickness or can be used. So different thickness ratio is also you have got from that. So another two joints also prepared, but here the for joint 3 and joint 5 have same thickness ratio, but the heat input is increased here. We discussed about why we increase the heat input. Similarly, joint 6 of same thing for joint 4, but heat input is increased here for joint 6. Here two joints you see here, joint two plates, plate A and plate B here, and this plate A of thickness constant is 2.6 mm, that is right side plate, and plate B is left side plate. This thickness is changed, that means 1.5 to 4 mm. Here is considering 4 mm plate. For all cases, this plate is thickness can be varies from 1.5 mm to 4 mm thickness. So different thermocouples are used for our temperature measurements. Here thermocouple TC1 means thermocouple 1 to thermocouple 6, and one thermocouple also at the bottom side of the plate. So these thermocouple are used for during temperature measured using data acquisition system during electron beam welding. And this electron beam welding are we done in our IT Kharagpur electron beam welding lab. And now this is the thermocouple temperature measurement. This is the peak temperature versus distance from weld center line. And this peak temperature, this is the figure A. This indicates the joint 4, and this joint 4 indicates that thermocouple which is nearest to the weld center, so higher peak temperature that is from the weld center. Then we see that two line, one is a solid line, one is dotted line. The solid line indicates the temperature of the thinner plate, and so dotted line indicates the temperature of the thicker plate. Now we have to find that on temperature measured on both sides of thinner and thicker side of the plate, that temperature of the thicker plate shows lower temperature than the thinner plate. Let's say joint 6, we see in joint 6 that in joint 6, in case of joint 4, same thickness, thinner and thicker side, that means weld with 2.4 into 2.6 into 4 mm plate. But thing is that heat input is more, so the peak temperature is also increased here. But in that case also the thicker plate shows lower peak temperature than the thinner plates. Here we joint 1 to joint 4, that thickness ratio is increased here, so that 0.52 and 1.57 to 1.53. So the cooling rate also increased with increase in thickness ratio. On all cases, you find the thicker side shows higher cooling rate than the thinner side. Now, in our investigation, what we did, we optimize our parameters based on similar thickness, that 2.6 with the 2.6. So complete penetration is observed here, and we are validate our data with our finite dimensional model data and find close agreement with that of experiment data. And this is the fusion boundary, and this is the figure B shows the microstructure of the fusion zone, and figure C shows the microstructure of the hedge HHZ and slide close to base metal. And in fusion zone, you find some columnar grains in zircaloy 4 and within columnar grains. And in case of heat affected zones, we got equised grains in the porous equised grains in the heat affected zone, and fine equised grains in the base metal. So this is the in joint 2 we find complete penetration. This is the similar thickness, that once both side of the plate is similar thickness. Now at constant heat input, if the thickness of the another side of the plate is increased here, so that means another side 2.6 weld with now 4 mm plate. Now same heat input is constant here, and that is find also validated the finite model data and found a good agreement. And we find this is the top view. Figure C shows the top view of the fusion zone. This is the bottom view of the fusion zone of dissimilar thick weld of 2.6 mm with 4 mm thick plate. And top side, we see the large columnar grains are observed on the side of the fusion zone of the thinner side. Thinner side, so cooling rate is very slow, so the grains can be grow, and large columnar grains are observed. Or small columnar grains are observed in thicker side. So heat input is constant, and the one side thickness of the plate is increased here. So we got some defect like porosity, micropores. This is the micropores are developed at the bottom side of the plate, and some lack of ventilation is observed here. Similarly, this is the overall features, overview of the world of thinner side, and the thinner side shows a higher grain size, and thicker side shows lower small grains and small heat affected zone. So one thing is that now we have to increase the heat, so that as the thickness is increased, so you can increase the heat, so heat input, so that complete penetration is observed. So joint 6 is prepared here. So joint 6, same thickness ratio of 2.6 welded with 4 mm thick plate, but here heat input is increased, so complete penetration is observed. No defect like porosity, some lack of penetration is not observed here. Some results we got from our grain size of fusion zone heat affected zone of joint 1 and joint 6, and in all cases thicker showed small grains in comparison to thinner side of fusion zone on both in heat affected zone. Further, in joint 5 and joint 6 prepared with higher heat input, the grain size also increased in both in fusion zone in heat affected zone of thinner and thicker side. This is a scanning electron microscope image of high magnification image and high magnified image, and is the figure shows the base metal. The base metal of zircon 4 is equized grains. This is the equized grains having size around 15 micrometer. The high magnification image of fusion zone of joint 4. This fusion zone consists of columnar grains already discussed, and within the columnar grains, the lamellar in Wadman-Staton structure is observed. That in some cross-wave type structure is observed here. And in case of heat affected zone, this is the figure C and D are the heat affected zone on thicker and thinner side. And thicker side, the grain size of heat affected is small. So in heat affected zone, both thinner and thicker side, so acicular type structure within the equized grain, acicular type structure is observed. Next thing is our XRT analysis of joint 4 of fusion zone, and in XRT analysis we found different phases like alpha ZR, beta ZR, some ZR CR2, ZR3 Fe. Actually, in base metal, zircon 4 consists of alpha phase with the holding increases after then converted into beta phase. So there is some phase transformation temperature, that is 863. After that, all our beta phase is converted, and during cooling, during solidification process, that or alpha beta phase converted to alpha phase, but as the electron welding very fast cooling process, so all beta phase not converted to alpha, and converted to alpha, and the fusion consists of beta phase, alpha phase, and some second phase particular produced due to segregation, ZR2 and ZR3 Fe. This is the TM analysis. TM analysis, all alpha ZR phase is analyzed. This is the figure, so this is the lathe-like structure is observed in the fusion zone, high magnified image of using TM. And this is from SADP analysis. From SADP analysis, observed that the alpha ZR phase are SCP structure, hexagonal closed plate structure. However, we are not shown here the beta ZR phase. The beta ZR actually BC structure. The precipitator also found from our TEM analysis. This is the dark field, bright field, high magnification bright field image. This is the dark field image, and these precipitator are found here. That precipitator cannot easily identified, so it's a annealing operation, and during annealing it can be heat treated so that the precipitator can easily grow, and we can easily identify using TEM. And the precipitator are hexagonal closed structure and identified as ZRCR2. This is the porosity, and this is during zircon 4, joint 4, a similar thickness, porosity is very less. However, you increase the thickness ratio, cooling rate is very fast. So number of pores in joint 4 is increased, already shown on the from microstructure also. And the increasing as the cooling rate is increases in joint 4, that time for escaping the dissolved gases can be dissolved gases in zircon 4 is cannot be very minimum, so that there can produce pores within the fusion zone. So with increasing heat input in joint 6, again the porosity is reduced because that cooling rate is very slow. So the porosity and the better understanding, we can characterize the sphericity calculation, and the sphericity can be compared with pore diameter. That means sphericity indicate, that means when sphericity is equal to 1, then pore is considered perfectly sphere. And here when the pore is very small in size, the sphericity is very high, and the pore is very large value, the large size. So pore diameter is very large, the sphericity is very small. So this is the single largest view of 3D analysis. This porosity analysis you can analyze using our XCT X-ray computed tomography. So this is the schematic view of 3D image of the largest pore of joint 4, and this is the microstructural image of that pore. This is the tensile test we have done of joint of base metal and all. But we found that all joints are fractured in base metal. So the base so that tensile ultimate tensile strength, the yield strength are found very close to base metal. Ductility is reduced in weld joints. The reduction in ductility in weld joints in comparison to base metal is attributed to some corrosive microstructure, also maybe due to some second phase particles are developed within the fusion zone. However, joint 2 shows better elongation than that of joint 4. The joint 4 shows minimum elongation comparison joint 2 of similar thickness. That attributed to disparity of microstructure, because in dissimilar thickness, a different structure, that size of grains are developed with on thinner and thicker side. So that can affect the elongation of the joints. So is the all fractured in base metal? So this is the ductile mode of fracture is observed in all in case of base metal, also in case of weld joints also. This is a Charpy V nose impact test result. Charpy impact strength that the base metal shows higher impact strength than compared to the weld joints. All the weld joints shows minimum impact strength, and this is due to some second phase particles or maybe some microstructural morphology. In comparison, fracture analysis have done found the base metal consists of fibrous structure. However, in weld joints of nose samples or fracture analysis have done and found that this consists of mixed mode, that ductile mode and some cleavage structures are also observed. This cleavage structure may be attributed to separations of some minor second phase particles in the weld joints. I done some major conclusions I have present here. Butt joints of dissimilar thickness of zircon 4 prepared by electrobeam welding. Thicker plates showed lower peak temperature, fast cooling rate, finer grain size, and a small geometry, fusion zone, heat affected zone. Then those of thinner plate the weld penetration and increase in cooling rate in the fusion zone. Joint of dissimilar thickness demonstrate inferior ductility, impact strength, and then the joint of similar thickness. Further, at constant input, dissimilar thick weld joints show more number of pores than similar thick counterpart. Thank you. This is my complete out all of you. This work is already published in International Journal of Advanced Manufacturing Technology, and I thank to my guide, Professor Gaurav Roy sir of IT Metallurgy Department, IIT Kharagpur, under which I completed this work, and thank to all members of this conference.
Okay. Yeah, Dr. Naik, and
Yes.
question is there on the. Okay, in case just I wanted to know one thing, that you are not taking any oscillation on the surface. You are just taking the monotonic movement of the beam.
No, yeah, in this case, we have not taken an oscillation in this work, in particular work, but another paper we have published in Science and Technology Welding Joining. In that case, we have also done some oscillation work. This work is also published in STWJ.
No,
and
because some of these can be answered by using the oscillation beam.
Yes,
and
sir.
keeping different retention time on the different thickness samples. That would be very interesting study.
Yes. But presently you have not taking this. If in future we also concentrate on that work also. In different thickness we can use oscillation patterns, so that we can compare with her work.
Okay.
Yes.
Thank you, Mr. Naik.
Yes, sir.
Very best for your PhD work.
Yes, sir. Thank you.
Sir. Now we will close the session, and we will meet. I think I'll hand it over to Madam Raki.
So this is the end of this first morning session. Now we'll break for tea for 15 minutes. So before that, Thank you, Dr. Tiwari, for chairing this session. As a token of appreciation on behalf of the organizing committee, I request Nataraju sir to please come on the dais and present Dr. Tiwari with a small memento. So, what time? 12. So, we'll take a short break and meet up at 11:20 sharp.
तुम्हें खाओ ना मतलब भूख लगे
କବାଟ ଆସିକି ବାଡେଇ ଦେଇ ପଳେଇଲା ଆଉ ଖୋଲିଲାନି
फिर वो बड़ा कार्ड है सब
କନେକ୍ସନ
कनेक्शन कनेक्शन कर दे
ଡିସକନେକ୍ସନ
हे 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 हे
ହାତରେ କି ଥଣ୍ଡା
कमरा है बहुत थोड़ा है
ଦିଅ ଚଟକି ଏଇ ଗଲା ଗଲା ଗଲା
ये खुशी खुशी है बड़ा से करो की करते आसु देखो रो
Good afternoon, everybody. So we are starting the second session of the day, that is session number 6 on the generation of electron beam for non-thermal applications. Today's session chair is Professor Vandana Nanal from TIFR Mumbai. Dr. Nanal joined TIFR in 1998 as a faculty. She is a leading member of International Collaboration Paris. Her research interests cover a wide range from nuclear physics, accelerator physics, to development of detectors and associated instrumentation. She has published more than 160 research papers, and she is very active and passionate about women in science issues, and she is a joint convener of TIFR Vigyan Vidushi Sama program and member of Gender in Physics Working Group of IPA. I welcome Dr. Vandana Nanal to this session, and I invite her to chair this session.
Thank you, and thanks to the organizers for giving me this opportunity. Welcome everybody. I think after exciting morning session and with a tea break, we are looking forward to this session. We have total 4 talks here, 2 invited talks and 2 oral presentations, and very exciting topics. So we are already about 15 minutes late, so let's get started. I request all the speakers to also stick to the time in the interest of the time, as well as it will we should not cut into the discussion time. Discussions are important aspect of the talks. So the first talk is by Dr. Ranjana Gangadhe from IPR. She's going to talk about cryopump development at Institute for Plasma Research. So just a brief word about Dr. Ranjana. I guess you need to get her profile up on the display. She's currently the head of the cryopump and pellet injector division at IPR. Her work involves developing technology for exhaust and fueling of fusion machine. One of her major contributions is development of Vstaa, a gas trapping yantra in the indigenous cryopump. And this technology is patented and an important milestone for IPR and the country as a whole. The 3 units of Vstaa are installed on thermovac chambers at SPAC ISRO and on fusion machine at IPR. And the other developments include advanced technique for fueling plasma of a fusion machine and development of single pellet injector system. So over to you, Dr. Ranjana. Your talk is 25 minutes. I'll give you a warning after 5 minutes. After 20 minutes, that is 5-minute warning. Sorry.
Hello.
Yes, we can hear you, Dr. Ranjana.
Is my presentation visible?
No, not yet.
Just a minute. Is it not visible?
No. I think that, you have to first choose the window and then open the share. Yeah.
Yeah. Screen 1? No. Yeah. Screen. Share.
Yeah.
Is it visible?
Yes, yes. Please go ahead.
Yeah. Good morning, everybody. And I thank IVS for giving me this opportunity to brief about the development of cryopump at Institute for Plasma Research. So as necessity is the mother of invention, all started with the requirement of pumping helium in fusion machines. So when we went through as what can be the possible options for pumping helium, it came out that if one has to pump a large amount of gas load of helium in a magnetic environment, then commercial solutions were not up to the mark to take up such gas loads and such environment. So it all started from there. Now, just to give some introduction, all of us are from IVS, so I'll not go into the details of how cryopump works, etc. But just to say a few words, that cryopump produces vacuum by capturing gas molecules on cryopanels. Now, these cryopanels can be cooled by any means, like one can flow liquid helium or liquid nitrogen, or it can be through the conduction effects of conduction through the cold head of a closed cycle loop refrigerator systems like GM cryocoolers, etc. Gases are trapped onto the cryopanel surface either by cryocondensation or cryosorption. Now, cryosorption involves that you cool a surface and have a porous material on it. It is a physical adsorption, and the adsorption takes place through the van der Waals forces. So, this cryosorption helps the absorption of gas molecules on cooled porous sorbent at relatively high temperature compared to condensation of the gas for the same level of vacuum to be achieved. Now, for example, if we have to say pump nitrogen by cryo condensation, then one has to go down to a temperature of around below 25 K to get a vacuum of the level of -6, -7, and all depends on the saturated vapor pressure of the gas at the particular temperature. And similarly, if we want to go for pumping helium, then pumping helium is very difficult by condensation. So we took the option of going with the cryosorption technique. And in this, we had a long journey. Institute for Plasma Research initiated this work of developing cryo pump for pumping helium. And then now, in the meantime, a lot of work was done involving selecting sorbents, developing sorbents, the glue required to fix the sorbent to the metal plate, thermal cycling, testing of the adhesion for thermal cycling, then setting up the characterization facilities for study of adsorption isotherms, measurement of thermal conductivity at cryogenic temperatures, and facility to measure outgassing rate of different materials, etc. So this all work then resulted in development of a cryo pump, and now it is from concept to product. And I'm very happy to share that everything in it is indigenous, developed in the country. And not only that, the product has, the research has been successful in carrying out the pumping of these gases, but also that there was a requirement from ISRO and for pumping of cryovac chambers, and we could develop for SAC ISRO 3 cryo pumps against a purchase order. And these pumps are running well since about 10 years, and we have received appreciation from SAC director as well. So coming to cryo pump, how different from others, I'll not go into the detail. We all know this. It's a cryo pump is a capture pump, and there are various other techniques to create vacuum. But these the advantage of the cryo pump is that one can custom build it, and if the requirement of pumping very large gas loads is there, then this is a good option. Just to give a brief that what is the basis of its operation. It is, if we go for condensation kind, you can see that for pumping nitrogen, one needs to have, if one needs to have a vapor pressure of about -6 or -7 range, then one has to go down, say, below 25 K. And by condensation, helium is very difficult to pump. So, and the other, then this led us to go for cryoadsorption pump using porous material. So these are clean pump, and as only the fluid is a refrigerant which cools the pump, extremely low partial pressures can be achieved, and it can be custom built. Now, just to give you a glimpse, that what we had used was, we tried many sorbents. Finally, we went ahead using coconut shell charcoal. And these are the granules of the charcoal. And if you zoom and see it in SEM, then it has a lot of pores in it. And 1 tablespoon of, say, the charcoal can give us a pore surface area of about 1 soccer field. So if we have some, say, 500 grams, then 108 soccer field area the gases get to absorb. Whereas if we use condensation, say 1 square meter of a surface, then that much area is only available for gases to get absorbed. So this is the nature, the property which nature has given to the porous material like coconut shell charcoal that we have utilized, and went ahead with the development of the cryo pump. So one can see that huge area and hence huge capacity is there to pump the gases. Now, cryopumps are commercially available as a closed loop refrigerator based systems, and these have a lot of applications, mostly in the thin film industry, in the chip industry, in space research as well. So the other option is to go for liquid helium based ones, but commercial products are not available because it is very difficult to handle liquid helium. You have to have a very big infrastructure for that, and it's costly also. And liquid nitrogen based pump, no commercial product is not available. Now, as I was saying that why we went ahead with the development of the cryo pump, it was that in the fusion, we require to pump helium. And after the fusion reaction happens of the deuterium, tritium atoms, helium and neutrons are generated. So this helium has to be pumped out. And for that, commercial solution, at least for handling very large gas loads, is not available. So just to give an example of how much big the vessel is and the requirement to pump a large amount of gas load is, you can see that in the fusion machine ITER, the volume, this is the vacuum vessel, and in the vacuum vessel, the volume is about 800 meters square, and the cryostat housing superconducting coils, which has a volume of about 16,000 meters square. So, and the gas load to be pumped of helium is in the range of about 2,000 millibar liter per second. So enormous amount of gas loads are required to be pumped. So this initiated actually the development at IPR. Other requirements to pump in the fusion machine are, the key issues are that we need ultra high vacuum in large vessels, and large gas throughputs are to be pumped. Pumping speeds are required are very high. 100% reliability and maintainability is required over long operation time. Tritium compatibility is also required, and working under high magnetic field, because if we use anything with the rotation or mechanical moving part, then there is a problem of induced current setting up and stopping the hindering the rotation. So these are the limitations, and this this requires that one go for such a pump which has no moving parts, can give high pumping speed of helium, and should be lower on the side of maintenance. So this led to going ahead with the development of the cryo pump at IPR. Coming to the technologies required, since we are pumping through the cooling effect of to low temperatures, so there was a requirement to develop the cryo panels. We had developed hydroformed cryo panels for this. The commercial name is pillow plates. Then the sorbent development required, we tested a number of sorbents, right from charcoal to cloth to spheres, and and the requirement was that we should have a large pore surface area, and also it should not be brittle. Then there was the requirement of cryoadhesive development, which can stick the sorbent to the metal surface. And this cryoadhesive also we have developed in India, going up till 4 Kelvin, because 4 Kelvin adhesives are not available and within the country. one can import them. But the idea was to build up a completely indigenous technology. Hence, this cryoadhesive was also developed within the country. And at IPR, we collaborated with the company, and they gave many samples, and we tested it. These samples, the characterization for our requirement was done at IPR, measuring the thermal conductivity, the pore surface area, adsorption isotherm study of the sorbent, and the thermal cycling of adhesive, the outgassing rate of the adhesive, etc. Then other engineering aspects include that flow analysis, thermal analysis. The physics part includes that given any geometry, one has to test the transmission probability study. And then once all these studies are done, to have a test facility to test the pumping speed, etc. So then again, the regeneration study is how whether on regeneration the adhesion remains intact if we increase the temperature, etc. So all these studies were done, and then all the facilities were established at IPR. Facility for adsorption study, isotherm study at 4 Kelvin and liquid nitrogen temperatures. Now, this adsorption isotherm unit, which is bought out item, which operates at 80K, was some changes were made in it to measure it at till 4 Kelvin, the adsorption isotherms. The outgassing measurement facility was established. Thermal conductivity at low temperature system was, the facility was established. Then all this led to the development of cryoadsorption cryo pump for pumping helium. Initially, we just set up a very small cryo pump with a very small panel area of 500 centimeter by 10 centimeter. And this gave us a pumping speed of 2000 liters per second for helium. This we call small scale cryo pump facility. Then we went with a larger cryo panel. It's a pillow plate kind of panel, wherein we coated coconut. We used coconut shell charcoal here, and the panel surface area was about 0.4 meter square. The pumping speed that turned out to be was 14,000 liters per second for helium. Then we went ahead as the requirement in a fusion machines are large gas loads to be pumped and large pumping speed. We went with the 8-panel setup with an area of about 3.2 meters square, and this gave up a large pumping speed, 70,000 liters per second for helium, and 150,000 liters per second for hydrogen. So it was about 2.5 liters per second per centimeter square that the sorbent, when cooled to such temperatures, gave us the pumping speed. Just to know, am I audible? Hello?
Yeah, you're audible. Please
continue. Okay. So then we went ahead. The small setup which we tested, we call it as after this we went ahead with looking for, as this was due to our inquisitiveness, that whether we are able to pump nitrogen at liquid nitrogen temperature. Because if it happens, then it will be of a great application in large volume chambers, wherein lot of nitrogen and water vapor is to be pumped. So this led us to the development of a liquid nitrogen based cryo pump, and we call it as a cryogenic vacuum pumping system. I mean, this we have patented because we got very good results with this. And looking at the applications which it can have, uh, and other aspects, we went for a patent filing on this pump. And the patent application we have received, and the first FER is completed. So the good thing about this pump is that it can pump nitrogen at liquid nitrogen temperature. Otherwise, to pump in commercial pumps, one has to go to very low temperatures for pumping nitrogen. And it uses coconut shell charcoal as a sorbent. Also, the good thing, it gives the base once you bring vacuum by rotary up till -3 millibar, then the vacuum level that is attained after filling up of the liquid nitrogen path is -7 millibar, and then it needs no electrical power for operation. It has no moving parts, so no wear and tear. And also, since the adhesive is developed in the country, and we have tested it for thermal cycling, outgassing, thermal conductivity, etc., this the adhesive developed can go up till actually 200 degrees centigrade. So one can bake this pump to 150 degrees centigrade without any problem. And this gives a very clean regeneration. So it does not exhibit any hysteresis on regeneration. That is, no gas remains clogged in the pores after regeneration. So clean regeneration happens. So adhesion of charcoal on the surface has to withstand thermal cycling. So this was thoroughly tested in the lab. So just to give again, give a glimpse that here there is a liquid nitrogen bath at its center. And then we have cooled these cryo panels through conduction. The cryo panels are in 2 halves to have ease of assembly. These are then coated with the charcoal. The charcoal is also developed in the country and is steam activated one. And this was, we got many samples from Bangalore, and we checked its porosity and few samples classified for it. So this is how my people in the lab are doing all the studies and the adsorption isotherm setup and then the pumping speed setup. So,
Dr. Ranjana, you have 5 more minutes.
Okay. So then there was an MOU signed between ISRO and SAC for supply of 9 cryo pumps for pumping the cryovac chambers. And in this, 3 units have already been supplied. So the one which we supplied to ISRO, it is a 400 mm opening, and we have named it as branded it as Agastya. Technology transfer for it is available on our website, and the name acronym is a gas trapping yantra. The story is of Rishi Agastya drinking up all the oceans in a war between the gods and the demons, because the demons hid inside the ocean. So this pump has enormous pumping speed for the opening of 400 and commercial opening of 400. This pump gives large pumping speed for water vapor. So hence the name Agastya. So this is how the development took. We went ahead with the particle flow analysis for various geometries. Then geometry was finalized. Then all the structural thermal analysis were done, fabrication, coating, and then finally the Agastya. So the PDI by SAC team, ISRO team, and the team at IPR involved in the development of the cryo pump. So this is the pump which we had developed. It gives for air 5,000 liters per second, water around 15,000. The gas load which we pumped for 2-3 days, actually it was higher in the vacuum side, -2 millibar liter per second, and the base pressure maintained was in the range of -7 millibar. So capacity which we checked for is 6,000 millibar liter. So this is how it is installed in SAC ISRO Ahmedabad. This is the cryovac chamber, and here is the Agastya installed. So we got the product acceptance from SAC ISRO for the pump. And now we are also going ahead with the development of pumping high Z gases. So in this we are targeting argon and xenon. Applications are there in IPR as well, and also it can be of general use to ISRO SAC space research, as they have a lot of requirement of about 6.5 lakh liter per second for xenon. But we have initiated it on a small scale. First we tested in the lab setup with 1800 liter per second pumping speed for xenon. We have also developed for our internal usage at IPR for SST1. We have developed Agastya 500. This gives pumping speed of 26,000 liters per second for water vapor and 4,000 for nitrogen. And for our high heat flux facility, xenon cryo pump is under development for 14,000 liters per second for xenon. It will give the pumping speed. Now, what is special about SST1 cryo pump is that it can pump hot gases, because they require it during the baking of the machine. So we had to put a lot of baffles, and this reduced the pumping speed of nitrogen, because baffles were required to cool down the gases that finally come to the cryo panel. So wherever such applications are there, that chamber is baked and then one has to pump lot of water vapor and nitrogen, then one can use such configuration. So this pump has two baths. Actually, this is custom made for SST1. So one is a buffer, one is the bath wherein the cryo panels are attached, the other is a buffer bath, and this can operate for 10 hours without refilling. So no electrical power required for operation of pump once the rotary -3 level vacuum is achieved with using rotary. So it has 500 mm opening, and as said that it has a huge pumping speed, 26,000 liters per second for water vapor. So other works which we did was a few of the pumps had gone bad in URSC Bangalore, SAC ISRO. So we tried to give them solution by recoating their cryo panels, and now the pumps are working fine. On small units, they had these pumps are quite old, about more than 20 years old, and the pores had got blocked due to various things that have got pumped over the years. So we recoated and gave them, and it was like refurbishing their pumps, which were lying because they were not operating up to the mark. So thank you. And we acknowledge all the space research, the Cryogenic Center, IISc Bangalore, URSC Bangalore for all cooperation. And we thank our director for boosting our morale and giving all the encouragement, and the team at ISRO, SAC. Thank you.
Thank you, Dr. Ranjana, for really a very, very nice talk, and it's a very impressive work. I hope these cryo pumps will also soon become available to the other users, because I'm sure for there's a lot of need for these things, because these are really high vacuum pumps. So now the paper is open for discussion. Maybe first we can take from the convention center if there are any questions, and others then later people can raise a hand and then we can take some questions. Somebody can help me with from the convention center if there are any questions. To open the participants in the meeting.
Madam, congratulations for this indigenous development. My question is whether any base level vacuum is required before operation of this pump, or it starts from atmosphere?
No, -3 one has to bring with the rotary pump, and then one can operate the, one can fill up the central bath with liquid nitrogen. And as the bath gets filled, the vacuum level keeps going down. And with a small setup of 400 mm opening, one can reach about 1 into 10 to the power -7 millibar as a base pressure.
Thank you.
Okay, any other questions? If not, I have one quick question. So the regeneration mechanism, what is the have you tested with the RGA that whether it how long it retains the memory of the trapped gases?
It gives a very clean regeneration. We can regenerate it by two means. I mean, that's what we had tried in lab. One is one can, through the same chamber, I mean, wherein we fill the liquid nitrogen, one can let the hot nitrogen gas to pass so that the panels get regenerated. Now we have fitted heaters onto the panels for regeneration. And after regeneration, again, we checked for the base vacuum, and it was giving in the range of -7 millibar. So it gives the clean regeneration and doesn't clog the gases, because temperature, this adhesive which we have developed in the country can take a higher temperature. One can go up till 150 degree without any probe, but we have checked it up till 200 degree.
Okay, fine.
There is one more question from auditorium.
Okay, go ahead.
Good morning, ma'am. My question is this pump has been tested for any heating operation? If I want to use this pump for any vacuum furnace, so is this any testing has been done?
For vacuum furnace, we have not applied it yet, but like in the SST, the plasma facing components will be heated to 250 degrees centigrade. And the vessel of the SST one will be at about 150 degrees centigrade. So when this goes on, a lot of gases will be evolving from these components, and that we have actually tested in the lab by heating the gases and allowing it to get pumped by this 500 mm opening cryo pump. So furnace, I mean, one has to say as to what temperature you take it and what is the gas load, that also matters. So one has to, one can't put it directly into the very hot thing. One has to stepwise cool down the gases and bring. Yeah, but like when it enters the baffle side, 50 to 80 degree temperature is still there of the gases, and even in a step it cools down and reaches the crab panels.
There is one more question in the chat, and that probably can be the last question in the interval because we need to move on to the next talk. So this one is, what is the consumption rate of liquid nitrogen, liters per hour or liters per day?
Actually, we had operated it for 24 hours, and I mean, it depends, like different for different one. For 400 opening one, we had 250 liters of liquid nitrogen consumption was there. But like in SST, I said that once you fill up these total 72 liters of liquid nitrogen, then for 10 hours, you need not look at the pump. It will keep operating without any problem. So one can leave in the night and go. No issue.
Very good. Very good. Thanks very much, Dr. Ranjana. And I think we'd like to give you this token of appreciation on behalf of organizers, and all the best for your future developments. We look forward to more exciting new cryo pumps. And as I said, I hope it will soon become available for the others.
Yeah,
So thank
you.
Yeah, so let me move on to the second talk. And this with this online thing, we are really jumping from Bangalore, from Ahmedabad to Bangalore. And this talk will be given by Dr. Uma Rao. She is presently the head of solar panel characterization and analysis section at UR Rao Satellite Center, Bangalore. She worked in this section since 2000, from 2014, and she has worked also as a project manager for Mars Orbiter mission. She will be talking about electron radiation effect on multi-junction solar cells. So over to you, Dr. Uma. Dr. Uma, are you there? Yeah. Oh, she's present physically. Okay.
Hello, Dr. Umara will be presenting from the auditorium.
Okay, very nice. Yeah, good. So I'll give you a warning after 20 minutes. Yeah, please go ahead.
Okay. Are you able to hear me?
Yes.
Okay. Good. Open it. Screen is visible?
Yes, but it's
Yes.
coming as a part of the
Okay.
display, not full screen. It's more
Okay,
like a web browser.
can open.
You could just open it with some Adobe Reader or something, you can use Control L. Why is it been opened with a browser?
PDF. Session 6. Can I open my mail? 6. Yes. Okay. Is it visible? Now it's okay?
Well, the full slide is not visible because it is opened with the web browser. Is it possible to open it in a simple thing? But it's just simple PDF reader.
Just a minute.
Use open with command rather than default. Go to the file name, click on the right side. Click on the right mouse click and ask open with.
नहीं हो रहा है.
Okay, if it's not possible, but then you will have to adjust the display so that we see the full slide.
No, it's open.
Yeah, okay.
Share screen. Okay.
All right, great. Can you use Control L?
Okay.
Wonderful. Thank you.
Good morning to all the delegates and members present in this conference. I am very thankful to the organizers for inviting me for this talk, and especially Archana Sharma for giving me this opportunity to give the presentation here. I will be presenting the electron radiation effects on multi-junction solar cells. The space radiation contains mainly high energy electrons, protons, and gamma rays. It degrades the solar cell performance of the solar cell and E components. The solar cell degradation is mainly due to trapped electrons, trapped protons, and solar flare protons. In it's okay. In the low Earth orbit, the main interaction is from the trapped proton. In the low Earth orbit satellites generally move around in the Earth in the altitude of around 500 kilometer to 1,500 kilometer, whereas geosatellites orbit around the Earth around 36,000 kilometer, where the trapped electron and trapped protons and solar flare protons are the major contribution is from the trapped electron protons and solar flare protons. And this is the Val-Annel belt radiation. From the figure, you can see that there are two radiation belts. One is inner belt and another one is the outer belt. Inner belt is mainly, it is around 2 Earth radius. It will be around 2,000 kilometers. And whereas the outer radiation belt will be around 6 or it is around 36,000 kilometers, where our satellites generally operates. And this is the trapped electron spectra. It's for any typical geosynchronous orbit satellites. And from the graph, it is clear that all these trapped electrons are having the energies ranges from few kilo electron volts to 7 mega electron volts, and the fluences varies from 1 into 10 power 16 to 1 into 10 power 7 electrons per centimeter square. This is how the all these trapped electrons present in the orbits where our satellites orbit. And this is the trapped proton spectra. These are from the figure. It is clear that trapped proton spectra, the energies ranges from few hundred kilo electron volts to 400 mega electron volts. Similarly, the fluence is also varies from 1 into 10 power 16 to 1 into 10 power 7 protons per centimeter square. And solar flare spectrum is actually, it is having a fluence around 1 into 10 power 12, and it is having an energy up to 160 mega electron volts. Generally, all these energy particles will be moving around, but because of the Earth's magnetic field, they will be trapped, and they will cause a lot of troubles to the solar materials as well as the many spacecraft materials. And that's why it's very, very important to study this effect to understand the behavior of the solar cells as well as the electronic components after it is exposed to the radiation environment. The main interactions of concern when solar cells are irradiated with space radiation or atomic displacement. Atomic displacement occurs when fast electrons interact with the atomic nuclei, resulting in a displacement of an atom within the material structure. A displaced atom within the crystal lattice or the material structure will result in the formation of an interstitial atom, a vacancy, and other electronic defects. The displaced atoms will form stable defects and traps. These traps act as a recombination center and reduces the performance of solar cell and causes permanent damage to the cell and even the electronic component. And sometimes this degradation radiation effect will causes single event upset and single event latching also electronic component. But for the solar cell, it causes permanent damage. However, by doing some annealing like at slightly higher temperature around 80 degree for around 8 hours or 10 hours long exposure, we can slightly recover back, but it is only a small percentage, maybe 1 or 2%. But whatever the caused by the radiation, we cannot recover, and it's a permanent damage. And I'll talk about the basics of multi-junction solar cell. This photovoltaic solar array system is a primary source in all the near orbit as well as the geosynchronous orbit and interplanetary orbits. And even it is very much useful in the terrestrial application also, wherever for the terrestrial power generation, even for the house purpose also, solar panels are nowadays used. But because of its robustness, cost effectiveness, environmental friendly, and tolerance to the radiation for the space application. The multi-junction solar cell is a semiconductor device in which many solar cells are stacked monolithically, grown one over the other, as you seen in the picture. And this is actually the bottom germanium junction. It is having the energy gap of around 0.67 to 7 electron volts. And middle gallium arsenide junction, energy gap varies from 1.3 to 1.4 electron volt. And indium gallium phosphide is around, top junction is around 1.7 to 1.9 electron volt. These are all the materials, 3 junction materials are used to utilize the sun spectrum for all the regions, like 350 nanometer up to 1800 nanometer. The full spectrum can be used by this type of junction, whereas single junction cannot be used for the larger ranges. That's why the efficiency of the multi-junction solar cell is very high. At present, whatever available in the market, this efficient solar cell is around 30%. Efficiency of solar cell is around 30%. These are the solar cells are most of the manufacture of the satellites uses, because it reduces the mass as well as the area of the solar panel. And always the reduction in any mass or area of the solar panels, whichever the spacecraft is carrying, will be advantageous, because it reduces the cost of overall spacecraft as well as the launch cost. Everything will be reduced. That's why nowadays most of the solar cell used are the multi-junction solar cell. And lot of advances are happening to improve the efficiency of the solar cell by introducing 4th junction or 5th junction, but still they are all in the laboratory stages. In all solar cell manufacturing, this radiation tolerance or the effect of radiation very to assess the performance of the solar cell in the space, so that it will give the idea of how long this solar array can perform and what way it will perform. This will give the input to the mission management and how to operate the spacecraft, how much power is available for the different systems of the spacecraft. That's why it's very, very critical to know the space radiation effect on these solar cells. Need for the radiation study. The radiation degrades, as we all know that, as already explained earlier, radiation degrades the performance of the solar cell. As all we know, any failure of this component in the spacecraft is irreparable. We cannot, once the satellites are flown in the space, we cannot do any repair or anything of the components or the systems. That's why hence it is more important to assess and understand the performance. It is impractical to wait for the spacecraft mission life. Most of the spacecraft will have 5 to 10 years mission life and 15 years mission life in the geosynchronous orbit. We cannot wait for the to know or to understand how it behaves in 15 years. We cannot be waiting, because whatever the technology we develop at present, after 15 years, it can become absolute. We may not be able to use this technology. Hence, it is very, very important to understand when we develop any component or a solar cell, we should understand its behavior, how it behaves after 15 years also. In this regard, the electron radiation and proton radiation test facilities are very, very important to simulate the space-like environment, radiation environment at ground, and do the accelerated test. And this test, whatever we are waiting for 15 years of mission life in this spacecraft, this can happen within half an hour or 1 hour. We can expose the accumulated fluence. When we do the calculation and other things, we know, suppose the spacecraft is in 15 years in the orbit, what is the total fluence it will experience. There are some software, open softwares are available. From that, we will calculate how much will be the total mission accumulated fluence. By putting some margins in that, we can irradiate those samples in the ground radiation accelerated test accelerators, and we will know how the solar cell will behave or how the electronic component behaves. Across the globe, this practice is followed, and many ECSs and AI standards are written or framed how to do the test, how much dosage it should be put per second, and how many samples we should irradiate. All those things, informations are available in these standards. And electron radiation effect on multi-junction solar cells. Since the multi-junction solar cells are made up of monolithically grown different layers, understanding of the behavior of this solar cell is complicated when compared to the single junction solar cell. Single junction solar cell, it's very easy, like so that if you irradiate and one particular junction or one particular cell will be there, you will know which cell is, this cell is having how much like tolerance or how it is affected. But when it is a multi-junction, when the cells are stacked one over the other, to understand which subcell or which cell is having more tolerance or more radiation affected, this is very, very complicated. So this study is will be very important to know the how to, when the manufacturing of the solar cell happening, which cell is having more the tolerance or which is having the more effect. If we know, then it can be, the process can be improved and the different material can be used for the solar cell growth. That's why these studies are very, very important in the solar cell development as well as the usage. And these solar cells were, in this study, we have done the radiation studies by using different facilities across India. Multi-junction solar cells were irradiated with 1 MeV electron radiation at room temperature by using DC accelerator, and 10 MeV electron radiation by using RF Linac accelerator from Electron Beam Center, BARC, Mumbai. And different techniques are used to characterize the solar cell pre and post radiation. Means whatever we, means the cell we are going to irradiate, generally we will do the pre-test, like different characterization by using that, how the solar cell as a pristine, means without doing any radiation test, we will first irradiate, we will characterize those cells first, then irradiate with the different energies and fluences. And after each energy and after each fluence, we will characterize once again to compare how the behavior will be pre and post radiation. That will give the idea how the radiation has affected the solar cell or the electronic component. The electrical measurement of solar cell pre and post are carried out using the sun simulator, which is having a spectrum similar to the sun at 28 degree. And this is the typical IV characteristics of a multi-junction solar cell after 1 MeV electron radiation. From the graph, it is very clear that both the x-axis will give the voltage and y-axis is the current curve. And from the graph, it is clear that both the voltages and current get affected due to radiation. And also we can see that by increasing the fluence, like when they accumulate, like from the 1 into 10 power 13 to 1 into 10 power 15, if you go, the effect is more, means the degradation is more. And this will affect the efficiency of the solar cell also. And these are the remaining factor, means the pre to post, how much is the degradation happened. It is giving the both graphical as well as the tabulated values. From the tabulation, you can see that both the current and voltage degradation is around 10% after 1 into 10 power 15 electrons per centimeter square. And similarly, the 10 MeV electron radiation is also carried out, and this is also indicates that with the higher the fluence, the higher the degradation. And from the table, it is clear more than 12 to 15% degradation is happening for the voltages, around 10% degradation is happening for the current. And from both the curve, it is clear that the 10 MeV electron radiation creates more damages to the solar cell compared to the 1 MeV electron radiation. And the higher the energy, the more the damage. And we have used one more characterization method called spectral response to characterize the solar cell. Actually, the IV characteristic will give the overall performance of the full solar cell. To understand which subcell, which we are having 3 subcells in the multi-junction solar cell, which subcell is having the problem or the tolerance, by doing the spectral response, we can find out. Spectral response is one of the major characterization used to evaluate the solar cell damage caused by the radiation. Spectral response curve represents the conversion ability of the solar cell as a function of the incident wavelength. And by using the formula, whatever the JSC, the current density of the solar cell can be characterized. What is happening in the spectral response for each wavelength, what is the output of the solar cell can be verified or measured, and by integrating under the curve, we can get the total current density of the particular cell. And this is the response of the solar cell after irradiation. From the graph, it is, from the figure, it is clear that this is actually the response of the top solar cell, and this is the response of the middle junction solar cell. And from that, it is clear that middle junction solar cell is, the gallium arsenide solar cell is having the more effect in, due to radiation. It will degrade more compared to the top cell. And similarly, we have used one more technique called photoluminescence measurement. The photoluminescence measurement gives the numerous information on the materials and the device properties. They are therefore widely used for solar cell characterization to assess the absorption, resistance losses, or defect levels. They are fast and non-destructive characterization because we need not have any need not to prepare any special samples to do this. As a whole solar cell can be characterized using the PL measurement. This is a non-destructive technique. When the transition from an upper to a lower energy state can occur without emitting a photon, the emissions efficiency is decreased. This is the photoluminescence.
Uma?
Yes, madam.
I request you to wind up in 5 minutes.
Okay, fine. Okay. And these are the characterization of the solar cell at different fluences. Higher the fluences, the illumination intensity will reduce. This will indicate the non-recombination centers are happened due to radiation. The PL emission reduces after radiation because of defect state, and it indicates the non-radiative recombination after radiation. 2 peaks are with the solar cell. One is for the gallium arsenide. This is for the gallium arsenide, the middle junction. This is for the top junction, indium gallium phosphide. PL peak intensity of the gallium arsenide cell degraded dramatically or drastically after radiation. This degradation rate was more compared to gallium indium phosphide. The degradation rate of PL intensity of the gallium indium phosphide is much less than the gallium arsenide. From this study, it confirms that the middle gallium arsenide cell is more prone to the radiation. It degrades more compared to the top cell. And these are the IV characteristics of the solar cell. This is the bottom junction, this is the middle junction, this is the top junction, this is the overall full junction, integrated the solar cell. And after each radiation, it will reduces. And from the characteristics, we can find out the carrier lifetime of the solar cells. Carrier lifetime is the performance indicator of the solar cell, and it degrades with the radiation. And it means that it indicates that there are some recombination centers. And these are the calculated value of the
carrier lifetime of the at a different electron and proton radiation, and this from this it shows that radiation reduces the carrier lifetime of the solar cell in all the junctions. Radiation creates the traps in solar cell and acts as recombination center. The carrier lifetime degrades with the radiation, and also not only the electron, even the protons also degrades the performance of the solar cell, and it will be almost 3 times lesser than at lower fluence itself. It will create more damages compared to the electron. Suppose if we are having at one end to 10 power 15 having some kind of a degradation, this can happen with the proton. It can happen at around 1 into 10 power 12 itself. Means the degrades happens more with the proton at lower fluences. And these are the different electron accelerator across the world. This is our EBC accelerator, and this is 2 Delft University facility in Europe, and this is the JPL facility in USA, and this is the accelerator, and this is the sample holder. And almost all the solar cell manufacturer and users does this test before usage in the spacecraft. And my conclusion is space radiation contains energetic electron, proton, and gamma radiation. Solar cell is the major power generation source for all spacecraft. Space radiation degrades the performance of the solar cell as well as the electronic components permanently, and it affects the electrical performance. That's why ground accelerators are very, very important to study the behavior of the solar cell as well as the electronic component to assess the performance in space. Thank you. Thank you.
Thank you, Dr. Uma, for a very nice presentation, and also thank you for keeping to the time. Very nice work on solar cells. So the paper is now open for discussion. As you all know, we are running late, so we will take 1 or 2 short questions. So please.
Hello. Yes, ma'am. My question is that a multi-junction solar cell, after post-radiation, we examine its property at sun simulator at 28 degrees Celsius. But in space, the temperature is much lower than that. So what is the combined effect of radiation and temperature with the performance of the cells?
Actually, why we are using the 28 degrees for the comparison purpose. Always we should do at particular temperature. That's why we generally use as a room temperature for the characterization purpose, because it will give a very good comparison. Otherwise, if you do a different temperature, it will not give. But however, whatever you are asking is correct. In space, the temperature we expect around 55 to 60 degree, but there are some thermal coefficients are there. Means for the current, it will be around 3 milliamps per degree centigrade, and similarly for voltage, 6 millivolts per degree centigrade. We are having the thermal coefficient. We apply those thermal coefficient to the cell for different temperature. We will not be characterizing at so many temperature ranges. That's why we will do at a one particular temperature and extrapolate it to the required temperature by using the temperature coefficients.
Thank you, Dr. Uma.
Thank you, ma'am.
And
I think in certificate, the title of the talk is wrongly written.
yes, I was just coming to that it's wrong, but I hope the organizers would take care of it and give her the correct certificate as a token of appreciation. I also request organizers to hand over the memento to the speaker as a token of appreciation.
Head APPD, Buxing sir, to give the memento.
Thank you all for giving me this opportunity. Thank you.
Thank you. And let's move on to the next talk now. So the next talk is actually an oral presentation. Next to both talks are oral presentations. So the first we will have Dr. Rohit Shukla. He is working in pulse power and applied research from BRC Vizag, and he has received several Young Scientist Awards. So we look forward to an exciting presentation on Bremslong X-ray radiation energy spectrum analysis of 9 MeV electron beam line at ECIL Hyderabad. Over to you, Dr. Rohit, and your talk is 12 minutes, so I'll give you warning up.
वापस क्यों चला जाएगा? फिर से ले लिया। You see them? Is it visible, ma'am?
Yes, please. Go ahead.
Okay, thank you, ma'am. Good evening, good afternoon, everybody. This is the means I would like to thank organizers for giving opportunity to our team from Diagnostic and Application Group PPMD BRC Vizag to present some of the work done for the LINAC energy measurement means photon energy measurement spectroscopy basically, and also the special distribution of the photons being emitted by electron beam interaction with the target at facility of ECL Hyderabad, where the peak electron energy is 9 MeV and approximately 9 MeV. And we had to convert this facility, means a big team was involved to for the establishment first, and then to convert this facility to neutron emitting facility. Basically, conversion of electron LINAC to photon source, and then from photon source to photoneutron emission from the facility. So one step in between was to know the spectrum of energy, because every photoneutron element, sensitive element, will have a threshold energy. So we were willing to know how much photons are percent-wise falling in the threshold energy, minimum energy of a neutron emitting facility. So the other presentation with my senior colleague will be made for the, I think, photoneutron facility, but I am only presenting the work for the energy spectrum measurement of this electron beam LINAC at ECL Hyderabad. And opportunity for this measurement was given by Director VTDG ma'am, Archana Sharma, and colleagues Premanand De and Avnish Dubey. They all were supporting this all activity at that place. So the presentation contains basically introduction, then what we have done for that LINAC angular dose measurements and energy spectrum analysis, and then the results and conclusions. So main thing was that how focused or defocused the emission of the photons from the electron beam target interaction is happening in the system, and what is the energy spectrum, as we have already, I have already tried to explain that this was also one of the main motto of this experiment. So this is the basis of some basic thing about the LINAC, which ECL Hyderabad is having RF based LINAC. It is 9 MeV system with the maximum ERF of 200 Hertz. Peak beam current is 100 milliampere, average power is 1 kilowatt, and pulse width 5 microsecond. Beam diameter is 8 millimeters. Tantalum target is used to produce brahmastolon. And we have used this TLD pellets, basically calcium sulfate dysprosium doped, having 13.3 millimeter diameter and 0.7 millimeter thickness for the measurement, basically. And as attenuator rods, we have used the copper rods to reduce the basically the energy dose reaching to these pellets of various thicknesses, of course. So first was our angular dose measurement. So first thing is that these pellets were first of all irradiated at our BRC Mumbai facility for the known dose exposures, and these were prepared in the same batch and then radiated with the known dose source as Mumbai BRC to know the relative dose variation before using them, before starting or thinking even to use them for this type of experiment. So it is written that all readings were found within 4% of relative error. I think we selected the pellets of 4% relative error, and rest were discarded. And one more point over here is that we have taken the energy measurements for, I think, 2 orders of variation. So linearity test was quite impressively noted by these pellets for 2 orders of variation in the radiation dose. So what we did that we have placed the pellets at 50 centimeter distances and 100 centimeter distance apart from the X-ray source generation, which is this is our Linux tube, means just pictorially represented over here. And the pellets were placed at an equidistance from the one bore line, what we call it, and equally spaced by 7.5 degree, almost 7.5 degree, because thickness you can guess that it is already 13 mm diameter of the pellets. So 50 centimeter, 100 centimeter distance apart from these pellets were placed, and the radiation dose was given for such time where they have already been tested for the linearity of the measurement. So from these X-ray generation point, angular dose measurement was conducted. Total 7 pellets were used, one at as shown 0 degree, then interval of 7.5 degree, and on both sides, right and left, to see. This was also one type of experiment to find out that whether we have the symmetric output, means pellets are really working to the desired performance. So yeah, we got this waveform, and this is a waveform at 50 centimeter, and similar waveform was also noted at 100 centimeter distance also from the source. So you can see that the radiation dose was decaying down when we are moving towards off-bore side, and at nearly 22.5 degree, dose reduces up to 50 to 54% of the axis dose. So since we have done the measurement at 2 distances at 2 different times, so the measurement was means it was not only single time measurement, but multiple measurements were done for this objective. So this is 100 centimeter dose variation, and dose variation pattern is same as that of 50 centimeter distance, and angular dose variation is quite stable with linear distances. Now, in that same experimental run, as I have tried explaining that we wanted to know energy spectral analysis for photoneutron facility upgradation for this. So we have used a transmission method for measuring the energy spectrum. So these calcium sulfate, dysprosium doped calcium sulfate pellets were used for the transmitted dose measurement, and attenuation property of metal, means material, was used for giving attenuation on the way. So copper rods of varying thicknesses from 1.2 centimeter to 20 centimeters. You see, this length varied from 1.2 centimeter, which was means very low cutoff of reaching up to 800 kV or so, and then up to 20 centimeters long. Copper rods were used to shield it from the direct emission. Shield means to attenuate the direct radiation falling into the pellets. So TLD pellets were placed behind every attenuator to measure the transmitted dose, and then the pellets were exposed at Hyderabad and were okay. So my colleague has made this. Why transmission method is used? So it was a short run of experiment. No limitation of bandwidth was there. Bandwidth, he means to say that if we use photo multiplier tubes, etc., then the bandwidth limitations do come from the scintillator point of view, and also from the photo multiplier point of view. Here, energy was measured by the dosimeter pellets. So this type of limitations was not there, but of course it was easy for us to use the pellets for that experiment, and it was the first measurement done by our team. So again, another advantage was that in these high gray radiation environments, usually we find that electronics also get damage. So that was also one anticipation, and because of which we have chosen this scheme as a first step for measuring the energy spectrum. This is a
Dr.
pellet.
Rohit?
Yes, ma'am. Yes.
Sorry to interrupt. Can you wrap up in next 2 minutes?
Yes, ma'am. Yes, ma'am. So this is calcium sulfate dope, dysprosium dose pellet performance, which we have used for our reference basically. So here we can see that at beyond certain energies where we are operating, the reports by the developer group says that they are almost flat in responses. So energy dependency is not there. So that's why we found it useful in our case. This is the energy spectrum estimation already reported in some places where thickness and energy dependent thickness has to be accounted in our calculation, and the fitting has to be done accordingly, and one has to take resort of the data available of attenuation based on the energy, and then least square fitting is required to be conducted. So this is our experimental setup where the line neck is placed, and we have used our assembly over here near about 2 meters distance. And this is the inside view of the whole assembly, and every this rod is backed by a TLD pellet on the back side of it. So some were also placed in the front side of this to measure the direct dose also. So this is the whole thing inverted and shown in the inset over here. So these are the results basically of the energy attenuation. So these are the normalized doses which we found with some numerical methods fitted and experimental. And they were almost overlapping each other except at very low thicknesses where I have said that the cutoff of the radiation do happen. So that may be due to stray electron accumulated dose. This is one observation of from our side. Now this is the final energy spectrum of the fitting coming out from the system. So what the major conclusion is that photon counts are maximum at the range of 2 to 3 MeV. And we can use some target material for this purpose to make it photoneutron source, which was subsequently used also. And Weierstrass energy peak is nearing about 2.5 MeV. So conclusions are this, that angular dose measurement were carried out at various distances, and we got a symmetric dose pattern from the off-bore axis. And it was very useful for us in this type of setup. It is easy to be implemented and can be used for higher dose ambience also. To get better estimation of peak of spectrum, more number of attenuators can be placed in a possible peak region. So means probably aluminum or lower Z material. We have not tried, but we will try in some other runs also. So this is what one major observation from our side. And it is used, it can easily be used for beyond 200 kV as the waveform suggests. So this is my thanks to all the people who worked, as I have told Avnish and Premanand and Director VTDG for giving me opportunity to work over that facility in Hyderabad, and Hyderabad colleagues and other colleagues at BRC who have made this facility as the electron beam.
Thank you, Dr. Rohit.
Thank you.
Thank you for nicely sharing your results on these new radiation pellets with us and showing a good result. The paper is open for discussion, and as you know, since it's a part of the oral presentation competition, we would like to take a question.
Yeah, I have one question. So
Yeah.
the tantalum we have used for the conversion.
No, sir, not tantalum. Acha, okay, that is electron beam line. Yes, yes, sir.
Yes. So what is the thickness?
Sir, exact data actually I don't remember because the facility was given to me to do only energy measurement of photons from that. So I have not gone into the details of the this line basically. That is available with our APPD colleague in Mumbai. And if you write one email to us, sir, we will be happy to share it.
In this line, I have another question. Like if you are using a particular thickness, the spectrum, or the attenuation from there, the production also is a little different from, let us
So,
say,
sir,
you use another.
for that purpose, I would say that it is not that much thick as I have used for the copper. You know, for copper, we have used even 1.2 centimeter. Tantalum is very thin as compared to that copper also. So first stopper which we have used, the tantalum thickness is much lesser than that. And of course, in every LINAC-based photon sources, the cutoff starts from not even from tantalum, but behind there will be vacuum locks and etc. And there also the thicknesses do come into picture. So yes, of course, there will be a cutoff as you are pointing out because of this thickness, tantalum thickness, as well as the housing plate thickness, which is containing the vacuum inside the LINAC, which is output side basically.
We'll take one more question from the
Yes,
auditorium.
sure.
This is the
Please go
last
ahead.
question.
हाँ रोहित जी मुझे जस्ट ये पूछना है कि आपको जिस तरह का जो रेडिएशन है इसमें बैक स्कैटर जो रेडिएशन है उसके प्रोटेक्शन के लिए कुछ आपने मेजरमेंट में कुछ प्रोटेक्शन लिया था
सर बैक स्कैटर के लिए जो है हमें एक चीज इसमें ऑब्जर्व हुई थी यू हैव आस्क्ड वेरी इंटरेस्टिंग क्वेश्चन so from the back side in first experiment we found that there was a uniform exposure of some counts. So one we tried means subtracting that from all the measurements, and in next we have actually put one lead block from the back side also. So you have pointed out very nice things. So
Thank
back
you very much,
scatter was noted.
Dr. Rohit.
Yes.
I think we need to move on. So we'll move on to the last talk of the session,
Thank
which
you.
will be given by Mr. Dhruva Bhattacharya. He will be talking about design and development of 40 kV LAB6 cathode-based compact thermionic diode electron gun. He is working in the Accelerator and Pulse Power Division BRC and has a lot of experience in the operation of RF electron LINAC accelerators. So, Dhruvaji, you may start your presentation and I'll give you a warning after 10 minutes.
Hello, am I audible?
You are audible, but we are not able to see you yet.
You want to see me?
Yeah, your presentation is visible and we can see you. Yes, please go ahead.
Okay. So presentation visible and I'm audible, and thank you to the organizers for giving me an opportunity to speak on this occasion. And our paper is Vstaa 1088. It is OCP 08. It is based on design and development of 40 kV LAB6 cathode-based compact thermionic diode electron gun. So basically, as an introduction or motivation, we can say that APPD BRC has been involved in the indigenous design and development of RF electron accelerators for industrial applications and cargo scanning. 10 MeV 3 kilowatt and 6 and 4 MeV dual energy are typical RF electron LINACs which we have developed. Rotationally symmetric electron guns form an integral part of an RF electron accelerator. Here in this case, typically it is 40 kV and the beam currents are 1 to 1.5 ampere, pulsed beam of course, of 3 to 10 microsecond. Beam sizes are 4 to 5 mm at the entrance of RF cavity. So I'll be talking about the design and development of this diode electron gun, whereby electron gun simulations, cathode assembly, gun characterization, results, failures, compact gun, conclusion, and future work. So we all know that when I'm talking about this thermal electron gun, then there are two effects. One is the temperature and the work function effect, which is given by the Richardson-Dushman law. We all know that it depends on the temperature and the work function. The other is about the extraction voltage and the geometric effect, which is given by this Child-Langmuir law and comes under the space charge effect. And what will be the current extracted from an electron gun? It depends on the competition between these two or the lower one of this, either of these two. So if the Richardson-Dushman current is less than the Child-Langmuir law current, then it is a temperature limited operation. And if it is more, then it is a space charge limited operation. A typical electron gun configuration will be like this. There will be a cathode here, focusing electrode. There is an anode, and there are equipotential surfaces. We all know that there are two regions, or basically three regions. Two regions. Region 1 is a focusing lens region. Region 2 is a defocusing lens region, and region 3 is a field-free region, where we are talking about the universal beam spread curve that the beam follows here. Here we are talking about the diode electron gun mode, and here the cathode and the focusing electrode or grid we are calling, they are shorted and they are at the same potential, which will be a negative 40 kV, and the anode is definitely grounded in this case. Now, electron gun simulations we have tried to do with the standard software, that is the CST Particle Studio. We are aimed at 40 kV and spatial limited current of 1.4 ampere diode electron gun, and using a planar cathode. The beam size should be less than 4 mm and parallel or converging beam at the cavity entrance. That's what the requirement is from the LINAC side. We start off by optimizing the anode and focusing electrode or the grid shapes. We try to do the parametric study, and some of the parameters are the grid ID, the Pierce angle or the modified Pierce angle of the grid or the focusing electrode, the cathode anode gap, the cathode grid gap, the anode and grid curvatures. What the study reveals is that as the cathode anode gap increases, this arrow is increasing and the other arrow on the right hand side, beam current, that goes on decreasing. Cathode grid gap, if it increasing, beam current decreases, grid focusing angle increases, beam current increases, and grid opening dia, if it increases, and then the beam current increases. So we have to optimize or play around with this stuff. Simulation results, we found out that the grid ID is typically 14 mm, angle 60 degree. The length here, I can show you this is the grid. Basically, the length is about 6 mm. The curvature here is 3 mm. And this is the anode. And for the anode also, we have got an aperture of 8 mm. The length is about 7.5. The curvature is 2.5 mm. The cathode is here, and this is the cathode support or the cathode assembly. In this simulation, we have not put any material of the cathode because it's running in the spatial limited operation. Cathode diameter is 8 mm and it's a planar configuration. The cathode grid distance, that means the distance between here is 1.4 mm, and the cathode anode, that means from the cathode to this surface of the anode, is about 22 mm. The right-hand side shows the electric field strength, which is maximum at 5.24 kV per mm, which is at the grid tip somewhere here. That's tolerable because typically it is about 10 kV per mm on the surface. And all these materials which we will be using, which are stainless steel. This is the simulation stuff of the beam coming out from the cathode, getting focused, then slightly getting a parallel beam, and then getting defocused, where this is the region of the universal beam spread curve below. Somewhere here, we try to measure the beam size, of course, in the simulation, and that comes out to be something around 3.2 mm, which is at 40 mm from the cathode. That's from here, somewhere here. So 40 kV 1413 milliampere spatial limited beam current has been simulated. In the simulation, we have used mesh cells, typically about 34 lakh. People who do this simulation will understand this. Mesh step size is about 0.4, and the run time takes about 9 minutes per run. Which cathode we are using? We are typically using the lanthanum hexaborate cathode. The reasons here are its low work function, 2.6 eV, high melting point, high current density, low evaporation rates. One of the major advantages is that it can work in vacuum levels of 10⁻⁶ to -5 millibar. It's less sensitive contamination due to multiple air exposures. And any contaminated cathode can be reused with the high temperature of cathode. That's what we have experienced in our accelerators. Cathode size we have chosen is a planar LAB6 pellet of diameter 10 mm and thickness 1 mm. Heating is indirectly heated by a tungsten spring coil filament, which will come in later slides. So this is basically the cathode assembly. These are the SolidWorks models cut out. And the LAB6 pellet here is shown here somewhere, and it is kept in a rhenium cup, which is again kept in a tantalum cup. The filament wire is about 0.5 mm tungsten wire having 9 turns, and the filament dia is 5 millimeter. The gap between this cathode pellet and the filament is 2.5 mm typically. There are 2 radial heat shields, as you can see from here. We'll see some figures. This is the inner shield, this is the outer shield. They are made of tantalum. 2 tantalum rods are there to connect this filament. So these 2 tantalum rods and this is a cover cup, which you can see here, or in this right-hand side diagram, this is a cover cup. They are metallized and braced to the ceramic base. Tantalum cylinders connected to cover cup are by 3 legs. So this is leg 1, leg 2, and the other side this is leg 3. So these are some more figures. So this is again the tantalum cover cup, 2 legs. And 1 tantalum rod is connected to the tantalum cylinder. That means this rod is connected to the tantalum cylinder. That means this cylinder. so that the filament and this whole structure is at the same cathode potential, which we'll be putting up as minus 40 kV. So we are not using any bombardment type of electron gun here, where one can put a voltage between this filament and the cathode and can do some experiments there also. So beam emission is taking place from this 8 mm diameter of the cathode. This is the LAB6 pellet, which is a purple color. Now the compact gun assembly is consisting of a 60 kV DN63 ceramic isolator, which is a ceramic to metal joint. This is the isolator. And it is having 63 DN63 feed through flanges. So these are the feed through flanges from here. Okay. And there is an intermediate flange here which supports the anode. This is the top flange which supports a grid pipe, and that we are having this grid, and in between that we are having the cathode assembly. And then followed by intermediate flange, which is having again a pipe which is supporting this anode. And this whole thing is kept inside a water-cooled vacuum chamber. And there are these two ports are there, DN35CF, where we can connect sputtering pumps in the system. And in the test bench, we will see that we have put some window where we can see what's going on inside, or measure the temperature also. So the gun is operated in a diode mode. All we are using is a metal gaskets, which is OFHC copper, we heard in this case. So this is the developed electron gun, as you can see from the schematic.
Excuse me?
So, yeah, madam.
Yeah. Can you wrap up in another 2-3 minutes?
Oh,
yeah, because you have already taken 10 minutes.
Okay. So basically, this is the electron gun developed, and I'll just go back. So it has to be characterized on a test bench. So it is characterized on a test bench, which is here. So this is the electron gun, and this is the test bench. This is the Marx supply for giving the minus 40 kV. This is another view, and this is the port through which you can see that it is heated up. The cathode assembly is there. There is a procedure for characterizing the gun. We have to do high voltage conditioning, filament conditioning, beam extraction, and then again do high voltage conditioning. So this is basically the filament characteristics when we do the filament conditioning. So when the filament is hot, it goes up to something around 255 degree Kelvin. And after that, we do the high voltage conditioning in diode mode, and finally the beam extraction. So I'll show you the beam extractor. So this is the VI characteristics of the electron gun. Where this is the extracted voltage and the beam current and different filament powers. Another view of another figure is the beam current versus the filament power, and here are the extracted voltage which I'm applying slowly. So this is at the highest voltage 40 kV, and this is at somewhere at 5 kV. This is the showing the oscilloscope photo. Which is having this high voltage is at 40 kV, and there are 3 FCTs which are using, and they are at placed at different positions, and we are finally here in this experiment we got about 1400 milliampere of beam. There was some failure because the filament got touched to the cathode, and then we had to increase the distance, so thereby the power had gone up to 220 watt. Otherwise, typically we operate at around 190 to 200 watt. And if I want to see how compact the gun is, I can show you that there were some guns which were developed earlier. So these are the photographs of it. Next version is this, somewhere in 2012. This is the third version, which is there, and our previous speaker talked about the system in which this gun is connected. And this is the one is the latest gun which I have already shown the photograph. So it's quite compact. The weight has come down from 32 kgs in the first to about 8 or 9 kgs. So it's very easy to handle. And so this is our conclusion. Simulations give us 1413 milliampere. Experiments 220 watt, 1380 milliampere, 40 kV. Future work is beam size and emittance measurement. High beam trials at high PRF. Using water cooling. Here we have not used the water cooling right now. Cathode assembly modifications to reduce filament power, and finally we have wanted to go for automated filament conditioning. So we'd like to thank all the colleagues for discussions and technical support in this development work, and thank you all.
Thank you. The paper is now open for discussion. Nice to have these different cathodes and informations on that. We can have a couple of quick questions.
Hello.
Yeah.
Sir, my question is that you have used spring type wire cathode. Is there any specific reason behind it?
So there is an echo.
Spring type wire cathode you are using.
Spring, okay, filament.
Yeah, is
That's-
there any
that's-
specific reason behind it, or if it is, or what is the advantages of this? Please.
See, you have to do, either you can directly heat the cathode or you can indirectly heat the cathode. If you have to indirectly heat the cathode, you have to use some filament. It can be a spring type or it can be a pancake type or a non-inductive type. Okay. And you can directly heat also. Directly heat means you put some, let's say, around the cathode, you put some graphite sort of connector and then you pass on the current through it. So thereby the current flows through the graphite and through the LAB6 and comes back. So that's one way to heat the LAB6. So which we have not tried.
Sir, my question is that why is that spring type?
Why is-
Because why that spring type you have chosen?
Spring type?
Yeah, spring type.
Spring type of filament.
Yeah.
Why? You can use any other type. You can use a spiral type of also.
Okay.
You can use any. I mean, so it was developed in-house, so it is easy to, fabricate it in-house. Or else you have to fabricate it as spiral type, that you can get it from a vendor also. Yeah, sorry.
Okay. All right. So let's thank Mr. Dhruva Bhattacharya.
one more
once.
question.
Is there? I'll just.
Okay, go ahead.
Did you experiment with extraction field? Any extraction be in between the cathode anode?
No, we have not tried. We will be.
You can extract more current if you have a extractor assembly.
You want to say that extraction between the filament and the cathode? We have not tried. We want to try that. And I think that will help. So in case of that, I believe 220 watts will be much more reduced to maybe around 160 or 150 watt, depending on what. We want to try that. Yeah.
Okay, it's getting late. So
one
maybe
more.
I think organizers told me to wrap up the session.
Dr. Dhruva, have you tried this thorioti tungsten or ytteria coated?
I'm sorry, there's a lot of echo here.
Have you tried this cathode based on ytterium tungsten filament or?
No.
Because
I have
these
not
are
tried,
also-
but I have not tried it. But I heard that this tungsten rhenium combination, that means I think 3% to 23%, 25% rhenium in a tungsten would be much more better or flexible in terms of its life and stuff for the filament. You have
Another one is the
I think it's getting late, so let us, you can discuss it over lunch now because people are present there. So it was not like a session coming from there. So
Sure.
thank you very much. And I request organizers to hand over the memento to the speaker.
I call upon Dr. Umar Rao to give the
Thank you.
present memento.
So thank you.
Yeah, thank you. Thank you, madam.
Back to the organizers. Thank you.
Now, I thank Professor Vandana Nanal to be with us during the session and chairing the session very nicely. Thank you so much, madam.
Thank you.
So this session is over. Now we'll meet around 1:45 after the lunch.
Hello. Can we stop the music, please? And we are ready to start the session. Yeah. Good afternoon, everybody. We are ready to start the session. This is session 7 of Vstaa 2022. This session is titled Development of Vacuum Devices and Electron Emitters. We are already running half an hour behind schedule. There are 7 talks in this. First 3 are invited talks. Last 4 are oral presentations. The titles of the talks are displayed here. The first talk is from Dr. L.M. Pant. Before he starts his talk, I will give him a brief outlook of Dr. Pant. Dr. Lalit Mohan Pant joined BRC Training School 31st batch in the year 1987 after completion of his MSc Physics in Lucknow University. He started his scientific career in 1988 at the Nuclear Research Laboratory with the Gamma Ray Astronomy Group at High Altitude Research Lab at Gulmarg, Kashmir. He was investigating the gamma ray sources with atmospheric Cherenkov telescopes. Later, he joined Nuclear Physics Division BRC in 1990. He completed his PhD in the year 2001 from Mumbai University. Soon after, he joined postdoctoral research at esteemed universities from Germany. He was actively involved in the CMS experiment in CERN, development of RPCs in INO, and his achievement includes successful installation and commissioning of ISM-RAN, Indian Scintillator Matrix for reactor anti-neutrino detection, project in Dhruva Hall for studies of sterile neutrino searches and reactor power monitoring. He is presently heading TPD, Technical Physics Division, BRC, since last year. Today, he will be talking to us on his latest work in searches for sterile neutrinos through measurement of reactor anti-neutrinos. Dr. L.M. Pant, sir. Stage is over to you. Thank you. Sir, I kindly request you to keep the talk to 25 plus 5, 25 minutes plus 5. Thank you.
So good afternoon. Am I audible? Okay, so first, thanks to the organizers of Vstaa for this opportunity to discuss about neutrinos, which are also sterile. And so as you see on the screen right now, and thank you, Bhushan, for the nice introduction. Thanks a lot to you. So the topic, as you see, is the sterile neutrino interaction. What is this black thing coming here? No, I don't want to go to the next slide. The title itself is hiding there, no? Sterile. Okay, so sterile neutrino searches with reactor antineutrinos, and as you see in the background, we have this. We have the Dhruva and the Cyrus reactors. So most of the programs in DAE started with reactors. The reactors got upgraded, and finally we moved to the accelerators also. The story which I'm going to discuss with you for the next 25 minutes basically starts from the Dhruva reactor. So the next few slides will be, I'll just try to set up about the neutrino things. So as you see here, the standard model of elementary particles, we have the quarks on the top, and these are the leptons. And the leptons include the three types of neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. They are basically the three generations, 1, 2, and 3, as and when they were discovered sequentially. And we are lucky to live in this era where the Higgs boson was also discovered, for which the Nobel Prize was given in 2013. So let me go through this. This animation is not working in this because I wanted these to come in parts actually, so it's not possible. If it's going to take too much time, I can go ahead with this. So as I said, we have these three, and thank you for this animation part, because it will be easier for me to discuss things and present them. So we have these three generations of neutrinos, the electron, the muon, and the tau, as and when they were discovered. And then we had, of course, the Higgs boson, which was discovered in 2012, for which the Nobel Prize was given in 2013. We all know that neutrino was proposed by Pauli in 1930. It's just a flip from the neutron to a proton, and which emits an antineutrino in the process. So neutrinos have these three leptonic flavors. They do not carry any charge, and their motion is influenced only by the weak nuclear force. This makes them notoriously difficult to detect. Now, what do we mean by difficult to detect? We all know that in, for example, the mean free path, if we consider, which basically translates to the interactions, the mean free path of an oxygen molecule in a room at, say, 0 degrees Celsius at 1 atmospheric pressure is about hundreds of nanometers. Now, when we talk about neutrino, a 1 MeV neutrino, in its mean free path in a material like lead, which is quite dense, about 11.9 grams per centimeter cube, the mean free path for a 1 MeV neutrino is 1 light year. So that is the sort of interactions they have. So they are extremely difficult. They interact. Interaction cross sections are very small, and so detecting them is much more difficult and challenging. So electron was discovered in 1897. So I'm just trying to give you a time flavor. And the electron neutrino was discovered in 1956 by Cowan-Rines experiment. And this forms the basis of all the measurements, all the setup which we have put up in the Dhruva reactor. Next was the muon, which is, these are all leptons. But as you see from this green dot, it becomes larger in size because of its mass. And so it has a mean lifetime of about 2.2 microsecond. And this was discovered in 1962 by Lederman, Schwartz, and Steinberger. As we move ahead, the tau, which is about 1.7 GeV in mass, was discovered from a big collaboration at SLAC and LBNL. And so they discovered the corresponding tau neutrino just in 2000 in the donut collaboration at Fermilab. So neutrinos, they are the most intriguing member of the standard model of physics, particle physics, and in the standard model, they are termed as massless. The Wolfgang-Pauli postulated in 1930, and in 1934, the theoretical framework was presented by Fermi, and finally in 1956, we could see the discovery of the neutrino by Rines and Covens. If we see how the things have changed in the neutrino field, 1995, this was the first experimental detection of neutrino by Rines and Cowen, but Cowen, because he died in 1974, so he couldn't get the Nobel Prize, but this discovery was made in 1956. 2002, we got a Nobel Prize for detection of cosmic neutrino, and finally in 2015, the Nobel Prize was given for the discovery of neutrino oscillations. The neutrinos oscillate between their mass eigenstates, the electron, the muon, and the tau. Kajita, as you see here, Kajita happened to be in BRC in December 2019. So these are the people who have really changed the whole scenario. And once the neutrino comes out of the standard model, means it is supposed to have a little mass with it, associated with it, the entire physics gets opened up into a new window, and it opens up the basic research for dark matter. So it is the fundamental particle, most abundant after photons in the universe. It interacts only with the via weak interaction, spin-half particle, electrically neutral, exits in 3 different flavor states, the electron, muon, and tau, and then oscillates between their mass eigenstates. It is kept massless in standard model, and that's why the physics which has come is called BSE, Beyond Standard Model. BSM, Beyond Standard Model Physics. So neutrinos are around us. And if you just put a banana on the breakfast table, it is emitting about 1 million neutrinos per day. Now, where these neutrinos come from? They basically come from the potassium, and any of the food ingredients which are having potassium and potassium-40 in it is bound to emit neutrinos. 90% of them are through the antineutrinos, and the remaining 10% comes from the neutrino. Then we have the sun, which is very close to us in the universe. And most of the neutrinos passing through the Earth emanate from the sun. They are about 10 to the power 10 solar neutrinos per second per centimeter square passing in a perpendicular direction to the sun. So you can imagine the flux of these neutrinos. Now, if you consider the photons and the neutrino, and suppose they are originating at the core of the sun, photons interact. So from the core, they will take about 200,000 years to come out on the surface of the sun, whereas neutrinos will just zip out within 2 seconds or so. Now, here I'm just trying to show you a pictorial representation of when the neutrino was discovered in 1956, but then we would like to see photographs. So in this photograph, if you see here is a mu-type neutrino coming, and it is interacting. And then you have the proton, which is on the top. Then you have the muon, mu minus, the blue line, and then you have the pi plus. They are in a magnetic field in a bubble chamber, and this was an experimental verification, though it was discovered in 56, to really show you, and they're bending in the magnetic field according to the E/M ratio. Now, this slide basically shows you the flux of the neutrinos coming from all possible things. And our interest is basically in these neutrinos, which are shown in this yellow band, which are coming from the power plants or the research reactors. Their energy range is few MeV. And as you see, the active galactic nuclei, the neutrinos coming from alien sources, they go up to almost TeV to PeV range. The fluxes are quite high for the cosmological neutrinos. Our focus will be here in the yellow band. So neutrinos play a crucial role in several eminent astrophysical and cosmological events in the universe. There are a list of things which I'm not going to discuss. I'm only going to talk about the sterile neutrino oscillations and the background for dark matter searches. These are the two things which we had been pursuing for last 6 years and would like to pursue for the next 4 to 5 years. And so let me just go through this curve, which looks quite puzzling for those who are viewing it for the first time. But on the extreme right, if you see here, there's a pointer here. So what you see here, if there were no oscillations, then you would have got this dotted curve here on the top. But since there are 3 flavors, and neutrinos are oscillating from one flavor to the other, so this dip that you see here, and on the x-axis, what you have is the distance from the source which is producing those neutrinos. So at a distance of about 100 kilometers or so, this dip was nicely explained by the 3-flavor neutrino. That is the electron, the muon, and the tau. Further, when you move to smaller distances, about a kilometer or so, another dip was explained on the basis of the 3-flavor neutrinos, and that is this gray part which is going here. So if this 3-flavor was okay, then it would have just merged here and gone like this. But then you see here, which is very close to the reactors, within a distance of 100 meters or so, where the lot of data which is existing shows which is not matching with this dashed lines. And this is called the reactor antineutrino anomaly. And so most of the experiments, as you see here, they are planned in this Terra Incognita. About 20 projects are there. And we have also initiated a project which is called ISMRAN. I will come to SMRAN later on. It is an acronym for Indian Scintillator Matrix for Reactor Antineutrinos, and it is situated at a 13-meter distance from the core of the Dhruva reactor. So we know that in the fission process, normally it's a thermal neutron and interacting with this uranium-235, and then there's a series of beta decays. So on an average, in a fission, we have about 6 antineutrinos produced. In the reactors, we have the antineutrinos, which are coming out of the electron type. So if we have a gigawatt reactor, this is the typical flux of antineutrinos which will be emitted. So this large flux basically counterbalances their very low interaction cross-section, which gives us a reasonable count rates. Here again, we go back to Rhines and Kovin. So here is Rhines, and this was discovered in 1956. In a reactor, here liquid scintillators are used, and photomultipliers are put here. And liquid scintillator technology was initiated at that time. But what we have done is the plastic-based scintillators we have used. And so we'll come to that, ISMRAN. So these are some calculations, number of free protons in 1 cubic meter. So we have used plastic scintillators, which are 10 by 10 centimeter in cross-section and 1 meter in length, about 90 of them, which add up to about 1 ton. The detector efficiency is 15%. These are the number of hydrogen atoms present there, a large number of target nuclei. So what happens, the antineutrino basically interacts with the proton and produces a positron and a neutron. The bulk of the energy is taken away by the positron, and a little energy is taken away by the neutron. The neutron will get thermalized, and then there are gadolinium wrappings in which they will be absorbed and produce a cascade of gamma rays. This positron, after depositing its initial kinetic energy, will get thermalized, and finally, at the end point of its range, it will annihilate with the electron and again produce these 2 photons here. Now, in Google, if you just search any of the neutrino programs, you will find that they run into kilotons. They are underground. This particular experiment has a lot of challenges because, first of all, it is overground. It is inside a reactor hall. So not only you have the cosmogenic background, you also have the reactor background, which has to be nicely shielded so that you don't confuse between the neutron which is produced in the interaction. This is called inverse beta decay. So that we do not take any of those neutrons which are present already in the reactor hall. We are only looking for the neutrons which are produced in this interaction, and then we try to establish a correlation between this positron and this neutron. So I will not go into the details of those humongous analysis which has been evolved to really separate these correlated events inside shielding in the reactor hall. But I'll definitely share the results with you. And now a slight changer, because I would like to acknowledge many people here right in the middle of my talk, because towards the end it just becomes like a flashing slide. So first of all, we are indebted to Dr. A.K. Mohanty, Director BARC, who had the insight and the foresight for the Ismaran project, as well as what we are going to do with the Apsara U right now in next 2 to 3 years. Professor V.M. Datar, who was also the head for Nuclear Physics Division, and students, of course, who are with us in this project and who have moved to other places and who are still working with us, and a series of divisions in BRC, Nuclear Physics Division, Technical Physics Division, EMID, CDM, ROD, RSD, RRSD, and NICER Bhubaneswar. And my apologies, because these slides are prepared at 1 o'clock in the night. I forgot to put Electronics Division into this. So they all have helped us into whatever I'm going to present in the next slides. So this is the simulation that was started by the people in the Nuclear Physics Division about the shielding. Already we have 10 centimeter of borated polythene to cut the neutrons and 10 centimeter of lead to cut the gamma rays. We could not increase this infinitely because there's a load bearing capacity at the Zuba about 30 tons per meter square. So these things are optimized. And so we finally came to a 10 centimeter configuration. So what you see on the top is the accepted events for the 10 centimeter lead. And for here you have the neutrons at 1 MeV with a 10 centimeter thick BP sheet. About only 1% were accepted. But then these don't bother us because we are looking for the correlations and coincidences. And in those things, all this background gets wiped out. So the proposed detector was presented that this is the configuration which we want. And then physicists just proposed something, and this is what the beautiful thing was made by the CDM people, and this has been realized, and it has been commissioned in the Dhua Reactor Hall. And so it took about 3 years to really complete this juggernaut. I call it a juggernaut because it is on wheels, and when the first photograph came like that, the first impression I got, it is almost like a Jagannath Rath. So these 3 wheels were there, they were finally trimmed down, and we have it only on 2 wheels with this jack support. The total weight is about 19 tons, including the core detector. So the core detector is just this much here, which is just 1 ton. So compare this with the kiloton detector, which are there for the neutrino physics programs. So this was the start of the story about 6 years back when we had a mini Smaran. We had just 16 scintillators. This is how we started building up the mini Smaran. And then you see the shieldings here. This was followed by covering the entire detector. So just 16 of these scintillators weighed 160 kilograms, but the entire shielding was about close to 8 tons. And then we had to put a little bit of HDPE also to further reduce the thermal neutrons moving around in the reactor hall. And the electronics that was employed was just a digitizer. As you see here, these 16 bars have got 32 outputs, and only 32 cables are going into the digitizers here. So there's no complicated electronics involved. This just saves the waveform as it comes, and we do the analysis offline. So here what you see is the measurements made on one of the plastic scintillator bars when the reactor is on and off. So in the reactor, also, you have this cosmogenic background which merges nicely with and without shielding. And these are the cosmic muons here, close to about 20 MeV. And this is the region where all that mystery is hidden about the neutrinos coming from the reactors. The typical energy range is from 1 to 8 MeV. So this campaign was run. Luckily, reactor goes off for certain reasons, and that becomes a mining ground for us. As you see, the reactor was off for 22 days, and we got about 7 antineutrinos. Now, these neutrinos are not coming from the reactor, but there are various processes happening in the reactor hall which can generate these neutrinos. So 7 neutrinos in 22 days when the reactor was off. When the reactor was on for the 3 campaigns, we got these are the numbers with some statistical errors. But please remember, this is a very small configuration, 16 bars. And from here, we have gone almost to 90 bars, which I will show you down the slides. So this was the first smoking gun signal that we got about detection of antineutrinos. And I'm again telling you, I'm not discussing the analysis part here. It is very, very complicated and to arrive at these numbers, taking care that we do not count any of the fake neutrons or positrons. And this is the line shape, which gave us the confidence. This is the line shape of the, and this is basically for the positron. But as I said, positron being the lighter in mass carries away most of the energy. So this line shape gave us the confidence that we are in the right direction with this mini Smaran. And finally, this paper got published just in January this year in NIM. And so, but before that, we had already started making the full-scale Smaran in Dhruva reactor. And so these here you see, these are those plastic scintillators. They are 1 meter in length, read by photomultipliers at both the ends. So all this was happening in the last year at Dhruva. As you see, this is the final matrix, which we called Smaran. 90 scintillators. And then you see here on the top, there are slots available. This is the lead, 10 centimeter on all the sides in stainless steel containers. And then the bolted polythene is on the outside on all the 6 faces. But then once you lock this, you will have no access to these scintillators. So a provision was made that on the top, you will have holes so that in situ, we can calibrate the detectors. So these are the holes which are made on the top covers also. And this is just some photographs of how it looks. So this is the north side, as you see here. All the signals are coming out from. So all this designing was done at CDM, a very beautiful design in which all the high voltage cables have been routed through these containers down and then brought to the high voltage crates. And all the signal cables are coming out from here on the other side. And these are the crossbars, which I was told by the RSD to ensure safety and stability during any seismic activity.
5 minutes, please.
Yeah, sure. Yeah. And this is the south side of that, the same setup. And this is how the work was being carried out. Now, here are the calculations for sterile neutrino. And these calculations again give us confidence. On the x-axis, we have sine squared theta. 1/4 basically shows the oscillation of the fourth flavor into the fourth flavor, which is the sterile part. And on the y-axis, you have the delta m square 4/1. So if at all there is the fourth flavor, which is the sterile part existing, why it is called sterile? Because when the radiation was not known in the earlier days, it was just called X-rays. So that's why the word has been given sterile neutrinos. They are neutrinos and sterile because they don't interact. So these curves very nicely tell us at Apsara U, Dhruva, and PFBR at different distances with the Smaran detector, the calculations and the simulations give us confidence that yes, we can detect the sterile neutrinos. So from there, I move into a different part now. And since Bhabha Day, last Bhabha Day, we had commissioned the Smaran at Dhruva. So data taking is going on. And meanwhile, we have moved to another experiment, again by the foresight of Dr. Mohanty, that tried to set up a coherent elastic neutrino nucleus scattering experiment in Apsara U. So here what happened, this is not the inverse beta decay. Here the neutrino comes and just gives the kick to the nucleus. And then the phonons are generated, and we have to detect those phonons. Now, this is a very challenging experiment as compared to Smaran, because for detecting those phonons, we have to use dilution refrigerator, which goes to a millikelvin order. So these type of technologies now we are going to implement, and there are challenges. So we will have some collaboration with NICER, Bhubaneswar, and this is going to work in a collaborative mode. The importance of coherent scattering over inverse beta decay is that the cross sections are 2 orders of magnitude higher. And these experiments are very important to understand because they become the background for the dark matter searches. If this can be detected, then certainly we can peep into the direction for searching the dark matter. As all of us know, 67% of the matter is called dark matter and dark energy, which totally adds up to about 95%. So this is a beginning in that direction. And then, of course, if we have accelerator-based experiment, as yesterday Dr. Krishna Gopal was mentioning about the high-intensity accelerators at Vstaa, then these experiments can be done. This is something which was proposed 40 years before with the SNS source at ORNL. And with the accelerator-based, you can nicely see here on the top what you see is the energy part. That is basically the photoelectrons. On the bottom part, you see the arrival of them in microseconds. Here is the beam off condition, and this is the beam on condition. You are able to decipher all the 3 flavors of the neutrinos with an accelerator-based experiment. Reactors do produce a QPS source of neutrinos, but then the sizes of the reactors are also huge. In case of accelerator-based with high-intensity accelerators, you can really pin down the problem very soon in a couple of months. So in this experiment, as you see here, cesium iodide was used 14.6 kilogram, and we are moving in the same direction if we can develop certain things like this in the country itself. So here we have the resources at Technical Physics Division. And as you see, these are the various type of furnaces, Zekrolsky crystal puller, and various crystals which have grown, and we are aiming in that direction. And all these parameters are there which do require a vacuum. Vacuum is important here also. And as you see, so it is a very low order vacuum, but a high order vacuum, just in -5. So, but still this is required for developing these technologies and these type of crystals, which we'll be developing. This is another technique of the Bridgman type, where we are developing the scintillators. And here also the vacuum plays a very important role. And just to say in a nutshell now, this is my last slide. The India-based coherent neutrino scattering experiment at Apsara-U, which has been given a name icon C, which will be a completely Atmanirbhar Bharat initiative in terms of detectors and digitizers. Digitizers are being developed in electronics division. Detectors, as I showed you, will be developed in-house with some collaboration with NICER group also. We are also aiming at the dilution refrigerators. If all those things can be made, then it will be a really successful program in the next 3 years. The preliminary work of background measurement has already started in Apsara-U. And so this is the BRC neutrino team. Here we have the NPD and here we have the TPD. And we hope that we'll be able to achieve this in next 3 to 4 years. And I really thank you all for your neutronic patience. Thank you.
Pant, for a wonderful overall view of Indian ISM RAN work here. Now the talk is open for any questions. Before we go to that, sir, I have one question.
Sure.
If we consider Earth itself as a overall detector, the entire mass of the Earth, what would be the cross section for detecting these neutrinos? I mean, what will be in terms of scale?
If you have the entire Earth as a detector,
yeah,
then it again depends on the interaction because these neutrinos anyway purging your Earth also. As I said, from the solar neutrinos which are coming, they are also passing through the Earth actually. And people are talking of doing a tomography for the Earth using those neutrinos. Interaction cross sections are small and making a detector. So at the most, we have detector as of now existing in the globe, like super Cami of 50 kiloton, and that is buried about a kilometer deep. So those are the challenges of really working.
One other question is, typically, what are the confidence levels of this results that you have displayed here, like 2 sigma, 3 sigma?
Well, they are all within 3 sigma level.
3 sigma.
Yeah.
Okay, thank you. Any other questions in the audience? Yeah, there.
Sir, what is the difference between cosmic rays and neutrinos?
Sorry, I didn't get the question.
Cosmic rays and neutrinos.
Difference between cosmic rays and neutrinos.
Difference between cosmic rays and neutrinos.
Yes.
See, cosmic rays consist of everything which is coming from the cosmic. For example, you have the protons, you have the electrons, and then in a strong interaction, you have the pions produced. And then what happens, these pions decay into various other forms. The end result of most of them are neutrinos. Even the muon which is produced in the top of the atmosphere of our Earth, that also decays into neutrinos. So it's all in this cosmic thing, everything comes. But if you consider the other particles, other than the neutrinos, they do interact. They do decay. But the neutrinos, they just, the interaction cross sections are so low, so they don't decay. And still the whole physics is not known. In the standard model, as I said, it was told that they are massless. But it has been observed that, no, they have a definite mass. Having a definite mass opens up a new window now to look for the unresolved queries. For example, dark matter is one of them. There are several things which have opened up now. That probably because of them having a certain mass, which is a very low mass. Recently, just last week at CERN, they have come with a 0.8 electron volt mass for the neutrinos. So it is just, that news is coming up. Maybe by next week, it will be a big news. So 0.8 electron volt mass has been given to the neutrinos. So because they have a mass, so the physics will change now.
Thank you very much, sir.
Sir, I just want to know that these instruments that we are making for detection, how we calibrate them.
Okay. So I can go back to the slides. We are using plastic detectors. So that's a very good question because, that's what is the difference between a physicist and an engineer? I'll tell you. Because we made this all this design and said, fine, we'll do it. Then half the way we realized how we will calibrate them. So now we very coolly went to the CDM and said, no, we want something on that. They said, what are you people doing? You just come then, but so great are those people. They said, okay, we'll do that also. So as you see from the top, there are slots through which we will embed the radioactive sources. They will go to each and every detector. Now this was designed halfway. So we wanted to have at least 100 detectors making 1 ton, and this is the reason we had to reduce it to 9 of these rows, 90 detectors, because 1 centimeter of space was given to insert the radioactive source. So that is in situ calibration that we will be doing once in 3 months or like that. We will use the cobalt, we will use the cesium like that. And that was very important because once you close this, and it is already closed now, you don't have any excess inside.
Thank you very much, sir. If there are no more questions, as a token of appreciation from the organizers of Vstaa 2022, we would like to present you with a small memento. So, thank you very much, sir. We move to the second talk of the day, of the session. This is by Dr. Abhay Deshpande on the title Linear Accelerator for Isotope Generation and Other Applications. Dr. Abhay Deshpande is working as scientist at Medical Electronics Division at Samir, Mumbai for the past 2 decades. His area of research is design and development of linear accelerator for medical applications. He has done MSc in physics with nuclear physics as specialization from Mumbai University. He has done PhD from KEK, Japan in physics and has worked on RF photo injector for multi-bunch beams. He has played a key role in the design and development of 6 and 15 MeV LINAC for radiotherapy in India. He has designed and developed RF gun for KEK, Japan, IUAC, and other institutions. Currently, he is involved in design of high energy, high current linear accelerators for generation of medical isotopes. He is actively pursuing Indo-Japan collaboration for multi-ion therapy R&D in India. Dr. Abhay Deshpande, please.
Thanks a lot. I hope I am audible.
Yeah.
Okay. So can you see my presentation?
Yes, we all see. Yeah. Can you? Yeah, please go ahead. Yeah.
Okay, just 1 second. Let me have a pointer. Well, to begin with, let me thank the organizer, in particular Dr. Archana Sharma, Dr. Pat Singh, and Dr. Bhushan, who have invited me to this particular event. And I'm very glad to talk to you, although I'm online for all of you, but I'm really very happy to be in the community of vacuum specialists as well as electron and other Linux specialists. Well, today I'll be talking on the developmental work that we are doing at my lab in Powai. Samir is a Government of India organization. For those who don't know Samir, I'll quickly go through. We started as an offshoot of TIFR, and right now we are at 5 different locations, Mumbai as well as Kharghar. We have got an office at Chennai, Visakhapatnam, Kolkata, and also now recently Samir Guwahati has added, from where Dr. Tiwari will be having a talk in the subsequent sessions. So my group specializes in the development of electron LINAC, and we are working on multiple such prototype development. We have made this whole system, which I'll be showing later on. So our main focus is to develop, and we have been working only on this accelerator for quite a long time. The base design is our side coupled standing wave structure, which operates at pi/2 mode. Now this mode, as you all know, is a very special mode, because if you're operating a LINAC in standing wave structure at pi/2 mode, then every alternating cavity, alternating cell is an acceleration cell, whereas the alternating cell does not have this field balance over there, so no acceleration is assured. So these are the typical coupling cells, and based on the location of the coupling cell, we can have on-axis accelerator, which our friends and colleagues from ABPD have developed at EBC, which is on-axis like structure, or else the structure which we have developed is the off-axis structure in which we can move the cells sidewise. So we get a stability benefits of pi/2 mode, and the electron beam as such is the pi mode. So this is how the simulation, what you are seeing over here, is the simulated result. So these are the coupling cells which play no role in acceleration, and these are the accelerating cells. So my power will be coupled like this from sidewise, where the beam will be traveling along the axis. So the cell to cell phase shift is pi/2 between these two cells and pi/2 over here. So in principle, my beam will be seeing a pi mode successfully in each and every cell. So I get a benefit of a high shunt impedance due to this particular mechanism. Our operating frequency is 2998 megahertz, and in this particular structure we are having it's a 6.5 structure. We also have a variant of 5.5 structure and 4.5 structure, and we get a very reasonably flat field. We can make them as much as we want. The buncher is inbuilt over here. I can change the buncher field injected into buncher by varying the coupling in my buncher region. So these are the various components that we make. Everything that you see is made in-house at Samir. All machining is done by us. All characterization is done by us. Brazings and leak testing, everything is done in-house. We achieve reasonably high gradients in our structures. And this is the side coupled cell which is attached to the main cell. This is how the electron linac looks like. It's just a small 30 centimeter long structure. And we have done a rigorous study of this structure. We can get 6 MeV energy using this linac with RF input of around 2.6 megawatt peak power. The pulse width is around 4 to 4.5 microsecond, and we achieve a reasonably good peak currents for these smaller structures. So we get fairly good radiation output from these structures, but as you know, for medical application, we have to restrict. So we curtail down the average current as we wish, and thereby achieve around 500 rads per minute at 1 meter as our standard output. Now this linac sits in this particular structure over here vertically, and the beam radiations come out in this particular direction. The patient sleeps on this couch. The couch has got X, Y, and Z motion, and the gantry goes around in theta motion. So the doctors can position the patient in such a way that the cancer is in front of the ISO center for our structure. This is our ongoing therapy at one of the hospitals where such system we have already commissioned. What we have done is that we committed to government that will make multiple such system, at least 3, and make sure that the whole technology is established in hospital and also to the patient treatment. Fortunately, we have been successfully delivering the doses to patients for past few years. We are having a machine at Adyar, Chennai, at Indore, and at Amaravati Hospital, where the patient treatment is ongoing. We get a reasonably good symmetry as well as flatness. Now, once we had done this structure, we went on for the longer structure, and it needed some tweaking. This is the gun which we have made for our longer structure. It's a demountable type of gun, and we operate around 20 kV as the injection voltage. The electrons are emitted from the gun and they're injected in the accelerator. This is a target which sits at the far end. These are the cavities which I already showed. This is a window which is also made in-house at our facility. So this is the complete linac tube that we have made in Samir, and flange to flange length of this linac tube is 1.2 meter. This is the diode gun which I just now showed. The electrons are injected from this side. This is my buncher section. The RF window sits over here. The Klystron inputs power in this case from this particular port, and fields are established across the linac. The beam comes from the exit end. If I put a target, a tungsten pellet, I get X-rays. If I remove the target, if it's a removable target, I can also get electron beam as the exit energy. This is the Klystron modulator. Klystrons are imported in our case, and the modulator is made in-house. These are the parameters of our, these are the Klystron parameters, and these are the parameters of the line type modulator that we are making at some years. So this is used to energize the electron LINAC. And once the fields are established, the electrons get accelerated and we get a very stable beam. This is our FPGA based console, which I'll skip for the time being. These are the various parameters that we have achieved using our LINAC. For the longer structure, we are somewhere around 70 milliampere is the peak current required for us. So we are fairly getting this particular current. We can increase it up to 100 milliampere by changing some parameters. But once we make a LINAC and establish it, further change is not possible. So we have to choose what current we are going to do at the beginning stage, because this is a diode gun. So later on, I'll show you a triode gun which my colleagues have made, and now we will be able to control the currents as well. So this is also very, very stable electron LINAC. We have made multiple such LINACs, and all these LINACs are functioning very, very stably and smoothly. Just for the sake of completion, we also made a dual energy LINAC, dual mode LINAC, in which we can have both photons and electrons as output, as well as for photon, we can have 6 and 15 MeV from the same structure. And for electrons, we can have a range of 6, 9, 12, 15, and 18 MeV from the same structure. So this is a very unique developmental work that we are doing. This is that structure which you can see there is a small switch. We can use the switch to detune the remnant part of the LINAC, and only part will be used for the acceleration. Then it will be 6 MeV. If you remove the plug, then the whole LINAC is made available for acceleration, and we can achieve 15 MeV. So this LINAC is also under test, and it's working smoothly in the energy varying mode. Now, based on this background, I think this was essential, because now I would come to see what we are going to do and what we are doing at present. So few years back, we started planning to use the LINAC that we have made to come with a prototype which can help us generate 99 MOLE. And the reason being that 99 MOLE is by and large produced from the reactors. So, and it's produced in abundance. So what we are trying to do is that we are trying to come with an alternative accelerator-based mechanism to make sure that the production of 99 MOLE as well as other isotopes is also possible. So the reactor-based MOLE mechanism is known to everybody. This is how the reactor-based MOLE comes out. We can get a stable MOLE 99 from the reactors, and this is the way it goes through. You get a 99 MOLE. You have to process the into facility and then package it into these kind of generators, and this is ready for dispatch. So the hospitals get this as the end product, and from this they can elute the 99M technetium. So this is the currently most practiced production mechanism of MOLE 99. Almost everybody is using this as the mechanism. Now, if you want to discuss about the ways of producing the MOLE 99 using accelerators, actually there are various alternatives. One is of course the proton type of accelerators, or deuteron accelerators as well, or else what we are proposing is the electron accelerator. When it comes to the proton accelerators, most popular choice is of course of cyclotrons, and now VECC has already got a cyclotron, which is 30 MeV cyclotron, which can directly produce the technetium. The typical mechanism of producing the MOLE technetium from the cyclotron is as follows. You have a cyclotron, it uses a proton beam. Proton beam is bombarded on 100 MOLE, and via P2N reaction, you get directly 99 TC. Now, this is a very, very simple mechanism, and cyclotrons are available, but by and large, the cyclotrons required for this kind of reactions are around 30 MeV or so energy as of now. So the commercially available G-like cyclotron which we have at RMC parallel may not be useful directly to produce 99 MTC. They can produce all other variants, FDG, etc., but need not produce the 99 MTC. The advantage is you get the 99 MTC. The disadvantage is that 99 MTC has got a short half-life of around 6.6 hours. So then the production mechanism should be in the vicinity where the patients will be coming to use this particular 99 MTC. That is the drawback. Therefore, we proposed the LINAC mode, and in LINAC mode, we are proposing the 100 MOLE target mode. If you have sufficiently good X-rays coming and bombarding the 100 MOLE, then via gamma N reaction, you can get 99 MOLE. The half-life of 99 MOLE, as you know, is 66 hours, and therefore you will be able to get reasonably stable MOLE in this particular case. So this is what we have proposed. The LINAC which I showed initially during the first half of my talk, we are proposing to use 2 such LINACs and put them in a series, do a sequential acceleration around 15 to 18 MV we are getting per LINAC. So we will be able to achieve 30 to 36 MV energy at the exit of the LINAC. The current which I have shown is of the order of 70 milliampere is the peak current that we are achieving. So if I operate the LINAC at a higher duty cycle, I will be able to achieve the desired average current at the exit of LINAC number 2. Subsequently, if I bring those electrons right up to the target and hit the target, then E gamma reaction will happen and I'll get photons in the forward direction, of course, in all the directions. And if I put the 100 MOLE target in the path of my photons, then the reaction of 100 MOLE gamma N to 99 MOLE will be feasible. So subsequently, it doesn't end over there. From there, you have to elude the technetium, which is more or less a stable process. So we have no specialization of the isotope handling part and isotope processing part. So for which we are having a collaborator called as INMAS. And INMAS is a hospital. It's a DRDO lab and hospital in New Delhi. So they are the experts who produced various kinds of isotopes, and they have the hospital where the isotopes are immediately used. So this is an ideal setup for us. So we are having a collaboration. Our role is to generate the high energy accelerator, get the electrons over here, hit them on the converter, and from there the INMAS will take over for the production of the isotope. So these are the base parameter that we are targeting around. This is the energy 28 to 30 MeV is the energy that we are expecting with a sufficiently large current so that our beam power will be somewhere around 5 to 10 kilowatt as our average power. The peak power of the klystron remains almost same, but the duty cycle of the klystrons are sufficiently large in this particular case. This is how the total beamline will eventually look like. The magnet is just for the initial testing purpose. Eventually the magnet and this whole part will be removed and the LINAC will come closer to this target over here. This is the shielding cube for which I'll be showing the slide separately later. So once the beam comes to the location, we are having 2 retractable type targets. One is a tungsten target, one is a copper target, and we can retract remotely either of the targets. In fact, you can remove both the targets and get the electrons directly coming outside. So we have provision of a copper converter, we have provision of a tungsten converter, and our colleagues are working on the direct MOLE as the third converter target, which will come and sit over here. So in any case, I need to have a mechanism to push in the MOLE target and retract the MOLE target from the particular location. So these targets are fixed targets. We can move them, but we cannot remove them. But the MOLE target, which comes as the secondary target, has to be removed from the location. This is just a photograph of the graded gun which my colleague has made. We have successfully tested and also commissioned the triode gun. Now we can control the current as fine as we wish to control. As you know, the heat is one of the major issue for the high duty cycle LINACs, and we have done a huge amount of time has been invested into understanding the dynamics of the heat load and how we are going to remove the heat in a continuous process. So we have geared down and finalized our thermal mechanism, and we have done a test setup and test experiment, and we are able to remove all the heat that is being dissipated because of the high average operation. Of course, once we put the LINAC tubes and start doing the operation, the situation changes dramatically. So we'll also go through the process and understand how the entire mechanism should be handled. The shielding is one of the major component in this case, and we are thankful to our colleagues and collaborators from BRC who have helped us in designing the shielding mechanism. And this shielding block contains multiple things. This is the lead for the photon shielding, followed by HDP, borated HDP, followed by 40% boron rubber as our final shield. So this will take care of the neutrons which are generated, and this will take care of the photons which are generated. This entire mechanism will be hosted into our radiation facility, and then we'll be able to operate it. Now the question remains, how am I going to push in the moly target, which after say one shift of irradiation, I have to remove it. So either I have to go make holes and put a continuously moving mechanism. What we have done is that as follow, we have made a mechanism in which some part of the shield will move when we require it to move, and then we'll be able to insert the target using a robotic mechanism and close the block once again, do the irradiation, and then remotely open the shield and direct at the target. So this is how the assembly will eventually look like. This is the shield which I showed, and we can open it remotely, and it will open up a cavity over here, and a robotic arm will place the moly target in the location. The arm will go off, the shields will close, and we can do an irradiation. That is what we are right now working upon, and this will help us to place the target as and when we wish to place it. So from the status point of view, we are most of the assemblies are in state of assembly. We are doing integrations of many of the components. The LINAC tubes are in a ready state. The target sub-assemblies are ready. The gun is already in place. What we don't have right now is the RF source, which is awaited for quite some time. There was a huge delay in getting the RF system, and we are confident that by this June or July we'll get the RF system. All other subsystems are in place, so once we get the source, we'll be able to integrate the things and then start doing the RF outgassing. Now, once we start doing the RF outgassing, it's a long process, as you know, as accelerator phases. It will take very long time for RF outgassing if you want to achieve a very good vacuum. By and large, we do a baking of all our system, and on a baking oven, it's a double jacket baking oven. We achieve 10⁻⁹ torr as the vacuum at which we do the pinch off. So -8 is the by and large the vacuum which we easily achieve at our end, and we operate our accelerators at that particular vacuum. So it's a fairly good vacuum. And when we start doing the RF outgassing, we do it for 150 to 2 hours to make sure that further degradation does not happen. Then our beam comes on. We have done the electron beam measurements at our end, and we get a beam diameter of around 2.4 to 2.5 millimeter as our beam at the exit of the LINAC. So it's a very small beam, very well focused beam. We don't need any external focusing as of now in our system. Now, once put 2 LINACs in series, which we are going to do it for the first time, we'll come to know what challenges we are going to face. That is the one main challenge. The second challenge is, of course, we have to learn handling the accelerators at such a high average power. That will be our second challenge. And after that, we'll be in a better position to understand how the beams are handled at that particular average power. So in a nutshell, this is where we are. We have to do preliminary beam demonstration at some point of time, then shift the entire system to in mass.
Dr. Deshpande, 5 minutes.
Yeah, I'll be concluding. It is just one more slide, so I'm concluding in time. And then shift the system to in mass, and then do the entire characterization of the system in the in mass radiation facility. That was my alarm, so I'm in time. And these are some results which other groups have obtained. They are able to produce technetium moly-99 using the LINAC at these energies and at these beam powers. In our case, the energy will be 30 MeV, and the beam power will be around 5 to 10 kilowatts. So we are fairly sure that we'll be able to achieve the radiation at some point of time. So just to conclude, we have successfully demonstrated 6 and 15 MeV LINAC technology. We are making them quite regularly, and our systems are well robust. They're used all across the country. Based on our expertise, we started working on the slightly higher energy and slightly higher average power accelerating system. That is to broaden our scope of work, and these accelerators will be used for isotope generations. That's number one. And there are some more other applications also which we are trying to work out so that the LINAC will be there, so we'll be able to get electrons and we'll be able to use the electron also for some various applications. These are opening up new avenues for us, and especially the neutron therapy for tumor is one of the system which will be eventually looking closely for. Once we get a hang of handling this kind of systems, we will be very keen on having neutron therapy for the tumors. I would like to conclude by thanking many of my colleagues and friends, many of who you might be sitting in the audience. Dr. Rajan is one of our guide for many of the isotope related activities. Dr. Anil Kumar Mishra, who is our PI from INMAS, he is now Director INMAS. Dr. Biju has helped us for the shielding and related guidance. Many of my friends and experts from BRC, BRIT, RMC have came up with discussion. No, isotope is an absolutely new field for us. So we relied on them for almost most of the discussions. And finally, team members and my colleagues from Samir who have been putting hard work in this tough time for last 3 years to make sure that the project stays on. And with that, I would like to thank one and everybody for listening to me thankfully. Thanks a lot.
Thank you. Thank you, Dr. Deshpande, for that wonderful enlightening talk on development of 6 MeV, 15 MeV accelerators in India. Before I throw the session to audience, I have 2 questions. Could you just enlighten us about how many of your indigenously made accelerators are working in medical purposes? And second question is, today is the day where, people are looking at what is called as targeted cancer therapy. So in terms of targeted cancer therapy, how would your accelerators be used or utilized in this purpose? Could you just enlighten us on these 2 things?
See, at present, sir, we are having 3 units which are functional at hospitals, which I showed earlier, and where we are of course delivering the photon as the mode of delivery. So we are having photon therapy. We are now working on the integration of multi-leaf collimator with our system, and the portal imaging will also come to our system. And with the multi-leaf and portal imaging as a part of our system down around 1.5 years, our system will be useful from the other aspect that you have mentioned. More importantly, what we have been seeing is that doctors are more keen on going to not for 6 MeV alone, but 6 and 15 together. So if you look for a cancer profile, I would say 85% of the therapies will be used by using a 6 MeV accelerator.
My question was basically how would it compare with, for example, hadron accelerators where they have the Bragg peak, so they can specifically locate the tumor and kind of do targeted.
No, both technologies are totally different. Photon therapy has got its own pros and own cons. Hadron therapy is naturally it is much more focused therapy. So we have proposed ion therapy system. It's a multi-ion therapy system, but it's in discussion stage and eventually it will come up.
Thank you.
But we cannot compare both of them at simultaneously.
Yes, thanks. Yeah. Are there any questions in the audience? Yeah, there is one question. Yeah, please. You can switch on the mic.
So this current what we are using for this molybdenum or whatever irradiation purposes, so what is the limiting factor? Because more will be very like you can produce more. So what is the limiting factor in this case?
Yeah, we can go for higher peak currents. As I said, sir, we have a cushion of around, we can from 75 milliampere to 100 milliampere is the expected peak current that we will be able to achieve using our LINAC. The limitation comes from the fact that, if I increase the current sufficiently on the larger set, there's a huge beam loading which is going to happen. And then the klystron mechanism, I need to go for much higher klystron. So we thought that, it will be prudent for us to go ahead with what we are having easily achievable. Around 100 milliampere is the first stage that we'll be able to achieve. And then subsequently, we can try to enhance the current at the next stage. So to begin with, we are targeting 75 to 100 milliampere as a peak current and pushing the load onto the average power.
Yeah, I have one more question. So you showed some plunger arrangement where you can have multiple energies kind of tuning. So how does that mechanism work?
So you see that our LINAC is a long structure. I'll try to show it again. I'll just quickly. It's not sharing anyway. So it's a long LINAC structure. It is having in our case there's a side coupling cavity is there. So after 9 main cells, there's a side cavity. If I push a plunger inside the side cavity, the power does not couple through further. So the rest of my around 12 cells or 20 cells become only vacuum-like structure. So only first 9 cells are used, which are correlate to 6 MeV as our energy. Now, if I remove the plunger, the whole power is conducted in the entire accelerator. The advantage is you can use both the energy. You can get both the two energy from the same structure. Disadvantage is that once you put a plunger in structure, our VSWRs are matched as per the longer structure, and if I put a plunger in between, then I'm not seeing the other cells. So the VSWR matching has to be carefully done. But my colleagues, Dr. Tanuja and our team, have successfully managed the operation point using the plunger for smaller structure and removing the plunger for the longer structure. Both are successfully achieved.
Thank you. Thank you, Dr. Abhay Deshpande, for that wonderful talk and enlightening us with your indigenous developments on 6 and 15 MeV accelerators. On behalf of the organizers of Vstaa 2022, we are offering a plaque for the talk, and that is displayed on your screen right now, and the same will reach you by post or by courier or in due course. Yeah.
Thank you so much, sir.
Please accept it, and thank you. Thank you very much.
Thanks a lot.
We now move on to the next talk of the session. This talk is by Dr. Sanjay Choksi on the title Overview of Manufacturing Technologies for the Development of Ultra-High Vacuum Compatible Components at RRCAT. Dr. Sanjay Choksi graduated in mechanical engineering from Maulana Azad NIT, Bhopal in 1988 and joined 32nd batch of BRC training school. Dr. Choksi started his career at Fast Breeder Reactor, IG Car, Kalpakam as a design engineer. Later, he joined Accelerator Program, RRCAT Indore in 1995. He was involved in the installation and commissioning of Indus 1 and Indus 2 synchrotron radiation sources and remain associated with them for more than 15 years now. His field of specialization is design, development, manufacturing, and installation of normal conducting accelerating structures for particle accelerators, transport lines, and user facilities for IRFEL, material handling systems, accelerator components, and radiation shielding for particle accelerators, etc. He has represented India in multiple international forums and is a recipient of several awards from DAE, Government of India. He is member of multiple professional bodies and has more than 50 publications. Presently, he is head of planning and machining group responsible for the development of particle accelerator components of RRCAT. Today, he will speak on the overview of manufacturing technologies for the development of ultra-high vacuum compatible components at RRCAT. Over to you, Dr. Sanjay Choksi.
Thank you, Dr. Bhushan, for the nice introduction. I'm audible, na? Hello.
Yes, you are. Yeah.
And first, I would like to thank organizer VSTTA for giving me opportunity to deliver this invited talk, especially Dr. Archana Sharma and Dr. Bhagat Singh, who was interacting me for some time.
Please share your slides. Yeah.
The screen is visible, na?
Yes, sir. Yes, sir. Please go ahead.
Okay. This is outline of my talk, and I will be covering the major facilities we have developed in RRCAT over the years for making particle accelerator component, especially ultra high vacuum components. And RRCAT laid foundation on February 19, 1984. So maybe in after 2 days, we'll be completing 38 years. And the laboratory work started from 1987. So we have a long experience of development of vacuum, high vacuum and ultra high vacuum components at RRCAT. And on 17th of December 2005, RRCAT was named as Raja Ramanna Center for Advanced Technology. We have two programs in RRCAT. One is accelerator program and laser program. They are the two major activities. We have two synchrotron radiations of our country, Indus 1 and Indus 2, and electron accelerators for material and food processing. And then we have terahertz and IRFEL activities. And other than that, we have is Indian Facility for Spallation Research and cryogenics and other development and superconducting RF technology, other application other than international collaborations. This is our Indus complex. We have injector microtron 20 MeV and Indus 1, which was commissioned in 99, and Indus 2 storage ring, which was commissioned in 2005. And since then, both the machines are operational round the clock for almost 26 days in a month. Other than that, IRFEL and ARPF, two major projects. And IRFEL, the work we have commissioned is we got the permission from ARB for operation of IRFEL project. Terahertz, we got the beam in terahertz. Now it is shifting to the new location. And two 10 MeV 5 kilowatt electron accelerator LINAC 1 and LINAC 2 have been indigenously developed for agriculture, medical, industrial radiation. We have large laser program also, and with high power laser for industrial and material processing and biomedical societal applications of lasers. The interest here actually as a high vacuum application, these laser, especially for terawatt or petawatt laser, have large chambers where we need to maintain some vacuum level. So I will be covering that. We have already developed such large chambers in RRCAT. So the long journey of making UHV compatible components, generally because vacuum is a very important part of any accelerator operation, and which has to run round the clock. And for Indus 1, Indus 2, it is almost 250 to 300 meter vacuum system, which has to be maintained a vacuum level, higher ultra high vacuum level. So we follow some guidelines actually for designing and then implementation of the system. And we have guidelines for welding, machining, selection of materials, and then while designing the systems, looking at trap hole, then sealing actually, which is very important for ultra high vacuum. And then when it comes to the manufacturing level, there are guidelines which has to be followed, then cutting fluid, and then surface finish, many things. So like we have a CDM in BRC for manufacturing facility, but there actually the mandate is making reactor components and vacuum component also, of course. But RRCAT, most of the component, if we see 90% of the component, they are ultra high vacuum compatible. So the whole culture in our facilities is slightly different. We have to follow the guidelines to maintain vacuum at all level during operations. So these are the guidelines we follow actually, from machining, material joining, and brazing, everything. The mandate of our manufacturing facilities at RRCAT is limited to particle accelerator, laser and related equipment machines. And we are not for very large mass manufacturing of the component, because each component have its own design complicacy as far as design and machining. So we develop technology and then we interact with industries where we give this industry, like we make lot of flanges, and later when ultra high vacuum flanges are required or sealings are required, we develop industries with our collaboration and our experience. So RRCAT manufacturing facility for high vacuum and ultra high vacuum has design manufacturing technology division, and we have laser component design and fabrication, and then few divisional machining facilities also. But if you see the size, almost 80% components are being developed by our division. So when we start the development of ultra high vacuum components for RRCAT, we take design for vacuum consideration, then inventory of the material which are UHV compatible, and then we have semi and precision machining facilities at RRCAT, which I will be covering. And then we have large chemical cleaning facilities, material joining and quality assurance. So first, when the design of these components, it is basically, as I earlier covered, that it is based on the UHV considerations, and of course RF and microwave, because all these components, they have two major consideration. One is high electrical field on the surfaces because of high power on the RF power, and other than that it is the vacuum considerations. So components are mainly designed by ultra high vacuum group of RRCAT, where Mr. DP Yadav will be covering major things tomorrow in his talk. And then the machining, joining, chemical cleaning, all these factor has to be taken care. So when we see the construction material for ultra high vacuum, the important is vacuum and RF, and then vacuum boundaries. And few components like bending magnet chambers and other chambers, they have large magnetic field also. So all these things combinedly decide how a chamber or a vacuum system has to be designed. So when we select the material, most generally in UHV compatible material for accelerator laser, the choice is austenitic stainless steel SS3 300 series, and then we have aluminum and aluminum alloys. So if you see, compared to Indus 1, Indus 2, most of the components are from aluminum and aluminum alloys, and we have OFE copper, which the selection criteria is more from RF point of view, and Glitco copper and niobium is the material choice for superconducting RF Linux. So we have large inventory in RRCAT, where we properly keep this material inventory after a proper quality assurance. So machining of UHV component, if we see, the correct machine selection of correct machining tool is very important. And the preferred technique for finishing in machining is generally turning and milling. And then form and surface finish of the final structures are critical for seal and sealing surfaces. And geometric tolerances are very critical on edge preparation for weld joints or brace joints. And brazing and bonding, all type of joining, two things are very important. One is the gap, joint gap or tolerances on that, or finish. And for weld ports, surface finish of the main body, weld upstream at the seam, and all critical features are very important for the final result. So I will just give a little glimpse because the spectrum of the audience is generous. So we have turning, milling, boring, drilling, reaming, tapping, electro discharge machining, grinding, all the facilities. And cutting tool selection, right from diamond, which is the hardest material, if you see on brilliant hardness is around 8,000, to high speed steel, which is generally used. There is a large variation, and selection of these type of high speed or carbide to or polycrystalline diamond or single diamond, depending upon the type of application and type of tooling we are using. So I start with the precision turning. We have a very good amount of turning facilities at RRCAT, where we make knife edge flange or all ultra high vacuum or high vacuum requirement of flanges on turning, because turning is a single point cutting process, and so this is generally good for axis symmetrical type of parts. And for making helicoflex seal grooves as per the requirement of the manufacturers of these seals, all these grooves are machined, designed, and then machined as per the requirement for the long term operations. And another thing is conflict flange, as you know. So for conflict flange, since the requirement is very large in number, we have developed process, and then we have developed tooling, a special type of form tools we have developed for making the conflict flange as per the requirement. And our rejection in this is almost nil, because almost more than 32, 33 years our production system has developed this sealing system so nicely, and our technicians are very expert in making that our success in making these type of flanges are very, very high. Then we have developed diamond seal for Indus 2, which is of aluminum alloy 6063 T5, and this has been successfully used for sealing of another copper-based aluminum alloy 22169 flanges in between, and this diamond seal is being used from Indus 2 since 2004-2005. So we have almost 50 turning facilities in RRCAT, and which cover all type of CNC, high precision CNC machines to conventional machines. This is the big, large hollow spindle machine where we can machine up to 700 diameter turning radius, and this hollow spindle is mainly used for machining of niobium cavity cells, and we have successfully developed many RF cavities, superconducting RF cavities in this machine, 650 megahertz or 1.3 gigahertz. Then we have another spinner machine, which is best machine available in our center, which has a runout of less than 1 micron. And this machine we have imported from Switzerland, very good machine. And generally for high gradient structures, we use this spinner UP65 machine. And we have recently added this large VTL machine for making Indus 2 RF cavities. So 500 megahertz RF cavity we have machined using this machine, which has some very special features. Then we have other old machines also. These are all CNC machines in RRCAT for different application, and these are all CNC operated machines. I have not listed conventional machines because they are available elsewhere also. And then if we see our milling facilities, this is a multi-point cutting operation where we have prismatic shape to be machined. Here also, these type of surfaces where vacuum is required is machined accurately. And we have one good machine available with us is we have 26 number of milling machine, and this is a DMG Mori Germany make machine, 5-axis simultaneous 5-axis machine. So this machine was actually purchased for making RF quarter pole, and which is very, very high accuracy machine. We are regularly making RFQ vanes out of that, and you can make any complex profile because I think spindle in this machine moves simultaneously in 5 axes. And then we have high precision jig boring machine with us. There are other milling machine centers, machining centers available with us, 3 axis or 4 axis. And this is also a very heavy duty BFW make machines where we may make large chambers up to 1.5, 1.6 meter without any problem. And these are all 3-axis machines. We have grinding facility, although for UHV application, grinding is not that much recommended. But for making form tools or the cutting tools, special cutting tools for making those profiles of vacuum, we use this tool, and we have total 6 number of grinding machine. I have just shown the surface grinder, but we have special tool grinding machines. We have electro discharge machining, almost 12 number in RRCAT. And recently we have added this submersible type of machine in our center. We have die sinking machine. We have electrical discharge drilling type of machine where we can make 0.3 to 3 millimeter electrode diameter drill in that. We have large number of drilling machines, almost 20 in the center, from radial to bench drilling machines. And this is for making holes BCD on the flanges and all. And we have now 3 drill tap centers, CNC type. So you don't manually drill the hole and tap the hole for UHV flanges. It can be done by the CNC machines. And for pre-cutting of these machines, we have a water jet cutting machine, air plasma. They are all CNC operated machines available with us. And there are many other machining facility which we have not covered because they are generally as a metal cutting process. And now I will move to the chemical cleaning available with us. Actually, chemical cleaning is the foundation in achieving UHV and required vacuum system performance. And the cleanliness start with the vacuum component, material selection, and fabrication. So we have all type of cleaning facilities for vacuum chamber components, RF component, everything, copper, SS. And RRCAT already has a very large experience of chemical cleaning. And other than chemical cleaning, we have means like ultrasonic vapor degreasing. We have copper plating facilities. So for vacuum brazing, we need special type of plating to increase the adhesion actually, because the brazing performance sometime we need to do a plating. So we have copper plating, degreasing, and chemical cleaning setup. And of course, electro polishing is a requirement of many components before it is being used finally. So we have large electro polish setup for Indus 2 front end, which you can see in photograph right side. And our chemical lab is set up with all analytical chemistry lab, instrument for analysis, wet analysis, and this thing. And we have instrument for electrode deposition, coating, and characterization studies. Recently, we have set up a big effluent treatment facilities for this chemical plant. These are the photographs you can see for Indus, and then RF coupler for CERN, and then we have DTL coating. So these are the plating facilities, some of the good, excellent result what our chemical lab has achieved. And we are collaborating with other laboratories also for that. These are some of the photographs shown for electropolished components. And we have now set up a electroformed facility also. So right left you can see a beam dump of proton accelerator, proposed proton accelerators at RRCAT. So we are developing electroformed bellows and copper this thing. And these are, yeah,
5 minutes, yeah.
Fine. Okay, so these are some of the good results for chemical cleaning. And you can see the results of electropolishing. And then RRCAT has mastered very good material joining facility. We have inert gas welding, TIG, MIG, brazing, EB welding, laser welding also. And you can see these are the correct process for TIG welding, GTAW. And then we have 8 number of very good welding machines available with us. And RRCAT is expertise in manufacturing of these ultra high vacuum chambers. And success of the large vacuum systems for Indus 2 is a result actually, which detail will be covered by Mr. DP Yadav tomorrow. And we have experience of UHV component for machining and then welding and then achieving the performance for almost 30 years. You can see Indus 1, Indus 2 cavity in this photograph, and large dipole chamber, then CERN coupler. All these things are some of the major component we have manufactured at RRCAT. These are the some beam diagnostic divide for Indus 2 developed. And then this is ion extraction chamber. This is the dipole chamber of Indus 2. There are some state chamber. Brazing, we have excellent facilities. We have two ultra clean control brazing furnaces, and in future we have to buy going for a horizontal brazing furnace also. These are all either like two brazing furnaces, and then we have ultra clean vacuum degassing furnaces and oven also. So these are the some of the results I have shown for brazing. The step we have involved in making these components, successful brazing component, SS to copper or copper to copper. And then this is the vacuum brazing of RR coupler and neck for ARPF project at RRCAT. We have hydrogen furnace glass blowing facilities also in RRCAT. And then you can see that glass to metal seal and then vacuum result you can is shown here. We have made glass metal seal cavity for magnetic operating. This is mainly for the laser component. And then we have demountable hollow cathode lamp, and we have a 15 kilowatt electron beam facility also for mainly for niobium welding. And we have a quality control facility which is equipped with the three column type of CMM coordinating measurement machine, and then two portable type of CMMs. And then we have all type of height gauge, and then this we have roundness measure system, and then we have surface texture form measurement machine, flatness. All these quality assurance required to finally qualify our machining and material joining. We have all type of setup available at RRCAT. We use coolant recommended for UHV machining without sulfur and chloride, zinc, phosphor. And then we used ethanol for cutting fruit for niobium machining. And then handling, we take care during machining as per the requirement of UHV. So this is one of the important achievement actually, the UHV requirement superconducting RF cavity if we see for niobium, titanium and its alloy electron beam welding. And the requirement of this superconducting RF, we have large number of joints in EB welding this thing. And you can see in this photograph, and it has to comply with the ASME pressure vessel code. So this is as per ASME section 9, the type of weld joint category and joint efficiency. This has been developed in RRCAT and successful UHV joints of SCRF cavity results. So these are some of the large vacuum chambers we have fabricated in-house for terawatt laser. Although vacuum requirement here is less, but machining and then assembly and then maintaining this vacuum level is actually challenge, because which we have done first time. There is not a metal seal here, but in that case, because of the size and the requirement of this thing final assembly, we found that making this vacuum chamber is this thing. But for petawatt, we are now developing few industry for making these type of interaction chambers. And future RRCAT will like to have because we have read that there are additive manufacturing for making UHV components, and RRCAT has already developed laser additive manufacturing facilities in this thing. And we are also looking to work on the magnetic pulse welding for UHV joint, and we are going to have one measuring machine for non-contact measurement. It will be useful for the quick measure of conflict flanges, knife edge flanges, and upgradation of the manufacturing facilities for proposed HBSRS 6GV machine at RRCAT or Indian Spallation Neutron Sources and Laser Project. And in my conclusion and remark that to cater the need of manufacturing of components for R&D program of RRCAT, advanced and versatile manufacturing was established, which is outfitted with the precision machining, material joining, assembly, and inspection facilities. Team of engineers and technicians at RRCAT has gained more than 30 years of experience in manufacturing and handling component of high and ultra high vacuum applications. And I acknowledge all the team and colleagues in RRCAT who has been contributed for my talk. Thanks.
Thank you. Thank you, Dr. Choksi. That was a wonderful overview of the entire manufacturing facilities available at RRCAT. It is wonderful to know that you have such fantastic facilities available. I have just one question before we proceed to the audience. In most of the cases, we now use aluminum as one of the most important materials in ultra high vacuum systems.
Yeah.
Now, welding aluminum and aluminum to SS or aluminum to copper is still a tricky thing.
Yeah.
So what is your experience in RRCAT, and what is the kind of leak rates that you have achieved in this dissimilar metal welding processes?
Actually, as far as aluminum to SS, we have tried different friction welding. Like Indus 2, if you, Mr. Yadav will cover tomorrow. The transition joint in aluminum to SS is presently only friction welded joint, which has developed with the industry. So there actually we have excellent result in this thing. But as far as brazing route is concerned, still aluminum brazing is under process. We are presently working on the SS to titanium and other joints which is required for bark actually, and that brazing material joining work is in process in our division.
Okay, yeah, thank you. Any questions in the audience, please? Any questions? We are already running.
Yes. So we are looking for somebody who can, after seeing this facility, can collaborate with RRCAT, especially all the excellent material joining facility and machining facility we have in house.
Yes.
Thank you, Doctor.
One question is there. One question.
Yeah.
Yeah, you were just telling about this friction stir welding, no?
Yeah.
So in that, at the end of the welding, there will be cut, I guess. And why not you try the magnetic welding?
Magnetic welding actually because I was interacting with Madam Archana Sharma, because I know that APPD has already developed this process. Sometime actually there is some limitation comes with the geometry, because many of our joint we found that making coils and this thing was not, but in my future work actually we would like to interact for magnetic pulse welding. And I have already visited BRC, that south side facility which BRC had developed, and we will definitely come out with the this thing for future accelerator wherever possible we will use, because this is a old process of material joining, and it is excellent actually, as because there is not much metallurgical change. So wherever possible with the joint configuration, we will definitely try this welding process actually, cold welding.
Thank you.
I've already
Thank you,
visited BRC for this.
Thank you very much. On behalf of the organizers of VSTA 2022, we would like to present you with a silver plaque, which is displayed on your screen right now, and this will reach you by post in due course. Kindly request you to accept it.
Thank you,
very
Dr.
much.
Bhushan. Thank you, Dr. Bhushan, an organizer. Thank you.
We proceed with the next talk of the session. This is a oral contributory presentation. This is by Shri P.C. Saroj on the title Development of Electron Beam Accelerators in EBC. Mr. P.C. Saroj is working as Project Manager EBC BTDG BRC where he is involved in development and utilization of electron beam facilities and electron beam center Kargar. He has contributed to the design and development of various multi-gigawatt compact nanosecond pulse power systems for strategic industrial and nuclear applications. He has contributed in the drafting and review of IAEA TEC doc on dissimilar metal weld inspection, monitoring and repair approaches at IAEA headquarters, Vienna, Austria. He has played a key role in transferring various technologies through TTC-BRC to private industries. He is recipient of 4 DAE Group Achievement Awards and a DAE Scientific and Technical Excellence Awards for the year and has authored more than 54 papers in national and international journals and conferences. Today, he will be presenting a talk on development of electron beam accelerators in EBC. Over to you, Shri Saroj.
Hello. Hello.
We request you to stick to time, 10 plus 2. Yeah, thank you.
Yeah, thank you, Dr. Bhushan. I thanks to Vstaa 2022 organizing committee for giving me this opportunity to present the electron beam center activity. It's a BEM technology activity, I can say, because APPD and EBC both, we are working together to bring the things. Just I will be giving the glimpse of this activity briefly. ये है ना नहीं जा रही अभी जाएगा बैक ठीक है तो my outline of the presentation is a electron accelerator block diagrams. I will be giving the glimpse of DC and RF both. And then subsystems we have developed at Electron Beam Center Kargar for both the accelerators. Then the accelerator simulator operating training related and a dual energy Indian cargo scanners and X-band Linux. This is just now is placed at EBC Kargar by APPD. And the DC accelerator and wastewater flue gas treatments carried out on DC accelerator located at EBC Kargar, and technology transferred so far, and future scopes, facility footprints, and collaboration responsibilities. So basically this RF and DC accelerator, as you can see the schematics. So in both cases, electron gun is there. And here high voltage generation part is different. Cockcroft Walton multiplier or parallel coupled multiplier is used for the high voltage generation. So we have the power supply and then inverter, and then after inverter we are feeding to high voltage transformer. This step up the voltage and connected to the multiplier column to multiply the voltage to the millions of volt, depending upon our accelerator design. So presently we have this capability of 1 to 3 million volts, and beam is accelerated from top through the accelerating columns and beam line, and it is brought to the outside atmosphere through the scan horn and titanium window. In between magnetic focusing, vacuum systems, and focusing coils, all the things are there in the beam line itself. So coming to the RF accelerators, here electron gun is there, then Linux cavity is there, and RF source is there. And again vacuum system, rotary pumps, and Faraday cups are there. And beam is again accelerated through the RF field, and this Claston modulator, Claston is driven by the Claston modulator, and gun is driven by the gun modulators. So again, here RF beam is brought through to the atmosphere through the scan horn and titanium window. So for RF clinic, major subsystems are the electron guns, which I have shown. It is located at top of this accelerator structure. And second is the RF cavity, that is the LINAC cavity. Here the test setup, and we have the test facility to carry out the cavity characterization. And this is the pulse modulator. This is for klystron and electron gun. There is a different modulators. This is for the klystron modulators. And this is the FCT used for measuring the pulse beam current. Recently, we are working with this CNID and EBCM together for solid state modulator. They have developed the CNID has developed the solid state modulators, and we are having this klystron and test setup facility where it is assembled, both the klystron modulator and this klystron assembled at the EBC Kharghars, and it has already tested in the diode mode to 135 kV, 88 amperes, 12 hertz, 7 microseconds. Our next plan is to test to the 116 kilovolts and high rip rates. Yeah. So this is the subsystems of DC accelerators. Just now, before that, I have spoken about this RF accelerator subsystems. So here we have got, as I have already explained, we have got, we are using the high power inverters, DC power supply, high power inverters, then high voltage transformer. These are feeding to this Cockcroft-Walton multiplier. This is the structure. This is the structure of the Cockcroft-Walton multiplier. This one. And these are the capacitor modules which are placed inside the high voltage multipliers. And this is the rectifier stacks. And when there is a breakdown, in order to protect the rectifier components, there is a surge limiting inductors. And this is the scan horn and wastewater feeder systems. So in-house, we have developed so far 500 kV. This is our recent accelerator at BRIT Vasi complex. Then we have also developed 3 MeV 30 kilowatt accelerators. And presently, we are working on the 1 MeV 100 kilowatt accelerator for wastewater treatments. And this is this already flue gas treatment. 3 MeV was utilized for the flue gas treatment. In case of the RF accelerators, this is a 6, I think, okay, 6 MeV radiography cargo scanner, single energy. And this is the 9 MeV LINAC used for this neutron radiography at ECL Hyderabad. And 6 by 4 MeV after successful commissioning at EBC Kharghar. As per IC and NC, we have shifted to gamma field for integration. It is already, it has qualified all the tests at gamma field. And this is the recent application we are developing, compact RF LINAC accelerator in a horizontal configuration for this 24/7 operations. And this is the present accelerator, 10 MeV 3 kilowatt. This is presently used for irradiation of the various R&D, agriculture, and industrial applications. And it is presently working. And so far, we have operated more than 600 hours for 600 hours of operation. So if I can go to chronological development of the electron accelerators, we can see 500 kb was the first accelerator, which was in 1998, was inaugurated by Honorable Prime Minister Atal Bihari Vajpayee. Then second was 10 MeV RF LINAC in 2008. It was inaugurated by Honorable PM Dr. Manmohan Singh. And then third is a 9 MeV RF LINAC in 2010. Fourth is 3 MeV DC accelerator in 2030, inaugurated by President of India, Sri Pranab Mukherjee. And 6 MeV RF LINAC cargo scanning 2016. And DC based wastewater treatment 2018. It was mentioned in one of this speech by President of India, present President of India, Sri Ramnath Kovind. And 1 MeV DC accelerator, presently we have successfully tested at EBC Kharghar. I will be giving the details later on. And dual energy, already I have explained, it is a 2021 development. And recently, 2021, we have also developed a electron accelerator simulator, which is used for the training of the accelerator personnel. So this is the accelerator simulator, which is already working. Already it was made indigenously within the in-house capability, and all these subsystems are can be simulated. Like a faults can be created. If any fault is there, operator can be trained through this. And presently, we have also made 2 more simulators, that is for DC and dual energy LINAC. So coming to India, cargo scanners at gamma fields. So here it's a big team. I can say team ICS. Multiple divisions are involved for these accelerators. So they are working together, and results are quite good. I'll just show the results. So it has been qualified all the tests as per NCA and IC, and dose stability is within less than ±3%, and gantry speed they have operated 0.2 meters per minute. Coming to 6 MeV X-band medical LINACs, this already my colleague from APPD, Dr. Mondal, has assembled, and it is already, everything is ready, and it is being tested after this safety regulatory permissions. This is the best water treatment facility at EBC Kharghar. So already we have done the prototype testing of the best water, that is DAE simulated waters of 10,000 liters. And then water feeder speed is maintained at that time is 600 LPM. And COD, BOD was reduced. I will be giving the glimpse of the results. And our target is to treat 2 million liters per day. And we are planning this for this Ganga Tannery waters applications. So this is the one of the important project for the societal or environmental application, I can say.
Mr. Saroj, you have 3 minutes.
Yeah, I'll finish. So 1 MeV DC accelerator, already I have explained. I will just show the video. I think that will be important. I think if it is not working, I can go to. Okay, take care. So this is the result of the dye water textile effluent treatment using 1 MeV DC accelerator at EBC Kharghar. It was treated with various doses as shown here, and it has been found that before this irradiation dye solution, these are this moong dal that was grown on this water, and tap water, this is the tap water, this is the different dose. And after 2 days, it was found around 3 kilograms is sufficient to treat the water, and this moong dal was grown in that water. This is the another best water treatment. This graph is there where we can see EB treated is superior to the gamma radiolysis, It has been reported in one of this journal paper, RSC. And our conclusion is EB technology is most reliable, promising cost-effective advanced oxidation process for wastewater treatment among the other gamma radiation, ozonolysis, and UV treatments. This is a just flue gas treatment layout of the flue gas treatment plant, and these are the different methods like a chemical method, NOx selective catalytic reduction technique for NOx, FGD methods, and then electron beam treatment. Again, electron beam flue gas treatment has the following advantage. It simultaneously removes both SO2 and NOx. It is dry process. The pollutants are converted to useful byproducts. This is economically viable process. So these are the technologies we have already transferred to two industries. This 10 MeV RF Clinic transferred to SIMEC, India, Navi Mumbai, and Messrs. Anand Ispat Technology, Surat. And FCT technology was transferred to Messrs. CG Power Plant and Industrial Solution Limited. These are the future development to improve the thermal parameters of the cavity. So for this, in order to increase the power beyond 5 kilowatt, whatever the accelerator we are having at EBC, we are going to have a further improvement in the thermal part and cooling of the cavity. So this is the latest design. This is the footprint layout. If we want to set up a facility, we need roughly 20 by 20 meters space for the setting the accelerator. So our this collaboration responsibilities are supports in the subsystem, fabrications and procurement. From user side, we need only budget, installation and integration of the system, site and civil construction is required at user side, shielding, radiation, safety and regulatory clearance. These are the logistic and manpowers, and trial operation, electricity, training of the operator, dosimetry process and development for application, then operation of the system after handover. So thanks for your kind attentions.
Thank you. Thank you, Mr. Saroj, for the wonderful overview of various accelerator development from 500 kV to 10 MeV. I think it's a wonderful thing. And also the societal benefits you have highlighted. I think it's a fantastic thing. And my one question is that of the various accelerators that you have developed, and maybe there are several in commercial operation.
Yeah.
So how does your accelerator compare with, for example, a lot of people are importing Chinese accelerators for various purposes.
Yeah.
So how does your accelerator compare with?
Yeah, presently, as we survey the markets, most of the accelerators in India, so far they have purchased is a DC accelerators. And those
I
are
mean indigenous.
I'm just trying to tell. Indigenous, if you compare indigenous and their power rating is definitely high. They are having hundreds of kilowatt power, and we are having this energy range of 1 to 3 MeV. They are having 1 to 5 MeV. So this is the one thing. Otherwise, as you say, topology, circuits, and other things, we are better than them, because I have seen the Chinese system. They are still using the linear power supply. Our people have developed the this solid state power supply. This is very compact and more efficient. And our efficiency is 98%. There is around 70%.
Right.
So
Yeah,
these
I
are
think
the
that is a
majority.
very good thing. I think we should promote on that. Yeah. Are there any questions in the audience? Anybody? Any questions? So thank you very much, Mr. Saroj. If there are no questions, let's.
Thank you.
Yeah. On behalf of the organizers, we would like to present you with a small memento. We move on to the next talk of the session. This is by Dr. Nishant Chaudhary. Dr. Nishant Chaudhary is presently working as scientific officer in APPD BRC. His research expertise is field of radiation dosimetry and processing, electron accelerator application developments, modifications of materials using radiation, film-based devices, and polymers. He has published more than 15 peer-reviewed research papers. The topic of his present talk is aerated condition utility of electron accelerator having high vacuum field. Over to you, Dr. Nishant Chaudhary.
Thank you. Okay. Good afternoon to all. And first, I like to thank all the organizers to giving me this opportunity. And equally, I am thankful to all my colleagues of Electron Beam Center Kharghar. Because of them, I am here. A special thanks to all the contributed authors who have contributed these results, whatever given. So basically, this first slide, I have taken the picture of our two accelerator at Electron Beam Center Kharghar. And in this topic is basically coming from that aerated condition utility of electron accelerator having high vacuum field. So basically, everyone knows that the accelerator runs because of vacuum. Without vacuum, there is no concept of accelerator. So suppose this accelerator, up to this level, there is high vacuum field in order of 10⁻⁷ millibar. But after that, it is air. So all the irradiation experiments is carried out in air. So everyone knows there are one benefit that user like to do their experiment in open atmospheric condition because it is easy to handle the sample and also the accelerator person to easy to run. Because if we compare with ion accelerators, either we have to keep the sample inside vacuum field, otherwise very close to the exit window, almost in touch condition of the exit window, and that is creates problematic for accelerator persons also, that to regain the vacuum, because if sample is some moisture content, it take very hard to restore the vacuum and other difficulties. So one benefit is the user friendly in air operation, but is air do anything else that is supportive, some beneficial aspects to carry out in air? So I try to highlight both of these aspects, whatever we did. So first I give the accelerator system basic, and on the dosimetry, it is simple how the regular routine dosimetry is carried out and establish the accelerator parameters with respect to the utilization, and research aspects, whatever I told that in what is the benefit in carrying out the utilization in open air, and the green technology for electronic waste management, then the agriculture application and irradiation of food commodities. After that, I will come for some comparative merit. There is some, what is the cost affair with electron accelerators? ये पॉइंटर नहीं काम anyway. Slide is not changing. चेंज नहीं हो रहा है, यहाँ पे चेंज नहीं हो रहा है, यहाँ पे चेंज हो रहा है.
नेटवर्क नहीं है, नेटवर्क
ये कैसे काम कैसे करते हैं? Okay, no. So in this slide, as I told, the vacuum component is very crucial, and there are 7 SIPs, 5 SIPs working continuously to maintain the vacuum in the desired limit. And here is the product, and it can be viewed in magnified level in this slide. And this is the control room view to handle the accelerator by a single operator. So this is the dosimetry pattern. It is, since it is scanned beam, scanning over 1 meter of scan length. So dose uniformity is achieved, which is in order within 5% for full scan length in dynamic mode with conveyor speed, and it is in static condition at different distances from the exit window. And in this case, we have verified the energy by other methods also. One method I have given here, it is called attenuation method, by which we measure the energy of output electron, and it is coming around 9.9 MeV in terms of most probable energy of the electron beam. So these are the many applications we carried out at our center, and these are from different users inside BRC, inside DAE, outside DAE, government organization, non-government organization. There are so many, but different type of, and out of these, just like for BHEL, this is completely commercial application. Full commercialization has achieved in this case with sugarcane application of Basant Dada Sugar Institute, Pune. It is also fully commercialized. Gemstone irradiation, it is also fully commercialized at our center, and some others are under research stage presently. So the ruggedness of the system has been tested by operating it 24-hour continuously. And as per demand of user, we have operated so many times, more than 6 hours. And these are the some applications. So by seeing this graph, sorry, this table, it can be viewed that the accelerator is capable to deliver in order of hundreds of gray dose also, and in orders of hundreds of mega gray dose also. So this, the broad range of applicability of one accelerator can be viewed only from these two figures. So these are the most successful experiments which were completed, continuously going on. Here it is coming, what is the benefit of carrying out the irradiation experiment in open air? So this, we have chosen one is organic semiconductor. So in organic semiconductor, everyone knows that what are the benefits, but nowadays some things, our proper applicability wise, we are flipping for organic semiconductor also. In case of organic semiconductor, we have divided it in two parts. In next slide, I will show the conducting polymers, but in this slide, I am showing molecular semiconductor. So in this case, molecular semiconductor, if we carry out the irradiation experiment in open air, it conductivity enhances up to dose of around 20 kilogray. After that, it tending to saturation. But if we carry out the same irradiation in vacuum in order of 10⁻³ millibar, or in argon atmosphere, conductivity will not improve. So this is a a big challenge is that electron beam acts as a dopant and take the benefit from the existing air, oxygen present in the air, and this is the response which is fallen with the dose as the gas sensitivity point of view. So these two graphs shows the linear increase of this molecular semiconductor up to this dose has potential to use as a thin film dosimeter, and also the gas sensitivity wise at a fixed concentration, it can be used as potential radiation dosimeter. Why this is happening? So this can be viewed in this slide. So this molecular semiconductor is basically an insulator, and in presence of air it becomes p-type semiconductor because of the dominance of holes. So if this schematic will show this blue color, I will say it is concentration of holes, and this red color is the molecular semiconductor itself, molecules. After in presence of air, oxygen molecules are present, but after irradiation with electron beam, these oxygen pores more hole in the layer, and it increases the conductivity because charge concentration improved. When we pour the H2S in this, it gives more electrons which neutralizes the holes, and density will reduce. So this is the phenomena after introducing this reducing gas in this p-type semiconductor. The conductivity will fall after exposing to this gas, and after removing this gas, it attains the original conductivity, whatever it achieved after electron beam irradiation in presence of air. So, and why air is taking role? Because in oxygen dissociates O molecules, which ultimately generates O3, which is highly oxidizing agent, and also it has shelf life. This reaction is reversible, going on continuously. So this is the major benefit achieved in of semiconductor with electron beam. Similar phenomena has observed in case of conducting polymer, which is we have taken PE.PSS, and this is the structure schematically shown. So this is PSS and this is PE dot. After electron beam treatment, this coiled fashion will come towards linear fashion, and which increases the conductivity up to some dose, and beyond this dose, since this is polymer, so cross-linking is dominated, and that's why the conductivity falls down. But thermoelectric conductivity is saturated, but the thermoelectric power factor will increase. So it can be a suitable candidate after electron beam irradiation for thermoelectric power generation. For details, we can refer this journal paper also for the same. So these are the major benefits, whatever we have seen by carrying out the experiment in open air. Similarly, in air irradiation of case of gemstone, so pre-irradiated gemstone is like this. After irradiation, it comes like this. So pre-irradiation it is less costly. After radiation, it becomes highly costly. So if we carry out this experiment on mass scale in vacuum, it is very difficult to do. Similarly, in the irradiation of natural phosphor CaF2, which is used for waste depository, and this is with the help of our material science division, Dr. Romu Haldar, she is in the audience. So this is also shown that the radiation sustainability of these waste depository material is very high. So this accelerator technology will say us to deliver the dose whatever a waste depository material can get in life of 50 years or 25 years. This is given pre-use status of this. Similarly, this is developed by, it is not visible, it is called selenium doped GGAD single crystal scintillator, and this is developed for beta battery by NRG and TPD BARC. And in case of the life of that beta battery with the source of RU106, energy is 1.6 MeV, and 50-year span it is 5 mega gray. So 5 mega gray in one shot is given by electron beam, and after irradiation, we have tested its optical transmission spectra, and there is no change. So this certifies that this selenium doped scintillator is suitable to use as beta battery. This is the electronic waste management used PCB. We can recover the reusable pure copper from the waste, and by delivering this dose by 300 gray, we can peel off the copper, which is 99.9% pure and reusable, and a safe disposal of electronic waste. If this experiment will carry out in vacuum, this will not happen. It is tested already.
3 minutes, Dr. Nisha.
So this is ketone irradiation, one of the major agriculture application carried out at EBC Kharghar with help of Basantdada Sugar Institute, and sugarcane production will enhance by 1.4 times. And they have given this technology a new slogan, Swachh Bharat, because it is biological waste treatment, Swasth Bharat because of the no side product or harmful as compared to the inorganic fertilizers, and Samridh Bharat because farmers encasing this technology to improve their crop output. This is one important, we have achieved the seed mutation by using electron beam with help of our biosciences group, BARC, and a comparison has come that the electron beam mutation is superior as compared to the gamma rays. So different type of crops has been developed by using electron beam of, just like for horse gram, this is a comparative figure control, and it is irradiated with gamma, it is irradiated with 10 MeV beam. So by visualization, anyone can understand the productivity of electron accelerator. Similarly, this is the rice variety, and already this variety is, this is controlled, this is muted with electron beam, and already this variety is transferred with help of Tamil Nadu Agriculture University, Coimbatore, to farmer for actual use of this rice variety. These are the referred journals for this technology using 10 MeV beam. Similarly, for his Moranga, this is the dose optimization for mutation of the moringa, and it is also transferred to the Tamil Nadu Agriculture University, Coimbatore, this muted seed for actual application. These are the food products irradiated, and this is the dosimetry carried out inside the food box of rava, and the dose profile is within the desired window. Required is 400 to 1000, but we have delivered 410 to 540. So system is suitable for the different type of food products. It is at least 12 types of food products has been irradiated, and their shelf life storage in room condition has been observed. And this is the basic one, last point, the comparison of gamma with electron beam. So the cost wise, if we say electron beam is cheaper comparative to gamma, because in case of cost, this requires replacement on every 3 to 4 years. But this cost of electron beam is one time in a span of 20 years. So this is the major challenge, and if we break up this to per hour basis, so electron accelerator running at 3 kilowatt power, it costs 3,700 rupees per hour, including running cost and spare consumable spares also. But cobalt 60 requires 6,833 rupees per hour. These are the major difference and cheap saying that electron beam is cheaper as compared to the cobalt 60 source. And if I concentrate some food product irradiation, so in case of 1 ton per hour irradiation of spices, electron beam costs 3 rupees 70 paise per kg, but cobalt 60 costs 6 rupees 80 paise per 6 rupees 80 paise per kg. And this calculation is as per existing infrastructure at EBC. If we go for a dedicated facility for that particular application, this cost will still reduce from 37 paise to 32 paise. And based upon that, the throughput wise, the accelerator of in order of 7 kilowatt or 6 kilowatt is more than sufficient to generate the required tons per hour. It is not need to go beyond 7 kilowatt or 8 kilowatt for that this type of food product irradiation, because demand can be satisfied well by these as compared to the different cobalt 60 based sources. So based upon this, we are keen and invite all the researchers as well as the commercial partners to collaborate with us and use this technology, which is for the different beneficial aspects.
Thank you. Thank you, Dr. Nishant, for the wonderful review. I just have one quick question. All this amount of dosage that you're giving, especially for food items, one has to be extremely careful about it, right?
Yeah.
So,
yes.
so what is the regulatory authority and how do you adhere to that regulatory authority's advice?
Sir, basically the regulatory authority is FDA, Food and Drug Authority of
FSSA.
Of state government, and they have some partnership with Biosciences Group of BARC. So they have provided us the window of particular material. Suppose for potato, they have given us for 200 gray to 400 gray. So we have to remain within that dosing. So we are profiling the dose inside the product by layering.
After the irradiation, that products are all marked. Right?
Yes.
This is irradiated product.
Yes. Yes.
Okay. Thank you. Thank you, Dr. Nishant. Any other questions? We move on. We have, on behalf of the organizers, I would like to give you a small memento. We move on to the next talk of the session. This is by Shalaka Kamble on the title Indigenously Developed Hot Cathodes of Lanthanum Hexaboride and Cerium Hexaboride for Electron Emission. Shalaka Kamble received MSc degree with a specialization in physics and nanostructures from the Department of Physics, Savitribai Phule University, Pune. Presently, she is pursuing PhD degree from the same institute and working as a DST women scientist. At present, her research area is focused on electron emitter materials, their synthesis by thermal plasma, and investigation of electron emission, mainly thermionic and field emission behavior of microcrystalline as well as nanocrystalline rare earth hexaborides. She has published 7 research publications in peer-reviewed international journals and accredited with 1 Indian patent. Today, she will be talking to us about indigenously developed hot cathode of lanthanum hexaboride and cerium hexaboride for electron emission. Over to you, Shalaka Kamble, please.
Good afternoon, everyone. Thank you for my introduction. Am I audible?
Yes, yes. You have to share your screen.
Yes. So is my presentation visible?
Yes, yes, it has come. Please go ahead.
Okay. So I'm Shalaka Kamble from Pune University. I'm working under guidance of Professor V.L. Mathe and Professor S.V. Boraskar at Department of Physics, Savitribai Phule, Pune University. So topic of my presentation is indigenous development of hot cathodes of lanthanum hexaboride and cerium hexaboride for electron emission applications. So this is the outline of my presentation. First, I will give brief introduction about the motivation behind this work, and then introduction about the experimental details, and then I will discuss results which I have got, and then I will conclude. So as we have listened that in the lanthanum hexaboride and cerium hexaboride cathodes have various technological applications. They are mostly used for electron emission purpose. So they are used as a cathode in electron guns, and these electron guns have finds application in X-ray tubes, plasma thrusters, accelerators, etc. So the work began at the beginning of my research career. I was working as a BRNS GRF fellow on the on one project in which our aim is to fabricate the densified nanocrystalline lanthanum hexaboride cathodes, and this cathode will be used for used in the electron guns, which are designed and developed by Electron Beam Center, BARC, Kharghar, Navi Mumbai. So presently they are using imported cathodes, and our aim is to find the substitute for this cathode, and that substitute has to be indigenous. So we are searching for the indigenous technique to develop the nanocrystalline lanthanum hexaboride cathodes. And also in addition to that, presently they are using microcrystalline LB6 cathode, which is a pallet of around 10 mm and thickness about 1 mm. So our aim is to synthesize nanocrystalline cathode. So the idea behind using the nanocrystalline cathode is like if we consider the surface, on the surface, if there are microcrystallites, and if we replace that microcrystallites with the nanocrystalline, then the emissions sites will be increased, and due to this, the electron emission will enhance. So looking at this, we started our work. So this is the whole experimental process to synthesize lanthanum hexaboride and cerium hexaboride microcrystalline as well as nanocrystalline powders first. So this is the first step. So we are we have synthesized microcrystalline lanthanum hexaboride and cerium hexaboride by using SHS process. So SHS process is this is the SHS reactor which I have shown here. So in the SHS reactor, there is a mixture of lanthanum or cerium oxide has been taken, and along with them boron oxide and magnesium powder will be mixed, and in this mixture will be burned or this is the this mixture. So the combustion will be started with the help of ignition pallet, and due to this the whole mixture so combustion of the whole mixture will be started, and after that it will take around 2 to 3 minutes to the full combustion of this mixture, and then we will get the crude mass. So after leaching, we will get lanthanum hexaboride microcrystalline powder if we use lanthanum oxide. If we use cerium oxide, we will get cerium cerium hexaboride microcrystalline powder. So this microcrystalline powders then we use to synthesize nanocrystalline powders by using arc plasma gaseous condensation method. So in this method, this is the arc plasma gaseous condensation route consists of a water-cooled stainless steel reactor in which there are 2 electrodes are placed. So the assembly is as it is shown here. So there is one cathode and anode which are vertically mounted, and this cathode and anode, the plasma will be stuck between this anode and cathode in the inert atmosphere of argon or nitrogen or helium. So depending on our desired product, we choose the ambient gas, and at the subatmospheric, the plasma was stuck. Because of this, the temperature of plasma is very high. So it is around 5,000. So at the center of the plasma, the temperature is high of about 5,000 to 10,000 Kelvin. Due to this high temperature, whatever precursor material which we have kept here on this anode, that will be evaporated. But as the evaporated particles go from the center to the periphery of the plasma, they will see the steep temperature gradient. The particles will be nucleated at the periphery of the plasma flow. And then as they see that steep temperature gradient, there is no further growth of the particle. And because of this, the nanocrystallites will be formed at the periphery of the plasma, and then they will be settled on the inner walls of the reactor. And walls of the reactor, they are water cooled, so that the particles should not stick to the wall. They only settle on the wall, which can easily scrape out. And in this way, we have got nanocrystalline lanthanum hexaboride or cerium hexaboride powder. So the products which we get here, both are in the powder form. So this powder we can use to fabricate pellet ship cathodes. So this is there are so many sintering methods are available right now, like tube furnace also we can use. We can use other vacuum furnaces, because lanthanum hexaboride or cerium hexaboride or other rare earth hexaboride, may get oxidized after 800 degrees Celsius. And for sintering, we require the temperature above 1200 degree Kelvin or above. So because of this, to hinder the oxidation, we require vacuum furnaces. But the cost of vacuum furnaces is so high. So then we have searched for the new method, which is novel arc plasma sintering process. So in this method, we have only changed our uh, anode design such that here you can see here are this anode will have a cavity, which is this cavity is exactly as the size of the pallet which we want to keep here. This pallet we have made with the help of hydraulic pallet press. So depending on the depending on the size and shape, we fabricate anode of that dimension, and thus this pallet is kept inside the cavity. And then again, the plasma will be strike on this anode. So because of the high temperature of the plasma, this anode also gets sintered. But here the main issue is we should not want to evaporate the pellet, only we want to heat it. So here we have optimized the plasma current and other plasma parameters such that this pellet should not be get evaporated. Only the sintering process can be happen. So like this,
Shalaka, you have 3 minutes.
Yes, sir. So so this is the whole process of development of a cathode. So this is sintering of LAB6 cathode. So we have already reported sintering of LAB6 cathode in the IEEE journal. So these are few results. So before and after synthesis, when we synthesize microcrystalline powder, we have confirmed the phase purity of the powder by using X-ray diffraction as well as Raman spectroscopy. And for morphology also, we have used FESM and TEM. And after confirmation of phase purity, we go forward to, further to synthesize a nanocrystalline powder. After again synthesizing the nanocrystalline powder, we confirm the phase purity as well as we check the morphology of the powder, and then we fabricate the cathodes. So while fabricating a cathode, we use PVA as a binder, and then so this is the FESM image of the cathode, which is recorded before sintering. So we can see that there is a surface roughness here. So so these are the optimization result for sintering. So in the arc plasma sintering setup, we have put the pallet of the 5 mm pallet, and we have varied the sintering duration. So as we vary the sintering duration, we can see that the sintering sintering effects are different for the various duration of sintering. So at the 10 minutes, we have get optimized results for the sintered pallet, and the optimized density obtained for this pallet is around 94%. So all these results were reported in IEEE publication. So these are so similar method followed for sintering of CAB6. Yes, sir. Yes, sir. So this same procedure has been followed for to sinter the CAB6 cathode. These are the X-ray diffraction results where we can see that the phase pure sintered pellets have been obtained, and the FESM image also shows the sintering of the pellets. So apart from this, by the similar method, we have synthesized microcrystalline as well as nanocrystalline gadolinium and other mixed hexaborides. So, and we have patented this. The patent has been published. So in conclusion, I can say that present work reports an economically viable and easy way to obtain densified cathodes of cerium hexaboride and lanthanum hexaboride, and this may act as an import substitute. So this is the actual photograph of the cathodes. So I would like to acknowledge my Professor P.L. Mathe and Professor S.V. Boraskar, as well as our collaborators, my lab mates, and Electron Beam Center, DRC Mumbai, and BRNS and the DST for funding this research. Thank you.
Thank you, Shalaka. I think it was a wonderful presentation on indigenous preparation of mixed as well as lanthanum and cerium hexaborides. There are any questions? Yes, yes. Due to shortage of time, we are not able to take any questions at this time. Shalaka will be available by email for any questions. Thank you very much. On behalf of the organizing committee of VSTA, we present you with a small memento. It will reach you. Thank you very much, Shalaka.
Thank you, sir.
Our next talk is on upgradation of indigenously developed BAG controllers in RRCAT. This will be given by Shri Dhananjay Devkar. Shri Dhananjay Devkar joined RRCAT in the year of 1989 and has been working in the field of ultra-high vacuum instrumentation since last 32 years. His area of expertise is development of SMPS and ultra-low current measurement for high vacuum requirements of accelerators. Currently, he is working as design development engineer in ultra-high vacuum section in RRCAT Indore. Today, he will be talking to us about upgradation of indigenously developed BAG controllers in RRCAT. Over to you, Dr. Dhananjay Devkar. 10 minutes plus 2 minutes. Please share your screen. Sir, we are not able to hear you still. And please share your screen. Sir, we have to go ahead. Can you please share your screen? Audio is also not coming. You have to share your screen. Sir, can you please check your audio jack or mic volume, either of them? Mic volume is okay. Audio jack is okay. Your screen is not shared still. We are not able to see your slides. Sir, due to paucity of time, we will have to cut it here. We will give you another slot maybe tomorrow morning. We will inform you accordingly. Thank you. Thank you, sir. So with this, we come to the end of this session. It has been a wonderful session. There have been 6 talks in together. The development of vacuum devices and electron emitters. On behalf of the organizing committee of VSTAA, I would like to thank all the speakers of this session, and sorry for Dr. Dhananjay Devkar, who could not be talking to us due to technical reasons. However, he will be given a slot or for talking his speech some other time during this symposium. Thank you very much. Over to session coordinator.
Thank you, sir. Thank you for coordinating the session. As a token of our acknowledgement to your contribution, please accept this. Thank you, sir. Thank you.
It has been an excellent session, sir. Chairing and interacting with the speakers. This was really good. Excellent.
We will for 10 minutes break for tea. Okay. After that, next session.
Hello, hello, Rajdeep sir.
Yeah, hello.
Yes, sir. Please do not check your slides and all because this is going on YouTube live. You will be shortly connected, sir.
Okay. So
Okay.
because I
Okay, yeah.
wanted to ensure that everything is okay. That's why I wanted.
Yeah, everything is fine. Everything is fine. Am I audible to you? You are audible to us. Everything is
Yeah,
fine.
right now it's
You
fine.
just don't share anything right now. Okay, sir.
Okay.
Okay. Yeah. Thank you. Thank you.
Thank you.
Good afternoon, everyone. Welcome to the 8th session of DAE-BRNS International Symposium on Vacuum Science and Technology and its application in accelerators. So topic of this session is vacuum technology in nuclear application. We have 5 distinguished speakers with us for this session. We have also requested Mrs. Uma B. Rao to chair this session. It's an honor for me to introduce Mrs. Uma B. Rao. She is presently working as head solar panel characterization and analysis section at UR Rao Satellite Center, Bengaluru. She has worked as a project manager for prestigious Mars Orbiter mission and GSAT-15 spacecrafts. She is deputy project director for various satellite projects. She got ISRO Team Excellence Award in 2016. So I welcome Mrs. Uma B. Rao and also request her to take the session ahead. There are 3 invited talks and it will be half an hour, 25 minutes the talk will be there and 5 minutes it will be question session. And 2 presentations are there. This will be 12 minutes and 3 minutes for the questions. And the first talk will be by Professor Rajdeep Singh Rawat. Professor Rajdeep Singh Rawat is currently a professor in physics and head of Natural Science and Science Education Academic Group in National Institute of Education, NTU. He did his MSc and PhD in physics with the specialization in experimental plasma physics from University of Delhi. He is currently the president of Asian African Association for Plasma Training since 2012 and president of International Physics Olympiad since 2018. He serves on board of directors of Division of Plasma Physics of Association of Asia Pacific Physical Society, and he also serves as associate editor for Review of Modern Plasma Physics and as educational editorial board members of Plasma Physics Express, IOP Journal, Journal of Theoretical and Applied Physics, Springer, and Physics Educator World Scientific. I welcome Professor Rajdeep Singh Rawat to give his lecture.
Thank you, Dr. Uma. May I share my screen now?
Yes, sir.
Do you see my screen?
Yes, sir.
Okay, I'm going to make it full screen. Do you still see my full screen?
Yes, sir.
Okay, but I'm going to
Sir,
stop.
can you speak a little louder?
Okay, just give me a minute. Do you see my full screen now?
Yes, sir.
All right. So,
Yeah, it is.
am I audible enough?
Yes, sir.
All right, then may I go ahead?
Yes.
All right. So, good afternoon, everybody. I'm Rajdeep from Nanyang Technological University, Singapore, and it is my pleasure to give a talk in this wonderful symposium. So I'm basically going to talk about the plasma focus device as a novel high density, high temperature plasma source for material processing and synthesis. I do understand there are many people who are working on many different fields, and the talks that I've been attending so far were mostly on the electron beam sources and the electron accelerators. So this is basically different from that. Of course, plasma focus is also called as a plasma gun. And so it's also a kind of a plasma accelerator. And because of the plasma instabilities, actually you also get electron beam accelerating to relativistic energies even in this device. And ions also, of course, being accelerated to high energy. But before I go on to proceed and talk about the content of my talk, let me just introduce our group. We are a very small group in Nanyang Technological University. This is probably one of the 2 plasma groups that NTU has, my university. So we work on this, the so-called dense plasma focus device, the one which you see over here. Let me see, my pointer is. Okay, so yeah, my pen is not working on. Okay, never mind. So this dense plasma focus device is the one that we have, and we also work on laser plasma sources because one of my colleague, Dr. Paul, he's from this Rutherford Appleton lab, and we have one nuclear physicist, Dr. Springham, in our group, and basically 3 of us work together on many different fields related to plasma, plasma focus and other work. So plasma focus simply is nothing but a coaxial plasma gun, as I pointed out. What you do, you store the energy in the capacitor bank over here, and then basically you close your switch, so energy is discharged into this coaxial plasma gun where we have an anode in the center. So the device is designed in such a way that the discharge actually initiates at the lower end of the device first, the so-called the closed end. And then because of the current flowing through this plasma, we have an azimuthal magnetic field, which pushes this plasma with a very high speed in the axial phase first, and then this plasma collapses at the top of the electrode system, so forming a hot dense plasma over there. So that is what you see over here. And this device is always designed in such a way that because this basically is nothing but an LC circuit, so it is designed in such a way that the plasma, when it reaches to the top of the anode, basically the current is also maximizing. So that means it is matching with the quarter time period of the LC circuit. And because of this, the very high current is flowing through the plasmas. So this pinch plasma, typically the current that flows through this is of the order of 100 kiloampere in a small device that we have, to almost close to half a mega ampere in the 10 kilojoule plasma focus device that we have. So in this device, this plasma basically being accelerated in the axial phase gets heated not only because of the current continuously increasing over there, but also because of the shock heating, and then compresses. When it compresses at the center, at the top of the anode, it again gets heated not only because of the high current, but because of the kinetic energy converting into, basically the heat. So this hot dense plasma over here can go to the temperatures which are of the order of about a keV. And this plasma, the cylindrical plasma, then suffer from the MHD instabilities, and that is basically because when you have a cylindrical plasma with the current passing through it, then basically the onset of MHD instabilities are there. So we get M0 and M1 modes of the instabilities, basically the sausage and the king instabilities, and those instabilities break up the plasmas resulting in the accelerations of the electrons down the electrode, which hits the electrode system and therefore can produce even the hard X-rays. And also because, as I mentioned, that the plasma is about a keV degree hot, so it also generates quite a good amount of soft X-rays as well. And at the same time, since the plasma is about 1 keV, if we fill it with the deuterium gas, we actually get some fusion reaction going on over here. But the main fusion, main source of the neutron production over there is not basically the thermonuclear plasmas. But because of the instability formation over there are high energy neutrons that are accelerated in the upward directions. And then they produce the neutrons by the beam target mechanism. So this device actually is also a sort of a multiple radiation source where we get not only the relativistic electrons, high energy ions, and as well as when you fill it with the deuterium, you can get neutrons. So we can do some investigations related to that. But in addition to that, this plasma also decays in the form of, the hot dense plasma streams. So you have a hot dense plasma also, which keeps on moving, accelerated in the upward direction. And that is what we use in order to process the materials. So what we do, we use this device for the processing and, deposition of material, which I will explain later on. So we have over the year developed many of these plasma focused devices in our lab, more than 10 or 11 of them. 4 of these devices we have given to our collaborator in US and Imperial College, and 1 in Greece and 1 in the neighboring Malaysia. But and 1 in China also recently. But we are still having about 6 of these devices with us on which we do different work, right from different, fundamental studies, as well as the application related work. So today I'm going to focus basically on the material processing and the material deposition related work that we have done over here. And in addition to doing just the experiments, we have also developed these devices, as I mentioned, and we have also focused quite a bit of resources and energies in developing high repetition plasma focused devices. And later on, you have a speaker over here, Dr. Rishi, who did his PhD from NTU, and he was the one who developed this FMPF3, the fast miniature plasma focused device, which is basically sub-kilojoule, basically 200 joule device, but operated at 10 hertz. So it basically is a rapidly plasma focused device. And to diagnose these devices, we have several sets of diagnostics ranging from, the electrical diagnostics, we have the optical diagnostics, we have X-ray diagnostics, and we have also developed a large number of neutron diagnostics over here. So this simple system actually gives us a platform where many different work can be done. So as I mentioned that the focus of this talk is basically about the plasma processing and deposition. So what happens is that when this pinch plasma formed at the center of this anode, like what you see in the gated IC3D imaging that we have done. So the plasma that is formed over here, it moves in the upward direction, and normally we place a substrate somewhere at the top over there. And that substrate actually then is exposed to the plasma that is coming from the lower side. So it is not only exposed to the plasmas, it is also exposed to the high energy ions. And if you are operating with the deuterium gas, you also get it exposed to the neutrons as well as you get it gets exposed to the X-rays and so whatnot. So basically it gets exposed to many different kinds of radiations. So the material that is exposed over there that can undergo many different processes, and what we have seen, we have achieved the phase transition in these materials. We have reconstructed the surfaces. We have achieved ion implantation, and we have done the nanostructuralization, basically synthesis of one-dimensional and even two-dimensional and three-dimensional nanostructures. As far as the deposition is concerned, normally we try to do this deposition by placing a suitable choice of material at the top of the anode, the electrode basically. And this hot dense plasma as well as the relativistic electron beams, they ablate this material. And this material, therefore, ablated material, it goes in the forward direction. And if you put your substrate over there, you actually can do the deposition of this. So what you see over here is a sequence of laser shadow graphs, basically taken using the 1 nanosecond nitrogen laser at the different times just after the pinch phase. That means once the pinch plasma column is formed. And over here, it's a graphite top. So as you can see, the graphite material starts to ablate, and it ablates for about a 2 to 3 microsecond duration. And we can form a thin film over there. And the advantage of this plasma focused device is that the plasma is over here is so hot, so dense, and the process is so energetic, and the conditions are so extreme that the amount of material that is ablated from the anode top is actually very large, and that actually gives some kind of an added advantage, which we will discuss later on. So we have done different types of depositions using this device, basically because the electrode, you want to maintain the current to flow through it. So normally we end up using the metal electrodes or the graphite, that means the conducting electrodes. And then you can use the background gas as a reactive gas. So with the plasma focus, the good thing is that it works with any kind of gas, right from the neutral gases. I mean, the noble gases like argon, neon, which we routinely fire this one device in, but it works very well in nitrogen, carbon, oxygen, even acetylene, methane, anything you put in it, you just need to find out the right pressure where it can focus and, can generate all these interesting things. And the materials that have been deposited or processed using this material, we have shown that, they normally exhibit superior or enhanced properties, and there is a reason for that, because this is a hot dense plasma that not only helps in the deposition process, and most of these depositions, because they are the multiple shot depositions, during the next shot, the plasma, the hot dense plasma precedes before the deposited material comes, and actually sort of process your deposited materials. And in plasma focused device, these ions, they are not only carrying the large amount of energy, but the flux is also very high, because the typical pinch plasma density is of the order of 10 to the power 24 to 25, maybe up to 26 particles per meter cube. And the absolute number of particles in the pinch is somewhere of the order of 10 to the 16 to 17. So you get a very large flux of particle, and therefore a large amount of energy can be deposited on the material. So that actually sort of treats the material, and most of the time we don't really need the post-deposition annealing in this device to achieve the crystalline phase of the material. Otherwise, normally people, when they deposit materials, they are normally in the amorphous form, and they have to do the post-deposition annealing maybe 1 hour, 2 hours, sometimes even 10 hours, sometimes even 2-3 days. Whereas in plasma focus, by nature, we have a very fast transient annealing of the substrate that is placed over there, substrate of the film that you are depositing over there. So that fast annealing actually helps in achieving the crystalline phase most of the time directly. So if I just mention the chronology of the kind of work, materials related work that has been done on plasma focus device, it started a long time ago, more than 30 years ago, by a group in Argentina in 1988, when they used this plasma focus device to process the stainless steel, the leftmost figure, as you see over there. But then after that, our group, when I was working as a PhD student, Delhi University, we used this plasma focus device to process the PZT thin films. This is lead zirconate titanate thin films. These are very thick films, which after even about 10 hours of annealing was not getting crystallized. But in plasma focus, we showed that okay, within one shot we were able to crystallize it. And then later on, we used this plasma focus to basically ablate the material which were placed downstream to deposit the carbon films, fullerene deposition, and so on and so forth. But later on, we shifted to different types of deposition, where we started using the anode fitted with the metal targets, and then use the background reactive gas to deposit any thin films. And this method was much more reliable, and many different films were grown by that. And later on in 2012 to 2016, one of my PhD students basically focused on synthesizing carbon nanotube using the plasma focus device, and we could even do that within one shot using this device. And later on, we are actually also able to successfully deposit even the graphene. So what are the advantages that this device actually shows for material deposition or processing? First of all, we can get extremely high deposition rates over here, and I will show some example. The films that are deposited in this case, they are dense, they are not porous, and because, as I mentioned, that this device basically is a pulse plasma device, where the quarter time period is of the order of few microseconds. So the entire deposition process is actually very fast. The entire plasma lasts. We have done even the post-pinch plasma dynamics measurements in this plasma focus device. The plasma does not last more than you can say about a microsecond, or maybe more than 100 microseconds or so. So it is still a some millisecond deposition. So it's extremely fast deposition or processing, you can say. And we can achieve the phase transitions. Different types of phase transitions have been achieved. Phase transition not only in the sense the change of the amorphous to crystalline or crystalline to amorphous, but the phase transition in the materials themselves. For example, the stainless steel was changed from one phase, martensite to austenite, and many other works that were done by some other groups all around the world. And material properties, after being processed or being deposited in this, normally, as I mentioned, they show superior properties. And I'll just give some of the examples over there. For example, over here, this shows the nice coatings of the magnetic materials. One of my PhD student, Panchening, she was focusing on the cobalt platinum thin film deposition using plasma focus and using PLD. So while in PLD, we were depositing like 50 nanometer thin film after, 1 hour of firing the pulse in the Nd:YAG laser at 10 hertz. In plasma focus device, we could do the same job just after firing 20 shots, 30 shots, or 50 shots maybe. So this was much faster deposition. So deposition rates are extremely high. For example, another work where we are showing the deposition of the zinc oxide. And zinc is a softer material, and the deposition in this case was even much higher. For example, in COPT, the deposition rate was typically between 1 nanometer to 4 nanometer per shot. But for zinc, we were getting like 50 nanometer per shot. So in fact, we demonstrated that this plasma focus can provide deposition rates faster than any other device, because many different people have reported many different methods of depositing zinc oxide. So, but this one exceeds the deposition rates exceed any one of them. The second thing, as I mentioned, that your materials are getting bombarded with the hot dense plasma during the next shot. And that actually helps you in getting the denser films. And so our films are very packed, very dense. So that is what you can see in this, the cross-sectional SEM of COPT as well as the zinc oxide thin films. So normally we get that. Now, another thing that we did was the surface reconstruction of these materials. We have done it for the bulk substrates as well as for the thin films. So for example, one of my student, he was working on magnetic nanoparticles, very small magnetic nanoparticles of the size of the order about 5 to 10 to 20 nanometers. And these magnetic nanoparticles, when they are smaller in size, their coercivity is very high. That is what we were looking for, so that they can be used for this, data storage application. And one of the ways that we were depositing these nanoparticles was using the PLD method. And PLD method, in order to get the nanoparticle formation, we have to control the pressure and the laser energies and the substrate to target distance very precisely to get the nanoparticles. And then because it was deposition normally at higher pressure, to get the nanoparticle synthesis in the gas phase migration, we used to take a lot of time. Then what we thought is that why not try to use plasma focus? So we, instead of depositing nanoparticle, we just deposit a smooth thin film of about 60-70 nanometer using the PLD method. So over there, you don't need much control, just use the very high vacuum and you can deposit smooth thin films. And then we irradiated using plasma focus. So within a single shot, the material morphology is changed, directly from the smooth thin film to the nanoparticles. If you increase the number of shots, of course, because of the energy from the next shot, these particles starts to, agglomerate together to form a bigger size particles. And that is what you see in the image down there. Now, in addition to that, as I mentioned, that they mentioned superior properties. For example, for PLD related synthesis of the magnetic nanoparticles, we were getting not only the phase of the material that we wanted to get into, but we were getting some peaks which were unidentified. Like, for example, over here in the XRD on the top left corner, you see many of the peaks are not labeled because we were not able to identify them. They were like an impurity peaks over there. And these material, which is basically FEPT, is supposed to be very highly hard magnetic material, and the coercivity of the material was supposed to be much larger. But what we find when we do the VSM measurement, the coercivity was not that high. But the same thing when we use the DPF for the deposition as well as for for synthesis of these materials, all those impurity peaks they disappeared, particularly in the DPF based synthesis, like what I was showing before. Panchening's work. And because there were no impurity phase, the magnetic properties were excellent. As you can see in the lower figure over here, they were very hard material. Hard material means anything with the coercivity greater than 100 OE values, they are considered hard. So they become extremely hard, magnetically hard materials. So we got basically better properties using this. And there are tons of these examples because we have published about more than 90 paper, close to 100 paper on this work. There are many other work where we observe the similar things. But over here, I'm just citing some reference things. So now let's look at certain criticism that this material faced, because everybody will ask, if it is so good, why it is not being used in the industries. Of course, there are certain criticism that this device always face, and that is basically there is a limited type of depositions. That means you get most of the time nanoparticles because the plasma focus by default work in the millibar pressure range, and when you do that, the plasma ablated and passing through the gas phase, it starts to synthesize nanoparticle in the gas phase itself. And because normally you are ablating the material from the pinch plasma region where it is basically expanding in the outward direction. So lack of uniformity is another criticism that this device faces. And similarly, because the anode has to be metal, previously we were all most of the time thinking, okay, it is very limited metal-based depositions, not much.
We're having 5 more minutes.
Yes, I do see that. I see 20 minutes right now. Okay, yeah. I have my clock on, so I will finish that. And then short-to-short variation because of the uncertainty in this. But these criticism, we over the year with our experience on deposition using this device, we are able to take care of that. We are able to not only deposit the nanoparticle morphology, we can get one-dimensional structure like what you have seen in the previous one. In one of the work done at the CRP Guwahati, together with collaborators Smriti Mohanty, we were able to synthesize the polyaniline nanowire by exposing the polyaniline with the electron beam in this device. Similarly, as I mentioned previously, that we were able to deposit carbon nanotube directly using this device. So what we did over here in this case, we used the carbon precursor in the device and fired it using the plasma focus device, and within a single shot. So I'm not going into the details of it. Of course, for the CNT deposition, you need to have a catalyst layer. So we were depositing the Fe catalyst using PLD, and then use the heat to convert them in nanoparticle. And when you fire in the plasma focus device, we could grow vertical carbon nanotube within one shot. So this is something which we are patenting. And these are basically 2 micron nanowires that we could obtain. And there is another thing that people normally want to get is, can we take out the catalyst layer? So can somebody directly grow the material on the stainless steel, say, substrate, which is might have some useful applications, particularly for as an electron emitter. So over here, normally what people do, they etch their material using chemically so that they can get some nanostructure and then they grow on that. So in plasma focus, because high energy ions precedes the plasma coming first, we showed that we can directly deposit the carbon nanotube on the metallic nanopart on the metal substrate using the plasma focus device, again in single shot. And we also have shown the deposition of the graphene as well as the the 2-dimensional and the 3-dimensional graphene using the plasma focus shot. And so far we have also deposited the large area, uniformity of the device, of the deposition. We can deposit it over the 3-inch substrate previously, but now we have developed a bigger device where our anode dimensions are much larger, so we can do a whole hard disk platter, a 65 deposition very uniformly, and we are patenting that technology basically for 1 nanometer thick carbon coating. So I'm not presenting those results over here. Reliability issues, reproducibility issues sometimes are highlighted, but we have shown that if you know your device well, you know how to condition it, it is actually very reliable. And basically because of the averaging, normally you are doing multiple shot deposition, you are able to reliably get what you want to get using plasma focus device. So previously people thought you can only do the metal-based deposition, but we have shown over the year that you can go from the metal to the metal oxide, nitrides, carbides, particularly by using the background reactive gas. And now with the CNT, we have also started to show that we can do a pure gas phase deposition using the plasma focus device. No need to use the anode material as the deposition material. There's another interesting application of plasma focus device which I wanted to highlight, was that in plasma focus device, the amount of heat load that will be there on the substrate, particularly at the closer distance, actually is higher than what the diverter, even the tokamak has. So for example, the heat load in the tokamak, in the diverter region, It's about of the order of about 2 to 20 megawatt per meter square. The plasma focus at the close vicinity of the pinch, actually you can get the heat load much larger than that. And in addition to that, plasma focus also provides you, the neutrons. And as I mentioned that the amount of heating that is done in the plasma focus is extremely fast. I mean, the rate at which the temperature can rise on the exposed samples are extremely fast. So this device actually provides an excellent low-cost alternative to do experiments where you want to test materials under extreme conditions. And since I knew that I don't have much time to talk about this, so this is not the focus of that talk. But we did publish some work recently on this, which are listed over here, which are related to the use of, exposure of tungsten material, carbon materials, stainless steel in plasma focus under different conditions to expose it to the various types of plasmas so that, and then later on evaluate. And most of these works are done under the projects, the coordinated research programs of IAEA, because IAEA does recognize plasma focus as an excellent facility where these kind of experiments are done. So in that IAEA CRP, it's not only the plasma focus group that are there, it's the people from the tokamak community, people from the electron beam Zulik facilities, and the other reactors are also there. So they basically share the substrates, and then try to expose them and try to understand what are the changes taking place over there. So under that kind of a collaborative program, we did some materials, under extreme conditions kind of work using this device. So this is my concluding slides. So basically, plasma focus is quite a versatile device. It's a very easy to make it. It has low maintenance, but it has a very rich physics. You can do many different kinds of basic plasma diagnostics, which we basically do. And then it is a very novel device for material processing and synthesis, including the testing materials for fusion first wall materials. So I think with that I stop. I probably still have 4 minutes for Q&A if there are any. Thank you very much for your attention. So I'm done.
Thank you, Professor Rajdeep, for your enlightening talk on high density, high temperature plasma for material processing. It has got a lot of industrial application in future. I'll open this floor for questions from the auditorium. There is one question.
Is there any question?
Yes, sir. Yes, sir. There is one question.
Increasing the strength of tools, people generally use nitriding process, and that is the inductively coupled plasma process. So how does your high temperature, high intensity plasma compare with this process, and will it help in increasing the tool strength, for example, like how they do it in nitriding, for example?
Yeah, so it definitely will help, and there are papers that we have published even on nitriding of zirconium, nitriding of titanium. Two things: either we deposit titanium nitride on the tools, or we deposit we nitride the material themselves, and that definitely has improved the material properties in terms of its hardness, in terms of other mechanical properties of the material. But the problem with the plasma focus device is it's not a volume plasma in that sense, So in ICP plasma, you have a volume plasma where between the
How does it compare with other processes? I mean, your nitriding, is it as strong as other
Yes,
processes?
it is as strong as possible, but you see the tool, it is only treated on one side because the plasma is coming in, is a directional plasma. It's forming at the top of the anode and then coming over there. So it's if you treat the thin films and all that, it's fine. But if you want to have a tool, then you have to develop it. But there can be a solution. All we need to do is
rotate the tool.
develop this repetitive plasma focus device and then rotate the tool, and then it can be done.
Yeah, right. Yeah. Thank you. Thank you, Dr. Rawat.
Welcome.
The online participants are having the question. I think there are no questions. Thank you, sir. On behalf of conference committee, a token of appreciation, a memento will be given to you, sir.
Okay, thank you for listening to me. Thank you very much. So I will stop sharing. Oh, it's already unshared. Okay. Thank you. Bye-bye.
Next invited talk will be by Dr. A.K. Gupta, Head NPD, on an overview of our activities at 14 UD Pelletron Accelerator and ECR based heavy ion accelerator program. Dr. A.K. Gupta joined Nuclear Physics Division BARC in 1990. Since joining, he has been closely involved with BARC TAFR Pelletron Accelerator Facility, a workhorse for conducting heavy ion accelerate based research in frontier areas of nuclear physics and diverse applications. His comprehensive body of work performed in-house has resulted into self-reliance in negative ion sources and beam technologies. Delivering ion species across the periodic table over the years, he has successfully established new application-oriented programs of departmental interest, enhancing the accelerator utilization factor significantly. His recent experimental work has augmented the accelerator facility for unambiguous identification of exotic negative ion species using accelerator mass spectrometry technique as a tool. He is leading the ECR-based heavy ion accelerator development program at BARC. Dr. Gupta is currently heading the Nuclear Physics Division, BARC. Welcome, Dr. Gupta, to give a talk.
Can you hear me? So good afternoon to everybody, and let me thank the organizers for giving me the opportunity to present the work. So I will be talking about an overview of activities at 14 million volt Peloton Accelerator and ECR-based heavy ion program. Currently, we are pursuing it at BRC. Okay, can you go down? Oh, so small. Every time. Okay, thanks. Yeah. So the outline, the accelerator overall activities, they have divided in three parts. The developmental aspects, the application-oriented activities, and the high voltage upgradation we have recently planned. And you know, in any facility to sustain for last more than 3 decades, you require a very consistent team to ensure that all your preventive and schedules for the maintenance operation, as well as, you know, the developmental aspects are consistent to give you the highest, you know, possible output and consistent operation so that the current level of scientific output could be sustained. And the another part of my talk is the status of ECR-based heavy ion accelerator program, which is basically consists of 18 gigahertz superconducting ECR source, and followed by a prototype heavy ion RFQ, which is under development. It's a 75 megahertz room temperature RFQ. And then I will be also talking about low beta, high beta superconducting ion developmental work, which we have initiated currently at BARS. And it is a collaborative pursuit. Now here is the facility, as you know, the facility basically is a 14 million volt machine. The whole accelerating structure is housed in a SF6 environment up to some about 6 bar SF6 pressure to provide the sufficient insulating strength. And then the If you look at here, you have the negative ions which are indispensable to any tandem accelerator. They are injected from the top. The variety of sources are here, which provides beam right from proton to, all the way up to uranium. All kind of elements can be covered. And we have dedicated sources developed in-house to provide the negative ion injection as per the user requirement. The negative ions are injected and they are further accelerated down after mass selection. And then once they reach here, the Q into V is the energy gained. So if I have 14 millivolt, 14 MeV is the negative ion energy by the time it reaches here. And because of the velocity, it gets stripped. And the multiply charged ions are further accelerated depending on the charge state. So you not only gain the energy in first stage, but also multiply depending on the charge state in the second stage. We call it low energy, and this is high energy. And the final ion beam with multiple charge states, further charges is selected here with another magnet. And the monoenergetic and the single mass ion is then transported to, left side of my, the slide is the cascade hall, where there are 5 beam ports for the desired experimental setup. And right to this is a superconducting LINAC booster. So the energy available typically from electron is further boosted using a superconducting LINAC, which is lead-coated copper LINAC system. And the facilities which we have here, it caters to nuclear physics, let's say predominantly, but you have other associated programs right from atomic condensed matter to applied programs, which are all well established, and also they are being used for various local departmental, let's say, usage, as well as by other non-DAE organizations. And typically the users are, BRC, predominantly BRC TFR, and you also have what non-DAE like ISRO and university institutions. These are the typical, output showing you over the years, including about 20 PRLs and letters actually. And here I show you the, specifications. So this is as I said, 14 megavolt machine, and the column rating is 15 megavolt, and you can have 100 particle nanoamp kind of beam at the target. And these are the typical beams which are accelerated so far, right from proton to iodine 129. And also molecular negative ions are also injected here depending on the, let's say, user interest. These are the beams through superconducting LINAC booster, because you have while injecting into the LINAC, you have to match the velocity acceptance of the LINAC, or also you should have a bunch beam. So your timing and as well as the bunching characteristics has to match before it is accepted by LINAC. So the limitation comes from the overall voltage from the peloton. So by now up to actually 37 I have not included. Up to 37 it has been accelerated through LINAC booster. This is the typical performance. If you look at the overall per decade, this is how the nuclear physics contributions and other allied, disciplinary, multidisciplinary areas are indicated here. You can see the typical growth, including the one which are having high impact factor generals. This is it. Now I show you that to sustain the the scientific output, you will have to maintain the voltage around 14 MB. But as it is machine is around more than 33 years old, there is a aging. So we would like to replace the accelerating structure from this is the existing one where there are 3 tubes in 1 million volt module by 2 tubes where the number of gaps, if you look at here, the drift space is completely removed, and you are able to insert more number of insulators. So you gain insulating strength by about 25%. Therefore, these the rating of this, let's say, let me call it high gradient tube, is around 1.3 to 1.4 MB, we save us 1 to 1.1 MB here. So there is a gain of net gain of voltage, and so the effective energy of the ions accelerated. To support these work, because this is not a what you turnkey project, you have to have the same team doing in-house development to sustain the various kind of beam requirement, and also the control and data acquisition systems. So I show you here the test bench where dedicated source like beryllium campaign, we require there's a different kind of system where you have typical, because of carcinogenic nature of the cancerous nature, you require very different kind of handling and safety measures. There's one, then you have dedicated lanthanide actinide negative ion sources, and they impair the ionization efficiency. Therefore, there are different methods we have utilized to generate these beams. Now, these are various dedicated sources have been developed on this test bench facility, and this is also used when you are not doing the developmental work to various applications, such as, you can do production characterization of polyatomic anions, then implantation and other isotopic measurements. This I just show you that, unlike the positive ions, which electron impact ionization offers you the universal means of producing any ion from across the periodic table, the converse is not true. That means for negative ions, you do need, the recipes and specific, methodologies to generate negative ions across the periodic table. And about 70% of the periodic table we have already mapped, except the inert gases, where anyway, intrinsically, they don't have electron affinity. And so if you look at here, we are right now, we have seen the lanthanide, actinides, rarer, all kind of things have been already covered with this facility. And there are dedicated sources functional there. This is one of the source which has a 36 sample remote control operated source. And this is already running around the clock for various applications like accelerator mass spectrometry. And because it reduces the downtime drastically, I just show you the characteristic performance of the system. So this, if you see, you don't have to spend time for changing from one beam to another beam. So this you can do without disrupting the operation from the control console. And also this is, as I said, that because of the better emittance here, you get higher transmission factor through the electron and Linac booster. Here is another development where we have developed this 1 giga sample, card where you have this kind of facility where the time resolution was measured to 1.4 nanosecond, and this has been also utilized during the nuclear physics experiment at Peloton. So this is in-house development. Then I go to the application-oriented activities. Now, as I said, that we have been augmenting depending on the user requirement, and I may cover some of them. AMS is one activity which we have been, the chlorine was very well established, and it is published also for doing the southern water, mapping for groundwater chlorine detection. It has its departmental, let's say, interest. But these measurements were then finally extended to iodine-129 successfully. And also we have extended these measurements to do some basic research for unambiguous identification of superhalogen anions using this technique at Peloton. Here I just show you the typical spectra where iodine-129 is measured in the standard, where you already know the ratio from the dated sample. And also your blank, that means the machine background, that how much the detection sensitivity finally you achieve. So this I show in the next slide. This is what we have achieved so far. 6 into -13 kind of detection sensitivity for iodine-129 has been already, let's say, obtained at the facility. Here I just show you that the superhalogen ions are basically the anions which are having higher, positive electron affinity than the even halogens, and they are prolifically generated, possess very, sufficient, rather I will say more than 50 microsecond lifetime, which are good enough to do the acceleration, and also offers significant magnitude of isotope suppression, which is very crucial for doing AMS measurement. And this technique is a novel method we have developed here for the first time to generate those anions. And as you know, the affinity, higher the affinity, lower the work function, you get highest formation probability of negative ions. And this typically shows that if I do secondary ion mass spectrometry, your ratio of, let's say, if I take SF6 minus 32 mass and 34 mass, it will be 4.1%. But actually, they do not form. That means there are certain other interfering, isobaric and molecular interferences that might be mimicking. So you will not be sure whether it is SFN and is equal to 1 to 6 or something else is interfering. For that, we have used again the AMS technique. And you can see I'm showing typically for SF6 minus injection from the accelerator. Then finally, you get a 6-fold coincidence measurement showing you all the 6 molecules and identifying it very unambiguously. These measurements are further extended to even tantalum.
And I show you, this is the from the second DAE mass spectra. But here, I will show you in the next where the AMS measurements have been done. So you see all the, so particularly for TaO6, you can see the 6-fold coincidence, verifying, unambiguously. Here I show you the other applications where they say the facility has been upgraded at 6-meter level of the pelletron. Pelletron is a 40-meter height, let's say, vertical tandem machine. Here you can generate using the proton beam at much higher current because of the shielding thickness given. It's a tapered shielding as you go up. So higher the shielding available at the base, so you are able to have even second neutron yield actually. And this is used for nuclear data measurements. And there are other applications which are radiological and all I'm not covering here, just to show you that the facility will keep on customizing depending on the user requirement. Here I show another applications where the proton beam is taken in the air. And this is very, what you call extensively utilized by NABTD to do induced mutation studies on rice, wheat, and very recently groundnut. And they have got good result in terms of higher yield as well as herbicide resistance. So that way it is a very already going on work. And then finally, we also try to now extend it to lithium and other ions, heavier ions, which cannot be as of now taken into air because of the energy. But this can be done when we go to the LINAC booster, there the energies are higher. So these are the measurements currently planned. And again, the idea is to have some kind of, societal application where people have tried gamma, electron, all kind of radiations, but heavy ion has got its own, merits and, advantages. That's why this route is being followed very, extensively by in collaboration with the NABTT. There is another technique which is called thin layer activation analysis, where the wear and corrosion rate, if I have, let's say, some internal, some very small component in a highly complex system, say reactor or any, huge, let's say, car or any machinery, and you would like to know whether the system, without disassembling or opening the system, can I know whether the system has undergone wear and tear or the life is over? So for that, this technique is used, where you are already having a marker. If it is a metal thing and if iron is around, you can have a proton iron, then you can fold cobalt there, 56 with half-life of around 77 days. And you can see as the wear and tear of the component goes on, the activity goes down. So you can reconstruct that what kind of life is still at and take a decision rather than, disassembling the system. There is another, application of thin layer activation analysis where IGCAR Kalpakam has, they're looking where has the, let's say, flow rate erosion. That means because of high, let's say, velocity flow of fluid, you are having erosion at the corners particularly. So this was also mapped and they could successfully do this, and this work is also published. It's a good work in satisfying the requirement. Here I show you another application using pelleton where we are having a track etch method. That means you are using heavy ions to make pores of 1 nanometer, which can be etched by chemical solution, appropriate solution, and you can have this kind of pores up to 1 micron size. And there we have got these kind of pores by various ion beams at different energies. They were all very well optimized that what should be the characteristics of the beam for which you would like to have the pores. And they are used by various, let's say, agencies like RMC and some universities. And recently in BRC also, the separation of helium and nitrogen were done, and the selectivity was close to the theoretical limit, 90%. And I now move on to the status of ECA. Can you please tell me how many minutes do I have?
More minutes.
10 minutes. So I can change the gear to little slow mode. So this is something I would like to spend a little more time. The pelletron as such provides you beam 5 MeV per nucleon to carry out the nuclear physics search. Unless you overcome the Coulombian barrier, the reaction is, highly improbable. So to do that, right now pelleton plus LINAC booster exists, and the total energy is basically 14 million volt into Q+1 and the further boosting by 8.6 MeV per charge state, which is coming from the pelleton. And the currents are around 1 to 5 particle nm. Now, this has a limitation. That means even if the pelleton runs at 14 million volt, you cannot get more than around, let's say, 80 mass accelerated through LINAC. So if you have to overcome this and get heavier masses accelerated through LINAC, you have to go for a ECR plus LINAC alternate injector. Now, because of the space constraint, this project moved to now, let's say, Hall 9, and finally, it has to go to Vizag, as Director Bach has, given a lot of support for the funding and allocating the space right here as well as at Vizag, which I may mention later. So this is showing you the energy per nucleon, which is required to carry out, useful nuclear reactions, and therefore you need a ECR-based heavy ion accelerator. Here it shows little comparison. There's a pelletron gives you a singly charged negative ion, while ECR can provide you multiply charged positive ions, right from proton to uranium. But proton is not it's a singly charged system in any case. And in negative ion source, you have a limitation because the affinities are less, they are lower than that, and your overall intrinsic yields are quite less. And inert gases anyway you can't produce. While here you can have, all the way across the periodic table. And the currents in here it's limited up to 10 to 5 PNA. Here you can go up to 100 PNA. And in fact, for oxygen, it is 1 electrical milliampere. In the same way, if you look at the physics aspect, you can do some of the things like inverse kinematics for light ion beams for light, but here you can do using heavier ion beams on the light target. And super heavy ion nuclears, let's say nuclear research is not feasible here. Here there is a, good possibility. And also one can have a secondary radioactive ion beam possibility here because high current you can do in-flight kind of. So this here shows the schematic, the ECR source, which is already have here, and we have been running it of late. Now we are going to relocate it to the Hall 9 BRC, where right now the system is disassembled, and we are in the process of finding some kind of, shielding for it to curb the X-rays, and finally it will be recommissioned. And then the mass and charge selected beam goes to the RFQ. Here also prototype RFQ, one of the, let's say 50 centimeter model is made. And this is with the improvised quality factor, as well as, you have the right resonant frequency very close to that. And this requires right now a lot of other work to do the beam test and then qualify it before we go to a 4.8 meter final RFQ. And followed by, we have two superconductive niobium structure. That means 5% and 7% beta. And that beta means the, velocity of the ion with respect to velocity of light. And this is required to again match the velocity acceptance of the LINAC. And this is so here I would like to show you this anyways here. Here we have made some progress. And the efforts which are re-energized currently at BRC as a collaborative pursuit, I will be showing you. This is typically the ECR, so superconducting ECR system. And these are the typical charge state. You can get up to oxygen plus 8 fully stripped, argon, you can go up to 15 plus, xenon up to plus 20. And these emittances are well below the acceptance of the downstream elements. Here this shows the specifications. It's a very powerful source, and it can go up to 1.7 kilowatt, kind of RF power. And the maximum extraction is 30 kV. And these are so you have a axial field, which is, let's say, superconducting, and then you have a multipole field, radial field, which is permanent magnet. It's a multi-layer permanent magnet system. And we have got very, high level of distinctive characteristics, and the intensities are far higher than any existing commercial source as of now. And it doesn't use any cryogen. It's just a 1 watt cryo compressor, and also have all the, modern design concepts like RF DC biasing. And you can get the feed in any form, gaseous, liquid, solid, all kind of things, high melting point, low melting point, all kind of ion source feed can be, coupled with the ECR source system. And also there is a possibility of doing charge breeding. So when it moves to, let's say, Vizag, where in the plenary talk, actually, it was covered that you will have KEB RIB beam using electron driver as well as proton driver. But those KEB beam has to be then charge bred. That means you have to multiply the charge state from singly part. Then that is the job where ECR comes into the picture. And this has that facility. And typically for lead, I'm showing here, you can go even up to 31 plus, that 32 plus, the yield goes down. So, but maximum 34 plus is already produced with this source system. And uranium case, we have seen up to 34 plus. And this is the one typical experiment which was done at ECR using the ECR source when it was in Fortia. before relocating the source to hall 9. And this was very successful, and this work is also appreciated internationally, and it is also published. And this shows the elaborate setup where low energy GD fusion was done using ECR source standalone by the NPD team. Then I go to the next element, which is room temperature superconducting, let's say RFQ, room temperature radio frequency quadrupole. The prototype, we have measured the, if you look at the simulated and the measured values, the full electromagnetic design and beam dynamics has been done. And we see very close to the simulated and measured values, the quality factor also. And this system is now to be beam tested before we go to 4.8 meter kind of heavy RFQ. So far, you have heard about proton RFQ and all, but this is having its own, let's say, challenges. And here I show you the next very important and more challenging, let's say, element, the superconducting niobium resonator. But as the design, this is a collaborative work with TIFR and EMADE division BARC, and CDM is doing the fabrication for the prototypes. So to start with, we have done with the SS, which is requirement to understand the machining tolerances and all, because niobium is an expensive metal, you can't straight away go for niobium. So therefore, this process is started. As of now, all SS components for one quarter wave resonator has been fabricated at CDM. Currently, we are trying to do the electron beam welding, and that's where the challenge lies. And in parallel, we have given a purchase order to work order to OFSC Copper for VK Industries Mumbai, it is here in Goregaon. They are also parallelly doing OFSC Copper fabrication because they don't have electron beam welding facility. So once the fabrication is done, it has to be transported back to CDM BRC, where by that time they should also, their learning curve should at least complete so that the copper can be tried here. Now, this shows the typical SS component. This is the typical design for the niobium quarter wave resonator, which we would like to have. And then right now, this system is designed for, replacing in TIFR first module. And the physics design is done by TIFR. And then from there, if you look at the similar thing, if you go to SS, right now we are trying to see how to really, weld those systems. Although the central conductor, the outer, let's say, coupling ports, and using ball pulling, all these things are already completed. And you see the central donut. Now these things have to be welded, and this is the beam in and beam out. So these are the challenges are now finally in the electron beam welding without losing the overall tolerances. This is what is currently under trial at CDM BRC. And I now come to the conclusion part. So if you look at the developmental activities implemented at Peloton have, not only enhanced the overall performance and uptime, but it has been, sustained. Always you will see the uptime more than 80% all along for more than 3 decades it is running. And we have also augmented various application-oriented programs driven by the users within DAE and outside DAE. And that has also resulted in enhancing the utilization capability of the machine. And to go further, because finally the idea is to go to heavier and heavier beams and much higher, let's say, intensities. For that, you need an ECR-based, heavy ion accelerator system, where the prototype heavy ion RFQ has been improvised, and right now it has to be, finally we have to go to beam testing when the ECR get recommissioned. We are also looking for some place where we can do it in parallel for the QIM, which is required to accelerate through prototype RFQ, so see the energy gain. And also, as I said, that as a first stage towards the quarter wave resonator for niobium, we have done the SS components manufacturing or fabrication at CDM. However, the challenges are being faced here, and multiple attempts are being made to resolve those technical issues. Our team is continuously day-to-day basis meeting them. And this phase, once we complete the learning curve, that will be helping us to do the OFSC copper welding, followed by the niobium cavity, let's say, welding and fabrication. Now, if you look at here, the whole scenario is, although we make the cavity, but where to house? The ECR heavy ion accelerator cannot be housed in BRC because the hall 9 area is 30 meter by 30 meter with us. So only pre-project R&D, which is what is going on, is only feasible there. Finally, the expertise in niobium resonator fabrication and the RFQ gained and the technology developed would be acting as a template for, setting up a greenfield facility at Vizag. That is the overall ultimate game. And with this, I thank the, audience. And if there is a question, we're happy to.
Thank you, Dr. Gupta ji, for giving informative talk on application of pelletron in different areas. I'm also one of the user of pelletron. We have used for the proton radiation of the solar cells. The floor is open to the for questions from the audience. Any questions? Token of appreciation, there will be some memento
Okay.
will be given.
Thank you.
Welcome Dr. Manjari Pandey for the next talk on overview of recent RF technologies in application. Dr. Manjari Pandey. Manjari Pandey is head radio frequency system section, accelerator control division, BRC. She is from 33rd batch of BRC training school. She has designed, developed, and integrated overall and standalone high-power RF system, inclusive of their transmission lines, both in pulse and CW modes, and RF electronics for proton accelerators like LEHIPA, Duratron, the RFQ accelerator, heavy ion accelerator, and RF ion source of 12 MeV neutron generator. She is sub-project coordinator for design and development of 325 MHz solid-state RF power systems under international collaboration is Indian Institute of Institutes and Fermilab collaboration. She is a recipient of the 7 DAE Group Achievement Awards, a Science and Technological Excellence Award, and SN Sheshadri Award for Instrumentation. Welcome, Dr. Manjari Pandey.
Manjari.
Show them how. People on the board.
Good evening. I'm Manjari Pandey from BARC. The title of my talk will be overview of recent RF technologies and accelerators. At the outset, I first like to thank the organizers for giving me the opportunity to present on my work via this invited talk. So outline of my
Little bit louder or mic you should add.
The outline of my talk, so it's okay? Outline of my talk will be, I Briefly, we'll be explaining about the accelerator technologies, mostly RF technologies. But since RF technologies is a very wide spectrum of technologies, I will be touching upon very few, mostly related to RF power and all. Then the technological advances, which is recently or till now has been doing, and RF systems for accelerators, which we have developed in BARC. Here I would like to note, and I'm happy to inform that during the keynote address, some part of our work has already been shown, and that has made my work easier because you could relate it to the keynote address given by Dr. Krishna Gopal on the opening ceremony. I'll be going in detail of those things, how it has been designed, developed, and integrated with the RF accelerators. So the important points will be seen. If you see in any RF accelerator, journey of RF energy starts from very low energy, that is a low level RF signal coming from LLRF, called LLRF, going through the high power RF systems where it is amplified in terms of power, transported from there to the accelerator for from the source to destination, and thereafter the RF power is integrated with the accelerator for generating the RF field and thereby accelerating the ion or electron beam. The loop is completed by taking the RF samples from the cavities and given back to low level RF for amplitude, frequency, and phase stabilization. Thereby, a stable RF voltage is presented by the RF system to the RF cavities of the RF structures. This way, the whole integrated overall RF system plays a very important role in any RF accelerator, and hence the RF technology, importance of the RF technology in such fields. Now, with the same theme going ahead, if you see the sort of a roadmap or you see the future technologies which is needed in RF accelerators are of plenty. There are two important things, in fact, three important things. One is the high gradient RF structures or high Q RF structures and the RF sources or the RF systems. These are the new technologies or the recent advances are being done to advance in such things. Then the question comes, why do we need these recent or future advanced accelerators? Because we need an improved and upgraded technology to improve their performance in terms of RF, in terms of accelerator. Now, if you see the performance in these are high energy accelerators are highly complex machines. So it does have an impact on its cost. And hence, by improvement in the performance and upgrading the technology, we reduce the cost by order of magnitude. Now, this requires a highly efficient sources of megawatt class. Now, radio frequency power. Let me tell you one thumb rule. An improvement of 1% in efficiency, of course, I'm talking about high energy accelerators, an improvement of 1% in efficiency amounts to reduction in electrical input power by 1 megawatt or more. So you can obviously see that why the importance of efficiency of any RF structure or accelerating cavity or RF systems is very important. In RF accelerator terminology, it is called wall plug efficiency. So the electrical power generated from the mains AC to the beam which is on the target. So the whole journey of this electrical power has to be very efficient, and at the same time, this is achievable by using a high Q and high gradient accelerators. So advances in all these terminologies or all these accelerators is very important part for the future and advanced accelerators. So what you need is a new methodologies. So new technology in structures with low cost, then discrete architectures of the RF sources or RF systems, distributed architectures, and energy recovering techniques. The energy recovering techniques are both in LINAC technology as well as in the devices technology. Nowadays is a very important part of energy, important part of technological advances. though I won't go much in detail for energy recovery techniques. The new technologies which are responsible for all these new methodologies is the first and very important thing is high efficiency vacuum-based devices. Because when you go into megawatt operation, there is no alternative to vacuum sealed devices. Earlier, the conventional sources were tetrodes, klystrons. They were having very less efficiency combined together. So the invention of multi-beam klystrons with depressed collectors, or the very, very recent, as recent as last year, the klystrons under HICA, that is high energy international klystron activity collaboration. It is a multidisciplinary and multi-lab across all the countries that activity is going on, and efficiency as high as 80% in S-band technology has already been achieved. The inductive output tube in the kilowatt regime, then phase locking injection magnetron devices. These are some of the few examples of the very, very recent new technologies which are being used or which are being actively pursued for the advancement. The next game changer is the solid state amplifiers, basically up to 100 to 200 kilowatt regime. I will be talking much in detail in the later slides. And low-level radio frequency control system, that is the LLRF control system, also is a very important and complex system which is necessary for accelerating. Now, all this performance improvement will greatly benefit the performance of the overall accelerator, and in terms of their high gradient and high Q technology also. So the technological maturity has to be achieved in all such things. Next comes the RF transmission lines. Now, RF transmission lines, although much work has already been done and overall technical maturity has already been achieved, nonetheless, the importance of those RF transmission lines is always there. RF transmission line is the transport line which transmits the high average power from the source, that is the RF power generating source, up to the accelerator in the kilowatt or megawatt range per component. So invariably, low insertion loss with high reliability of each and every component is required. Some of the components of transmission line need to transmit machines kilowatt to megawatt. Sometimes they are under dry air to withstand the high voltage breakdown, arcing, especially in the bends. And RF window and RF coupler, these are the very two important and very critical components of RF transmission lines, are always in the good vacuum. And without vacuum, their RF performance degrades. So in this such high power regime, the proper selection of materials, surface treatments like coating, surface texturing to suppress the multipacting. When you go into the high power region, since there are many bends and surface impurities and absence of good vacuum or dry air, the electron avalanche process starts and it gives rise to the multipacting, giving rise to the irreversible damage to the transmission line components. Obviously, in some part of the components, field emission, very RF breakdown, all this needs much more attention, and each of these points are good points to study in detail. Now, ultra-high vacuum in high-power devices, as I said earlier, in like klystron, tetrodes are also there, which are used in the high-power region. The next RF technology is the superconducting RF structures. Obviously, I won't go in much in detail, but this needs much attention. Recently, or as on now, the good RF superconducting structures with high quality factor and high gradient are being achieved. This technology is fastly progressing. So what it needs is the investigation of physics of its surface resistance and magnetic flux losses, exploring doping materials, new doping materials to reduce the surface resistance, new investigation into the new materials, new structural shapes, Then exploring advanced topologies and innovative manufacturing methods are some of the requirements, and the world labs are progressing very fast on this. So in totality, the development of these innovative and improved technologies that work at RF frequencies will always ensure the improved performance and the cost for all the future accelerators and all the upgrades thereafter. Now, I'll be specifically going into some of the RF technologies in detail. For the first one in this is the high efficiency RF or microwave power systems. Now, mainly in any high power RF systems, the efficiency of the whole system is mainly dictated by its power generation device. So vacuum-based or vacuum-sealed devices like klystron tetrodes were used in the kilowatt to megawatt regime earlier. Nowadays, but the conventional klystrons were having a very low efficiency. Though the device was having almost 60 to 62% of efficiency, if you take the paraphernalia, all the associated high voltage, low voltage supplies and all other RF and DC and AC technologies, combined it together, RF system efficiency was going down to as low as 35 to 45%. And this leads to relatively overall performance, leads to low performance of the RF system and the accelerator. So improvement in efficiency and reliability reduces the efforts associated with high voltages. One of the technology which is actively being pursued is multi-beam klystron, which can increase the net efficiency while operating at moderate high beam voltage. The conventional klystrons operate at 80 kV, 90 kV, whereas these can go up to 40 to 50 kV. So the permeance of the beam is improved, and the efficiency of the multi-beam klystron, if it is clubbed with a depressed collector, which is also a new technology in which there is the energy recovery techniques are used, that will be very highly useful technology and it will improve the efficiency. The efforts on high efficiency international klystron collaboration, activity collaboration using innovative methods of electron bunching. So basically the electron bunching process called BAC, they are improving and using it into the cavities which are there inside the klystron, which they are also RF cavities. They are just doing the opposite job of accelerator. They convert RF they convert the electron beam into the RF energy, and that bunching process is being improved. And as of now or presently, as per the literature survey, it says that the efficiency of 80% is achieved in S-band klystrons, and hopefully in future this technology or this invention will lead to the much more at a lower frequencies also and will have a drastic efficiency improvement. Use of linear as a circuit. Klystron mostly is operated in a saturation mode. So in saturation, there is a non-linearity introduced. Now using the linear as a circuit, we can address these non-linearity issues. So in conclusion, all these efforts of efficiency improvement will lead to the overall efficiency, high efficiency, less electricity consumption, and less operating cost, and directly improving the overall accelerator operation or the performance. Here again, wall plug efficiency of the accelerator, this will particularly contribute very high into the wall plug efficiency. Now coming back to these are the technologies in RF technologies advancements. Now, how do we implement in our own programs? Again, this LABA program was mentioned in the keynote address. So in this LABA, there are 3 accelerators, 3 MeV RFQ, 10 MeV DTL, that is a drift tube line hack, 20 MeV drift tube line hack. Now, all these 3 RF cavities are being driven by 1 megawatt 352 megahertz Klystron RF system. Just to give an introduction, each of these Klystron RF system comprises of a solid state driver, a Klystron tube, associated high voltage and low voltage and even high current bias supplies, an interlock protection system including a very fast protections of which covers the range of microseconds, and a waveguide which is a WR2300 based RF transmission line. Now all these components are capable of handling 1 megawatt CW power, that is a continuous wave power. For the 3 MeV RFQ, since it has been achieved a few years back, so I won't be going in detail of all this. So first, just to give a status that the first Klystron system was commissioned and RF power of around 500 kilowatt was fed across the 2 ports of RFQ via waveguide transmission line. And 3 MeV proton beam was achieved, and thereafter a number of experiments were carried out with the 3 MeV beam. Recently, 10 MeV beam detail commissioning is in full progress. For that, a second Klystron system has been tested and commissioned initially on the RF load up to 800 kilowatt power. The waveguide line carrying this RF power has been also commissioned and tested to feed the power across 2 ports of 6.5 MeV DTL, because the 10 MeV DTL is in 4 tanks. So the first 2 tanks is commissioned at the moment, are in line along with the ion source RFQ and 6.5 MeV DTL. And this will be powering that 2 tanks of DTL to achieve 6.5 MeV of proton energy. So this is the photograph of this is the second Klystron. You can see here the Klystron, which is a Thales-MAC TH2089. And these are the high voltage. With this, there is a regulated high voltage power supply, which is on the ground floor. The Klystron is in the basement, Klystron gallery. The RH VPS, that is a regulated high voltage power supply, is a very highly regulated, almost less than 0.3%, the ripple of 0.1%. This using PWM technology, IPR and ECL combinedly has commissioned this, and the high voltage from the regulated high voltage supply comes into the Klystron gallery. Here there are 2 again high voltage systems which are floating at 100 kV, the red one and this red and yellow one. One is a high voltage interface, also accommodating the very huge crowbar operating at 100 kV. And there is an anode supply. Now these all bias supply goes into the electron gun of the Klystron. And this is the Klystron cavities are inside these electromagnets. And the output of the Klystron is taken out from this RF window. And there is a small waveguide transmission line, which is that consists of harmonic filter, diaxial coupler, and circulator. And then thereafter, a waveguide bend and a taper going into the LINAC gallery. Now, all this is a 1 megawatt capacity and 2 megawatt DC supply, DC power for this. Along with this Klystron, there is a controller-based interlock and protection system, which is handling around 80 plus analog, digital, optical field signals, as long as also RF signals. Also, there are some fast protections, especially for crowbar event under the event of arcing. And it protects the Klystron around in 2 microsecond time under the event of any arcing, short circuit, or very high current rise. Then there is a circulator. For that, you need a tuning of this ferrite-based device, and you have almost 8 low voltage and high voltage bias supplies. All these are low voltage supplies are housed here, and then there is a controller-based protection system which we have developed. And this is again the Klystron, and you can see the transmission line going from the Klystron side. What you are seeing is the waveguide layout for 10 MeV DTL. These are the simulated structure layout. This is a 10 MeV DTL with 4 tanks. So at the moment, these first 2 tanks have been commissioned and are in line with earlier accelerator of RFQ. So the waveguide line starts from here. From behind this is a klystron gallery. So the RF power from the klystron gallery comes from the klystron gallery and gets divided into 1:4 by this WR2300 waveguide transmission line, again carrying capacities of 1 megawatt maximum, 1 megawatt average. And it consists of straight sections, bends, magic tees, directional couplers. These are the terminating loads. And it transfers the RF power via waveguide transmission line. Then there is a RF window, and then there is a RF coupler, which couples the
having
RF.
5 minutes.
5 minutes?
5 minutes.
Oh, okay, I'll adjust the speed.
Speed up the
Yeah, I'll skip some. Right. And this is the waveguide transmission line in klystron gallery. And this is the actual detail view of the transmission line, waveguide transmission line for 6.5 MeV detail. This is the, again, exploded view, and this is the vacuum connections for the waveguide window, and thereafter the coupler part of it. This all have been installed, commissioned, and RF conditioning has already taken place. The second technology which I would like to emphasize is the solid-state RF systems, which is a game changer in today's world. These are the discrete structures which employ modular and low voltage, high efficiency amplifier system with low loss power combining technology. And up to kilowatt regime, this is a perfect candidate for the kilowatt regime. It allows a solid-state amplifier per cavity, because if you use a klystron, there's a single device-based transmission line. Here you can use one amplifier, which simplifies the whole architecture. It simplifies the RF distribution line. And the most important advantage of this is it's a fault tolerant and hot swappable. That is, when one device, since it is a combining technology of many RF devices has been used, even if one of the devices shut down or tripped, still RF power availability is ensured, which is not the case with the vacuum tube devices. And hence solid-state devices are fastly progressing. Breakthroughs in material developments have led to the improved efficiency of solid-state devices like MOSFETs in terms of power as well as efficiency. And hence, the pace of progress for solid-state amplifier is very fast. Using such MOSFETs, again, this had a mention in the keynote address under US DOE labs and India DAE labs. There is a mutual agreement, collaboration agreement, and which is called Indian Institute of Fermilab Collaboration, and under which we are supposed to exchange and develop the technologies which are mutually benefit for both the countries. Three accelerators, one at Fermilab and two in India will be developed. So for this, there is an in-kind collaboration from our side, and based on our solid-state RF technology, the IPR, or that is intellectual property right of this solid-state RF technology, belongs to Atomic Energy and hence India. So 9 such amplifiers were developed based on the BRC technology, and 8 of such solid-state amplifiers were coupled to the single-spoke resonator of proton improvement plan injector test facility, in short PIP2IT, to achieve 17 MeV beam energy. Now also we have already developed, which I have not shown it here, next phase as a 325 20 kilowatt, and RRCAT has developed 650 megahertz. So all these technology developments which are at par with international standards, because these amplifiers have been validated and standardized as per international standards and well accepted and commissioned, deployed at Fermilab. So this same technology, same advanced RF technology will be used for Indian accelerators, both at RRCAT and at Vizag. This is the vacuum now. Coming back to the vacuum. The vacuum is a very important ingredient of some of the components of whole integrated RF system. Especially klystron and tetros, as I said earlier, are the vacuum seal devices, and we keep maintaining the vacuum of that. Waveguide components like RF windows and couplers are always critical for under high power operation, and vacuum always adds to the performance of those operations. Now coming to the exact challenges which are faced in couplers and windows is the multipackaging and RF breakdown and arcing. Especially for multipackaging nowadays there is a terminology called secondary electron emission yield (SEY), which to compensate for this we have to apply low SEY surface coating like titanium nitride, which suppresses the electron avalanches and thereby multipackaging is avoided. Also, the recent advances in ceramic technology, like ability to provide the bulk DC conductivity without increasing the RF losses, would be extremely useful in these areas, especially in RF couplers, coaxial RF couplers in superconducting cavities. RF control, as I said earlier, low-level RF is also a very, very important technology which is used in this. Because of recent very strong advances or technological performances in superconducting cavities, attaining very high quality factor of the order of 10 raised to 10 and unloaded and in loaded up to 10 raised to 7 and hence the very narrow cavity resonances. The challenges imposed on the LLRF for stringent amplitude and phase stability of RF field is very important. Let me tell you one example. The instability in the amplitude of the order of 0.01 or 0.0 phase instability of 0.01 degree imposes a...
Madam, your time is up.
Just 2 minutes.
Shortage of time.
Yeah, just
3 more talks.
2 minutes. Give rise to the very unstable RF power and hence the role of LLRF along with hybrid algorithms, very fast components, very fast and very speed components with EMI, EMC hardened components. These are the challenges which they are facing and they have to work under different modes of RF conditioning, power ramping and normal operation. So the stringent RF stability requirements, precision measurements and control of RF compensation against the detuning by microphonics and Lorentz force. The role of LLRF is very important. Now, I will just mention and skip this transparency RF accelerating structures. Again, in the fabrication and development of RF structures, all these parameters are very important, like cavity design, cavity fabrication, use of fast tuners for microphonic control, higher order mode suppressors, surface processing methods. So all the new developments are always augment with the performance of the. So in conclusion, RF technologies for both normal conducting and superconducting RF is actually a very large spectrum of technologies. So recent advances in high Q and high gradient LINAC and associated technologies are very promising. RF integrated system starting from RF signal to RF structure is a very fast and emerging technique with many technological leaps happening in these areas. And they are discussed here, whereas many of the other technologies remains untouched. A very promising and interesting field of RF technology is very useful for attending a super performance of the high gradient, high Q accelerators in future. Thank you.
Any questions? There will be memento given to you as a token of appreciation.
Thanks.
Next will be oral contributory papers. Next presentation will be by Dr. Biju K. on radiation shielding aspects of 30 MeV electron linear accelerator facility. Dr. Biju Keshav Kumar joined the Baba Atomic Research Center, Mumbai in 1992. She is currently working in Health Physics Division, VRC. Her major area of research includes accelerator radiation safety, neutron and photon dosimetry, and Monte Carlo simulations. She has about 100 publications in peer-reviewed journals and conferences. I welcome Dr. Biju to give a talk. Only 10 minutes will be there and 2 minutes for the questions. It's a PDF, you can open. Okay, do it. Thank you, ma'am, for the kind introduction. And a good evening to all of you. And I would also like to thank the organizers of Vstaa for giving me this opportunity to present a paper here. And I'll be presenting a paper on radiation shielding aspects of a 30 MeV electron linear accelerator facility. And outline of my talk is going to be this way, that I'll be introducing some scientific basis for the shielding philosophy, and what are the crucial parameters that has to be looked into or maybe identified and quantified for shielding calculation, effective shielding calculation, and also a typical methodology that has been followed in shielding calculations. And nevertheless, that I'll be presenting some of the results which for the single energy point, that is 30 MeV electrons in this presentation. And whenever we think of a radiation generating device, see, first and foremost thing that we need to see is how much is the radiation that the device is producing. And the second thing that we look for into, like, that has to be shielded definitely, and how far it has to be shielded. What should be the permissible levels that should be outside the shielding. So coming back to electrons, these electrons that can be, as you know, high energy electrons can be stopped by few centimeters of material like tungsten or shield, whereas this electrons, when they are getting absorbed in the material, it loses its energy by two methods. That is, one is collision loss, in which the electrons, they lose its energy by ionization and excitation of the atoms. Whereas the second process is the radiative loss, which produces a Bremsstrahlung radiation. That is much more penetrating radiation than the incident or initial radiation. So this part, that radiative loss part, is a major concern from the radiation protection point of view. So that is what I would like to discuss about this figure. See, you can see in the x-axis it is energy, and y-axis it is called stopping power of the medium, in which we have two curves. One is red, and then other one is green one. Here, you can always say that red one is a collision loss, and probably we can say it is the probability of loss of energy by collision, and the other one is the probability of loss of energy by radiation emission. And you can see as the energy of the electrons goes higher and higher, the collision loss decreases. And this collision loss, I was already mentioning that it's only an heating effect, and which a shielding person need not worry. But you can see as energy goes high, this radiative loss picks it up, and it dominates over the collision loss. And this is what is important in tungsten. This number is called, we call it as a critical energy, and it is around 10 MeV, whereas in the water that comes out to be 100 MeV.
And another radiation that has been produced in electron accelerators are the neutrons, and these neutrons are produced by photons, high energy photons, and we call it as photoneutrons, and they are produced by three different mechanisms, 3 to 4, that is giant dipole resonance or GDR neutrons, quasi-neutron, delta resonance, and intranuclear cascade. And you can see this cross-section which have given in this figure. In tungsten, you can definitely see it as a threshold reaction, and the neutrons are produced in tungsten only after an energy of 7 MeV. And in aluminum, you can see this is for aluminum. Aluminum, it is threshold is around 15 MeV. So, so in principle, we have a philosophy that once the electron energy is going above 10 MeV, only we think of neutrons actually in the to be considered in the shielding. See here, another thing is that typical shielding assessment, and this shield what to say, attenuation of radiation by shield can be expressed by an analytical equation, that is that h d theta is a radiation dose after the shield thickness of d, and h theta is the unshielded dose, that is without shield how much is the output or source term what we call, and it has been reduced by the inverse square of the distance, square of the distances, and there is another exponential term which gives you the attenuation of dose by the shield. And here you can say d theta is something like that, what is the actual depth that has been traversed by the beam in the shield. And this exponential term again can be simplified by two things. That is, one is called lambda t, that is called TVL or 10th value layer, which reduces the intensity by a factor of 10. And also there is a lambda h, which is called half value layer, which reduces the intensity by half. And these are the typical TVL values, that is particularly for 30 MeV Bremslang. In concrete, iron, lead, and HTP, also the neutron TVL values. And now we can just come back to that, is that H theta, whatever is told here is the source term, which is very crucial, and it has to be very accurately measured. And this is highly angular and energy dependent too. So these are generally being calculated or estimated by Monte Carlo methods. And here also, we also have done some Monte Carlo simulations for 30 MeV electrons, and that has been done using a generalized code called FLUCA. And FLUCA is nothing but it's a radiation transport code. In radiation transport code, Monte Carlo based radiation transport is nothing but it is mimicking mathematically the actual transport through the matter. Okay, radiation transport through the matter, and takes care of all interactions and production of secondaries, etc., all energy absorptions, everything. So here we have simulated a 30 MeV electron beam falling on a thick target, tungsten target, and we have scored the angular distribution as well as energy distribution of the secondary radiation that has been generated. Again, see, when coming to the results, and the first figure, that is, this is the photon energy distribution. You can see in x-axis it is energy of the photon, and y-axis is the differential photon fluence or Bremslang fluence. You can see it is in the 0 degree, 90 degree, 180 degree, and there is a large energy variations.
Madam, 2 more minutes to complete.
I would like to conclude that it is that energy that is in the forward direction is much higher, and in the lateral direction is lower. And this is the energy distribution of the photoneutrons produced by 30 MeV electrons. And the third figure gives us gives you the angular distribution of the intensity, that is energy integrated intensity. And you can see Bremslang is highly anisotropic, and there is a dip in the 90 degree, and whereas the photoneutrons are almost isotropic. And here the fourth set of calculations that we have done, it is for the integrated yield or source terms obtained by the FLUCA simulations. And here we have forward Bremslang, sideward Bremslang, and also photoneutron yield. And this has been compared with standard literature, one of the standard literature that is called NCRP 144 report, which is actually the data is of 1990. So there is a lot of debate happens about the results that is too generic numbers, and then it is very old data. But this study compares quite well with these results, and our data is around 20 to 30% lower comparing to the this literature value. Another result, that is computer shielding thickness, concrete wall thicknesses for the 30 MeV electron accelerator, and we can see that for a unit power of 30 MeV electron accelerator, the front wall comes out to be in a typical calculations, like where the distances are considered as 10 meter is 365, and once you raise the power from 1 to 10, it becomes 410, and similarly the side walls are 200 to 235, and you can look at that even the photoneutrons can be shielded by even lower thicknesses like 144 to 161, and from this I would like to say, once a beam power is twice only one, you need only 15 centimeter of concrete extra, that is one half value layer, and once beam power is 10 times, there is typical typographical mistake here, beam power is 10 times, only one additional TVL is required. And also, see, once the Bremsstrahlung shielding is taken care, even the photoneutrons are also automatically shielded. And finally coming to a conclusion, see, it is found that the source term values reported in the NCRP 144 report is higher by 20 to 30% that of the estimated by the study. Use of source term values of NCRP report for shielding is preferable and conservative. It's one of the observation. Then the typical wall thickness is required to shield the Bremsstrahlung dose rate is about 400 centimeter for the front wall and 220 centimeter for the side walls. Another thing is the design of the roof. In the design of the roof, roof shielding can be thinner than the primary or secondary walls, but it should eliminate the unacceptable radiation field due to the sky shine. That is in the areas far away, including the public domains around the facility. And another safety aspect is that estimation of induced activity in air and accelerator components, and also the noxious gas generations are other radiation safety aspects to be addressed in the design stage. And also additional administrative controls such as radiation interlocks and access controls can be implemented to control the accidental exposures. And with this, I'm concluding my talk, and really thank you very much for the patient hearing. Thank you very much.
Thank you, Dr. Biju, for giving a talk on radiation shielding aspects of electron linear accelerator facility. Any questions from the audience? Okay, thank you.
Thank you very much.
Hello.
Next talk will be by Dr. Rishish Verma on utilization of 9 MeV RF LINAC as photoneutron source for neutron radiography application. Rishi Verma obtained his PhD degree in physics from Nanyang Technological University, Singapore. He is presently serving as Head Energetic Systems Development Section at Pulsed Power and Electromagnetics Division, BARC, Vaishakapatnam. Throughout career, he has been actively involved in the design and development of various types of customized pulsed power systems, which tiled energy storage, pulse compression, and switching techniques. He has authored several research papers in peer-reviewed journals and conference proceedings of international repute, having greater than 700 citations. His research interests include pulsed power and electromagnetics, dense plasma, accelerators and neutron generators. I welcome Rishi Verma to give a talk, and your time will be 12 minutes, sir.
Okay, ma'am.
Please go ahead, sir.
Ma'am, is the presentation visible to all? Hello, ma'am.
Yes, sir. Yes, sir. It's visible. You please go ahead, sir.
Shall I start now?
Yes, yes.
Okay. Yeah. Good evening to all, and thank you very much to the organizing committee of Vstaa 2022 for giving this platform to share my experience. This brief talk is basically on the utilization of 9 MeV RF LINAC as photoneutron source for radiography application that we are trying to do. And multiple divisions have been involved to do this work. Foremost is the Pulse Power Electromagnetics Division at BRC Facility Vizag, and Electron Beam Center colleagues at APPD BRC Mumbai are also thoroughly involved in it. And then we got help from Technical Physics Division for the neutron radiography part. And this LINAC, which I'll be presenting, is basically in ECL Hyderabad, and Control and Automation Division is working with us on this project. Here's the presentation outline. A very brief overview of that. I'll just be showing how the electron beam works as a neutron source, basic scheme of that, then a scheme of photoneutron generation. The basic 9 MeV RF LINAC system on which we are working. I'll just give a brief hardware overview of that, and then I'll be coming to the experimental results. I'm not detailing on that part because I'll be already covering this in my presentation. Finally, utilization of the system as a photoneutron source for neutron radiography application. Although it's a very enabling technology, but it has some inherent complications when we do the photoneutron interaction happens and we try to do a radiography with it. Finally, a progress summary and the way forward for this project. So electron beam as a neutron source, we all know, I mean, like that because of this giant dipole resonance mechanism, this is the fundamental mechanism that is responsible for the gamma N reaction to happen. And as you can see in the IAE technical report, I mean, it is well established that the beam energy of say 100 MeV or more can yield up to 10 to the power 12 for neutron per second for per kilowatt of beam. And the typical beam currents I have also shown for the reference. So, and these are the various targets. They have the different thresholds to give the gamma N reaction for the GDR mechanism to dominate. Here is the basic scheme of neutron generation. We followed actually a two-part scheme in which first the electron beam interacts with the gamma to produce the gamma with a high Z target, and then to produce from the gamma the neutrons, the second target is there. And the reason behind is that we have basically when we work with the 9 MeV electron beam, the typical energy is the average energy falls around 2.2 MeV or 2 MeV, and that basically yields satisfies the threshold reaction for the beryllium to happen and to give the gamma N reaction. As you can see, for the high threshold reactions also does exist, and for that the tantalum targets or the lead target and the tungsten targets they give, but the threshold energy for these reactions are pretty high, that is 8 MeV or so. So we went for the first low threshold reaction, which is for beryllium, which gives around 1.667 MeV of gamma, and the neutron production can come out of the photoneutron generation. So here's the overview of a 9 MeV RF LINAC on which we are working. This part is basically the electron gun, and here what you can see is axis coupled LINAC cavity. And from here, the RF feed comes in, which is from the klystron, which gives a peak power of about 7.5 megawatts. It's a Thales 216 klystron. Here's the basic specifications of our LINAC. 9 MeV is the peak energy. Beam current, it can cater up to 150 milliampere with a beam power of around 2 kilowatts. The pulse duration is 6 microseconds, and it can be taken up to a rep rate of 250 hertz maximum. And frequency, micro frequency, which it couples and pumps up the energy of the electrons, is 2856 from the klystron. Here is the basic hardware integration. I would just highlight the major part. The electron gun is sitting at the back of the accelerator section. And here is the axis coupling of the klystron, which is from Thales 2163, giving a 7.5 megawatt of peak power. And here comes the electron beam. A tantalum target is there, which converts the electron beam into gamma, and then the gamma interaction takes place in the beryllium target. Here is the overview of beam tube and the tantalum target that we have used for the gamma production. As you can see, this tantalum target is about 1.6 millimeter. It has thickness and it has a water cooled jacket because the heat flux that gets developed is pretty high. So that is a very intricate fabrication. But here it sits this 1.6 millimeter. What it shows in pink is basically the tantalum, and the backside is the copper wall, and the water flows in between this. Finally, basically, we are using the three types of optimum thicknesses of important materials. One is of E to gamma converter and the gamma to N converter. And then for the thermalization of the neutrons, generated neutrons, we had to use HDP of appropriate thickness. So for the E gamma converter, the candidate materials are tantalum, tungsten, lead, and molybdenum. And here you could see for the Bremsstrahlung influence per electron is maximum for the tungsten, but it is because of fabrication issues, we have taken the second next, which comes the tantalum. We have used the tantalum, it is the most efficient one, then follows up with the lead and molybdenum. And here the beryllium thickness, next I want to highlight, the optimum thickness of the beryllium target for the gamma interaction is about 6.5 centimeters. And then the neutrons that comes out of the beryllium target, the optimum thickness for this HDP is about 3 centimeters again. Here comes the photoneutron target assembly, which works in our setup. Here is the electron beam. What you're seeing on the red is basically tantalum target, a water cooled jacket in front of it, and it interfaces directly with the beryllium with a 40 millimeter thickness in between, and a 30 millimeter of HDP interfaces given in between to thermalize the neutrons. And here is our basically the opening which comes to the which forms a neutron beam for the radiography application. This is the installation of a neutron target assembly. Here comes the image plane of the radiography, and this lead shield, what it covers is basically the interface of the tantalum target, which interfaces with the beryllium target, and this is all the HDP on top of it to thermalize the neutrons coming out of it. So this is where the neutrons start coming, and this is basically the image plane. These are the physical dimensions of the target. Radiation shielding of the LINAC hall. I mean, as just in the previous target Madam told about, I mean, that's one of the very important aspects when we work with the LINACs. So this 9 mm RF LINAC is placed in a completely radiation shielded hall. And as you could see, there are various positions have been shown, and the maximum radiation levels, I mean, like as you can see in the top, this has about a 3 meters of thick wall. On the other side, around 2.5 meters. So this complete LINAC hall in which we do the experiments, it is radiation shielded, and we are thankful to HPD for giving us the complete measures of the doses that we get onto the different corners when we do the experiment. Finally, I would like to highlight for the 9 MeV the neutron yield of about 10 to the power 8 neutrons per second for 1 microampere of current with average Gauss energy of around 2.07 MeV. And the neutron flux which comes out average has average energy about 0.4 MeV. For this, we are getting a pretty low dose of around 0.006 millisieverts per gray, which is very much in the safe limits. For running this accelerator, we use different protection and safety interlocks. I won't go much in details of it. I would like to highlight only a few, like these arc detectors are there for in the LINAC cavity. Whenever the arc happens, that it stops. Then the clusteron door locks are there. Scram unit is very important, and a lot of heat gets generated. I mean, the heat load is pretty high in the LINAC. So these are the checks where we do for the heat loads in the different sections of our hardware setup. Finally, coming to the experimental results and measurements. Here is the temporal profile of the electron beam. As I said, I mean, that the RF pulsing that we are doing is of 6 microseconds. To corresponding to that, this is the beam current trace, which comes in. We are also measuring the forward and the reflected powers. As you can see, the reflected power is minimal over here, and initial some reflections are there, and then it gets stabilized. We also measure, I mean, like the thumb rule check, what we do when we start the LINAC is to work with a luminescent screen, whether the beam start coming. With the gamma interaction, this luminescent screen grows. And you could see it's around 2.5 microseconds is the per division. So this roughly satisfied the 6 microseconds of pulsing into this. Next comes the typical energy of the electron beam. So this we measured with the two-plate method by the charge deposition technique. And the first plate is of aluminium with a 12 millimeter thickness. The second is of 25 millimeter. And by this setup, it can measure up to 7 MeV to 12 MeV of the electron beam this can measure. And the technique is pretty simple. We just measure the ratios of the charge deposited in the form of a current pulse, as you could see. And this that gives a energy ratio. This energy ratio is about 0.85, and it confirms to about 7.8 MeV is the max beam energy what we are getting in this LINAC. And this is the setup I have shown. And next comes the scaling measure of the gamma dose, because our entire neutron scaling is a function of the gamma dose that we are getting, and which further depends on at what PRF we are running the device, how fast we are doing the repetition rate in that. So it can go up to maximum of 250 Hertz. And at 250 Hertz of peak operation, it gives a 22 gray per minute of gamma dose. So this is the measurement of the gamma dose when we run the device in the fast repetitive mode. The scaling of the gamma. Here comes the gamma energy spectrum and the angular dose measurement distribution also. My colleague Dr. Rohit Shukla and his group did extensive work on this with the help of TLD pellets, and the absorption is done by the different thicknesses basically. And there is a calcium sulfate dysprosium pellets were kept at the backside. And we found that this around 2 MeV to 2.2 MeV is the peak energy of the gamma that we are getting into this. And this is the angular dose distribution of it with separate with around a full width half maximum of around 5 degrees. The dose is max at the center. In this high gamma environment, I mean, the another changing part was that whatever neutron dose we are getting, in fact, that how to quantify that dose, because the activation is so high inside the hall that none of the conventional neutron monitors work. So we went for the passive technique. And in this, I would like to highlight that we went for the silver, EDM, and the gold were the possible candidates for us because of their half-life and the cross-section consideration. The best is, of course, gold, because it gives a single energy peak with a 2.69 half days of half-life, and it gives a single product gamma, which is about a 411.79. But the fastest measurement, if you want to do in that case, you have to go for silver or EDM, because they give 20 seconds. Yeah.
You are having 2 more minutes.
Yes, ma'am. I'll conclude that fast.
Thank you. Thank you.
Yeah. And then EDM. So we opted for silver, and here is the neutron flux measurement that we did with the silver at the aperture and as well as at the image plane. So at the aperture, we were getting around 10 to the power 6 neutrons per centimeter square per second with a per kilowatt of beam. And on the image plane, we obtained about 10 to the power 4. We also did the measurement because we were doing this photoneutron generation. So the gamma and neutrons need to be separated. And we found that we did this with a differential measurement, one detector having a cross section for neutron as well as gamma both, and another one only for gamma. As you can see, those coincident are the gammas basically, and then the later delayed pulse of around 35 microseconds of neutrons. So that's, we saw that, I mean, this neutron emission is about after the 5 microsecond delay of the gamma emission, and that's how we wanted to gate our camera in this duration. This is basically a basic of the neutron radiography. We could see the low Z thing. This is a conventional radiography. A bullet has no explosive inside, which is typically a low Z material. But when you do the neutron radiography, it is visible. So that's the advantage you get. These are the typical methods by which the neutron radiography can be done. And I will directly come to what we are doing. We are using lithium fluoride zinc sulfide screens basically because the thermal neutron cross-section means flux requirement is pretty low for that, and they give a very nice brightness for doing the neutron radiography. Lithium is the most important material in this with 940 bonds, and it gives a green light basically onto the CCD when the neutrons fall on it, and that's how the image conversion takes place. So this is a typical setup that we have implemented. The neutron beams comes from here, a scintillating screen is there, and the typical object that we can image is up to 20 centimeter by 20 centimeter with this camera, and it's a 6 megapixel gated CCD camera that has recently been obtained. We tested our camera response on the Dhruva line recently, just around 2 months back, and we got an image resolution of about 800 microns. So these are the cadmium foils basically on this, and this is neutron. Our photoneutron target is ready. With the setup, the interface has already been done, and we are now in the coming month time, we are going to do the neutron radiography with the gated ICCT. As I said, we have to neglect the gamma part of it, and we have to use only the neutrons, generated neutrons for the radiography application. So that is the very challenging part in this project. And hopefully it will be done very soon. So this is just a summary of what all I presented just now. Aperture, we are getting 10.6. At the image plane, we are getting around 10.4. And the anisotropy is about 1.2. I'm around the image plane. And this is a very important result. The time resolved means the gamma and the neutron pulse. Basically, this gives us the gating time for how much time we have to gate the neutrons and for how much time we have to keep the gate closed. This has also been modified. Our gamma and target assembly has been modified to bring down the residual gamma. Earlier it was 800 R per hour. Now we are getting about 60 R per hour. So this will give a better neutron to gamma ratio for the high resolution imaging. And finally, we are going to implement this setup very soon by the end of May 2022. So that is all from my side.
Thank you, Dr. Rishi, for giving a very informative talk on utilization of 9 MeV RF LINAC. Thank you so much. As a token of appreciation, there will be a memento will be given to you.
Thank you very much, ma'am.
Thank you. Thank you.
Thanks to the organizing committee for giving this platform again, ma'am. Thank you so much. Thank you.
There will be a invited talk by B.B. Sahu. B.B. Sahu received his master degrees in physics from Utkal University, Bhubaneswar in 1999 and completed his PhD from Plasma Lab at IIT Delhi in 2008 on experimental and theoretical investigation on helicon wave plasmas in conducting waveguide. And he is a designated professor at Center for Low Temperature Plasma Sciences, Graduate School of Engineering. There he worked in the areas of plasma sources, plasma diagnostics, and plasma application in thin film etching. In November 2020, he joined the Center for Energy Studies, IIT Delhi, as an associate professor. I welcome B.B. Sahu. So there will be a 15 minutes for you for your talk, sir. You please go ahead, sir.
Okay, thank you, madam. Is my screen is visible? Hello, is my screen is visible?
Yes, it's visible.
Okay, thank you, madam.
Yes.
Thank you, madam. And I would like to first thank the organizers who has given me an opportunity to be here and present a work. And to be honest, this work is performed in South Korea while I was working as a designated professor there. So, and this work is different from the other talks which we have seen here. And this is relevant to a diagnostics, plasma diagnostics, the powerful tool which can be utilized for different kind of application. And today's talk is basically the effect of electron beam irradiation from a hollow cathode source on the characteristic property of lithium manganese oxide film as an LIB, lithium ion battery electrode. So this is the outline of my talk. So I briefly talk about very briefly overview and then present the material design and strategy on the basis of plasma control, then some results and using diagnostics and material properties. And I would like to conclude. So since the time is very small and also the talk is relevant to plasma based thin film processes, I will highlight briefly about the overview. So this is a battery. Battery is operated using electrochemical reaction. So it has three main components like cathode, which is a positive terminal, anode, and electrolyte. So these, in order to make a battery, there nowadays battery is used extensively in different areas, and the typical battery we are now looking for is lithium based. So mainly lithium batteries or lithium ion batteries. And lithium metal is the lightest metal and in the periodic table, and it has a very good electrochemical properties, and has excellent property, and it is highly reactive material. And this is the lithium ion battery. So basically in battery there are cathode, anode is through, and charge is transferred through the electrolyte. So this is the key component of a battery, lithium ion battery. So, and why we are so much bothering about lithium ion battery? Because in battery, this LIB, lithium ion battery, it is rechargeable, it is a secondary battery, and rechargeable lithium ion battery are used extensively in market. So it has a very high volumetric as well as the gravimetric energy density. So it is quite useful, and now it is taking care a leading role in the market. And most of the lithium ion battery is now targeting about 4 to 2.5 volt. And these are the various leading company which are manufacturing solid based solid battery, so solid thin film battery. And one of the company is also included in India. I have gone through it. So these are, and they have utilized different kind of material like electrolyte, cathode and anode. So for particularly cathode, people also use lithium manganese oxide. So what is the key requirement? So the key requirement is energy with relation to the power. Basically in the battery, the energy stored in the battery is proportional to the amount of active material, that is cathode and anode. And the power rate of energy delivery is depends upon the sufficient mass and electrical transfer through the electrodes. And since the battery is made up of several material and thin film material, and the thin film property control is very much key. So it is very necessary to control the microstructure and morphology of the thin film. And it is very much dependent on the nature of fabrication. And one of such fabrication is plasma-based synthesis of material. And it has a lot of advantage in manufacturing with desired characteristic features. So this is the typical battery structure. So we need current collector layer, which is for connecting the wire for current, and electrode. This is a electrode, basically cathode, electrolyte and anode. And on top of there is another current collecting layer, and on top of there is a shielding. So basically this battery is made of in various stages. It is a stage-wise process. So each and every material should be prepared with a designated property. So it is very important to gain such kind of property during fabrication. And this is another, there are different material, cathode material. So today's talk is basically a material relevant to cathode. So I am talking about lithium manganese oxide among the various possibility. Now it has the advantage, it has a spinal structure. And when the lithium manganese oxide are cycled, and crystal lattice is basically cubic. So the volumetric changes, which is a major problem in the battery, is minimum. So if we make this battery with spinal structure or cubic structure, the volumetric changes will be minimum. So it gives additional advantage through the battery manufacturing. And the major issue in manufacturing is the high temperature budget requirement. So people have used plasma-based technique, and they have utilized very high temperature up to 500 to 1000 degree for fabrication. So we need a dedicated process with low temperature, and for that we need dedicated plasma source. And also in plasma there are parameters like electron temperature, ions, plasma potential, and also various reaction occur, which are basically excitation, ionization, dissociation. So we need to control the process parameter, which is very much essential for gaining the desired chemistry for the fabrication of thin film. So we have to make an integrated aspect. We have to take care of the plasma source, also plasma diagnostics, also we have to material. So we need to dedicate, but it is not straightforward. For material science, then bother about material. For plasma science, we bother about plasma sources and diagnostics and the mechanism of plasma generation. So we need to take an integrated aspect of this whole process so that we can produce a technology which will be useful for the society with desired property. But there are still some challenges in diagnostics as well as plasma sources as well as materials. So this is this experiment. So in order to make a low temperature, our motivation was to develop a low temperature process utilizing the plasma control. So this is the system we have used, and it is a multi-target magnetron sputtering system. In this system, there is a small source, hollow cathode source, which we have designed and utilized for the manufacturing. So this is the schematic. You can see we have used dual magnetron sputtering, and this is the target to the substrate distance is about 11 centimeter. So we can control this by the rod control, and without heating we prepare the sample. So temperature is nominal, about 200 to 250 degree we kept, and this is the mechanism of hollow cathode discharge. Basically, the electron neutral mean free path is basically inversely proportional to the gas pressure. So we inject a gas and with a pressure, and we vary the pressure to 20 to 60 milliliter, and we generate an electron beam. And so this is the cathode. So beam is generated, it is passed through this chamber, and we apply this to the plasma generation also. So there are two parameters. So when we are utilizing the hollow cathode source, so we are passing the gas through the common line. But when we are utilizing hollow cathode as well as magnetron, so we have to switch on the magnetron. But when we are not utilizing the hollow cathode, we are not switching on the power of hollow cathode. So hollow cathode discharge source power is fixed 100 watt, and we vary the magnetron power up to 150. So we kept the magnetron power. And one of the aspect, because the magnetrons are operated using radio frequency 13.56 megahertz, in the radio frequency environment, we need Langmuir probe, which should be RF compensated. Because plasma potential fluctuate with time, so we need RF compensated Langmuir probe to measure the error-free plasma parameter. So we developed a Langmuir probe on the basis of design of our group while I was studying in IIT Delhi with Professor Ganguly group. And also we made a similar probe structure, and which is also published in our recent literature. So then after developing this source, we started the film property, study about the film growth. So you take the film growth profile, and we can see that about 5 by 5 centimeter area is quite with film with good uniformity. So we thought this will be utilized for the initial study, and to track the plasma parameter, how the hollow cathode source is utilized and what is its effect. So we do the plasma diagnostic using the RF Langmuir probe. So we inject the SCD, hollow cathode electron beam, and we switch on the magnetron. Then we measure the Langmuir probe. So we measure the Langmuir probe when the hollow cathode discharge power is off, means hollow cathode source is not operation, and when the operation of hollow cathode discharge as well as the magnetron. So in addition, this means there are two parameters. With SCD means hollow cathode source is on. Without SCD means hollow cathode source is off. This means power is off. So when we vary the pressure, we can see that with increasing pressure, the plasma density is increasing up to 40 milliliter, and then it started decreasing. But without hollow cathode discharge, with increasing pressure, density is gradually decreasing. Similarly, electron temperature also slightly increasing, then falling, tracking the profile of N0. Now, in the presence of hollow cathode source, we notice that there is additional ones of electron population called warm electron population, which is present in the discharge. So which is energy about 10 to 15 eV. So this is a warm energy population which is occurring through this electron beam. And we found that this warm energy electron population is making ionization, which is making effective ionization in the hollow cathode discharge. So we found that plasma generation in using the hollow cathode source is quite useful. Then we process the thin film manufacturing of lithium manganese oxide. So we take the growth rate. This is the growth rate with increasing pressure, we can see, without the hollow cathode source, and this is with the hollow cathode source. And we got a very good deposition rate using the hollow cathode source in addition to the RF. So which is also quite improved as compared to the literature value of the reported literature using magnetron sputtering. Then we investigate the material property. So we take some selected samples. So we take the maximum here. If you see, this is the 40 milliliter sample. This is the with maximum plasma density. We take this sample as a reference sample without hollow cathode source, and we took 5 sample with hollow cathode discharge produced sample. So you can see that the discharge operated with around 40. So around 40 milliliter, which is a good sign of X-ray peaks. So XRD peaks are very well very well observed, as well as if you see the distance between target to magnetron to target is about 10 centimeter, the peaks are quite good. And if the distance is little bit shorter, peaks are there, but it is somehow it is acquiring some manganese oxide. So we compare with our result with the literature. So you see that one can see that the literature value is very highly. Literature produced film are very grown on in a very high temperature environment. In our case, we made it at a very low temperature environment, around 200. This film is produced around 200 degrees centigrade. So
Sir, you are having 2 more minutes.
yes, madam, I am about to finish. So
Thank you.
This is the structure. This is the Raman analysis data. You can see the Raman peaks are changing. So this is an indication that microstructure is changing with plasma condition. So which compare with the literature value, and it is well. And this is the value. This is the TEM analysis, the electron microscope, dark field as well as bright field images of the optimal sample, which is prepared at 40 milliliter. So it is showing deep crystal planes. And finally, this is with the help of another group. So we have tested the features, whether it will be useful for battery application or not. So we got the specific discharge capacity, which is also very well. Initially, it is coming very well. So more studies are going on, collaboration work is going on. So hopefully we'll get some more output in future. And in conclusion, I would like to say that magnetron sputtering in plasma based processes, any application, we need to control the plasma parameters. So we need a dedicated diagnostics. So we need to understand the plasma generation mechanism as well as the plasma diagnostic is useful, how the plasma parameters are affecting the film properties. So we need to study an integrated aspect. So it is also important. And here in this study, we demonstrated that the control of plasma parameter near the deposition environment is very crucial, important for the low temperature deposition of lithium manganese oxide thin film with desired structural and morphological property. So we report an integrated study to investigate the plasma characteristics as well as the thin film characteristics. So recently we have published a paper without the utilization of SCD. So this work may be lead to another publication in future. So I'd like to thank you for your kind patience and giving me this opportunity. Thank you.
Thank you, Dr. Sahu, for giving the detailed talk on the plasma characterization. And it is a very, very useful talk. Thank you so much, sir.
Thank you, madam.
With this, we conclude this session.
Thank you all the speakers. Thank you, Mrs. Uma BR. Now, on behalf of the organizing committee, we would like to give you a memento. I would like to request Dr. A.K. Gupta to come on stage and present Mrs. Uma B. Rao with a memento. Now we'll move on to the next session.
Good evening, everyone. This is the last evening talk of today's program, Vstaa 2022. I request Dr. A.K. Gupta, Head NPD, to chair the session.
Can you hear me? Thank you very much.
Yeah, yes.
Yes, sir. Can you hear me?
Yeah, I can hear you, Gupta ji.
Yes, sir. So, actually, very good evening to all of you, sir. And it is indeed, privilege to chair a session where our guru, many of us who has learned the, not only accelerator physics and technology, but also the project management techniques. So, with this, I also would like to add that the way, we have been interacting and learning with the, Singh's Hub, we used to call him with full of love, is such that he can put very simply at a 10th standard, 12th standard, any complicated thing. So that has been his hallmark, and all of us, you will be looking for his interesting talk. Maybe I can read the his official introduction. Dr. Singh made very important contributions towards design and development of a 2 MB tandem accelerator and 6 million volt folded tandem ion accelerator, FOTIA, at BRC, and made outstanding contributions towards indigenous development of accelerator technologies. Dr. Singh contributed immensely towards an ambitious Indian program which involves thorium utilization in the fuel cycle for nuclear energy generation. Dr. Singh was founder president of the Indian Society for Particle Accelerators, ISPA, till 2016, DAE Rajaramanna Fellow, and senior professor of physics at HBNI. Dr. Singh was head of the Ion Accelerator Development Division, which is called now IADD. In short, presently, he is visiting associate at IUSC, New Delhi. Good thing. I thank you, sir. We look forward to your talk, Dr. Singh. Can you hear me, sir? You can start your talk.
Okay. Thank you, Gupta ji, for very nice introduction. And I will also like to thank organizers, particularly Dr. Archana Sharma and Mr. Bug Singh, for giving me this opportunity to share with you my 45 years of experience in accelerator physics and technology. In fact, I am presenting this on behalf of many directors from whom I have taken the inputs. Some of these material has already been presented, so it will be a repeat. Please bear with me. But I am trying to put the whole thing at one place in a very comprehensive manner. So my talk is on Indian Accelerator Program, an overview, and therefore now I'm sure that what is accelerator you would like to ask. In fact, what is microscope for the biologist and telescope to the astrophysicist? For the nuclear physics people, accelerator is the same, and accelerator is called as a ultra sensitive microscope. And any nuclear physics, I think Gupta ji about few hours back has given a very comprehensive talk on the accelerators and their utilization. But let me just repeat it that any nuclear physics person or any physicist would like to know two things. One is that what are the building blocks of matter? We are all made up of matter. So we would like to know what we are made up of. And of course, once we know those building blocks, what is the interaction between them, which is keeping them all together? And of course, production of heavy ions, heavy particles, production of radioactive ion beams, and what is the maximum A and Z which is possible? I think all these questions can be answered through accelerators. And I would like to answer some of these things here. So you can see that resolving power or the smaller object which you can resolve, that depends upon what kind of projectile you are using and what is the wavelength, because it is proportional to wavelength. And it is the resolving power or the resolution is inversely proportional to energy. And therefore, higher the energy, smaller things you can resolve. And that is why there is a race to build bigger and bigger accelerators. And these are some of the numbers which you can see, that if you want to see an object which is which has a size of about 10 power minus 18 meter, then the wavelength to this order corresponds to about 100 GeV. Therefore, if you want to see this kind of objects, you need an proton energy of 100 GeV. If you want to, and this is the dimension of roughly the quarks, basically. And therefore, the quarks were observed when they were interactions of the particles around a few tens of GeV. In fact, it was observed at 33 GeV using at Stanford Laboratory SLAC, when the 33 GeV electron beam was bombarded with the target, and three quarks were discovered that time. But now the question is coming whether these quarks are the final objects or they are also divided. Now, as I mentioned earlier, that if you want to answer this question, you have to have higher energy particles, so that the wavelength is much smaller, and we will be able to see the substructure of quarks also. In fact, theoreticians have already started talking about quite a few times back that these quarks are also not fundamental particles. They are also subdivided. They are also made up of something else, and which they call it partons. And if you want to see the partons, then you have to make higher and higher energy. And in that direction, several big accelerator labs, for example, CERN has already started thinking. And as was mentioned by Maurizio Bretner yesterday, there is an approval of another accelerator called FCC, that means Future Circular Cyclotron or Cyclo, and that will be about 100 TeV energy of electrons. And that will have several options, that it will be electron colliding with the positron, or electron colliding with hadrons, or hadron colliding with hadrons. Several options will be there. And the cost of that accelerator FCC is going to be more than $50 billion or something like that. But this project has been approved by the council at CERN, and people have started. Now, these are all international things which I am talking. Let us talk about what is the status in India and how we have grown with that. Now, at this moment, I would like to tell that accelerator physics and technology has matured quite enough in India, and we are ready to take up a lot of jobs, particularly design related or even the technology development related. But just to give you an history, that in India, accelerator development started in actually 40s, when Professor Meghnad Saha decided to build a 38-inch cyclotron at SIP Delhi. And of course, he could not commission it. It was commissioned by later in 1960 with about 70 microampere internal beam and 0.1 microampere external beam. And the energy was 4 MeV. Now you can see here that the transmission is very small. From internal to external is very small. That means the beam dynamics was not known very properly. But it gave a lot of experience to people and gave a lot of confidence. And around the same time, people thought that, okay, we can't build big accelerators. Why not to make small accelerators? And they also can be used for a very nice experiments in nuclear physics. And around that time itself, the Cockcroft-Walton type of accelerators were quite popular. And therefore, several Cockcroft-Walton accelerators for neutron generation were built. And excellent research were done using these 14 MeV neutrons, which were produced using these particles accelerated by this accelerator. Of course, all of you know that one of the famous reaction is that you have a deuteron beam from Cockcroft-Walton, and you made to collide on the tritium, then 14 MeV neutrons are generated. And 14 MeV neutrons are very good tools for doing the nuclear physics, and a lot of experiments were done. And here are some examples, for example, how the accelerator development has taken place in India. At TIFR itself, a 300 kV open air Van de Graaff was made, and it was operated. It was published also in 1959. And later on, 1 MeV electron accelerator was also made around roughly around the same time. So this was the development at Tata Institute. You can see on the right-hand side the figure, and you concentrate on DT reaction, you can see that even at 100 keV, and if you have about 100 microampere current, then you can get about 10 power 9 neutrons per second. So that is a very good flux for doing the nuclear physics. And in view of that, Aligarh Muslim University built a 150 keV accelerator or CW type for neutron generator, and very good quality experiments were done. Around the same time, 400 kV Cockcroft-Waltons were also built at SINP and Bose Institute. So around that time, several accelerators, small accelerators were built. Roughly around the same time, in 1949, Tata Institute set up a facility of 1 million volt Cockcroft-Walton. We used to call it cascade generator, and it was used for several years for doing nuclear physics. Later on, of course, it was donated to Calicut University, where also it was used very effectively for many, many experiments. And these are shown here. So you can see the on the figure below, the 1 MeV Cockcroft-Walton at Tata Institute of Fundamental Research. Now, if you see today, there are 4 main centers of accelerators. See, you can't just stop at 400 kV or 1 million volt. You have to go to higher energies and different masses also, projectiles. So at this moment, there are several places accelerator facilities have been set up, but there are more, mainly 4 institutes which have built several accelerators. One is BARC and TIFR, because they are working together. Then RRK at Raja Ramanna Center for Advanced Technology in Indore, Variable Energy Cyclotron Center at Kolkata, and there is one center basically for universities. It is an Inter-University Accelerator Center in New Delhi. These are the main centers which are having several accelerators, but there are other accelerators at, for example, at IOP is 3 MV Peloton. IG car has 2 small accelerators, 1.7 million volt tandem plus a 400 kV heavy ion machine. And Bilaspur University has a 3 MV Peloton. Punjab University has IIT Kanpur has Banaras. So there are several accelerators. In fact, there are many accelerators. These are for research purpose, but there are many accelerators which are now used for therapy as well as for industrial applications. And in fact, I was talking to Vivek Yadav in the morning, and he gave me some figure that there are 600 accelerators in hospitals and few hundreds for industry. So India is at this moment having about 1,000 accelerators working in various things. So I've listed the accelerators here. I'll not go through it, but I'll just list it here. and put into three categories. First category is the accelerators for protons and heavy ions, and you can see a very large number of them. And you can see the last ones which are in the green, that now these accelerators are also going to be very extensively used for cancer therapy. And in Bombay also, there are going to be two accelerators, one for proton accelerator for cancer therapy. And as was mentioned by Mauricio yesterday, that carbon-12 or heavier ions are much better for cancer therapy. Therefore, a national hadrons facility is being set up, is under planning now at TMC Mumbai, and it will be in Kharghar, where I stay. And that will be a heavy ion facility. Now for industry, and from the point of view of fabrication, electron accelerators are simple, and they are more efficient, and their utilization for places where radiation is required and it is effectively used, then electron accelerators better, and you can see a list of several accelerators. But for industry and health, you need about up to maximum 10 MeV electron accelerators, but for basic research, you need higher energies, and therefore at RRCAT we have two synchrotron radiation sources. One is 450 MeV and is called Indus 1, and other one is 2.5 GeV, Indus 2, and their critical wavelengths are 63 angstrom for Indus 1 and about 1.8 for Indus 2. And therefore, these can be very effectively used for basic research. And there are large number of them. And not only that, I have seen that there are very large number of electron accelerators in various hospitals, and they are very effectively used. And of course, for cancer therapy and even for other therapies, these accelerators are much better than the gamma ray treatments, because the X-ray can deposit the energy at the correct place without damaging the good cells. Now, coming back to these were the accelerators which are already in operation. Then, of course, we would like to have higher accelerators depending upon applications. So here I have mentioned the few projects which have been taken up, and they are all complicated projects, so a lot of R&D has to go. And one of them is 1 GeV continuous wave CW LINAC for accelerator-driven system, which will use thorium as the fuel in the reactors. And this project has been going on, and a lot of work has been done in various parts of it. And this is one. And the other one is for basic research. It's a pulsed accelerator that is called neutron spallation source. There is also 1 GeV, about 1 GeV. And then there is another one that, you see, we already have 2.5 GeV synchrotron radiation source. Now, if you want to study things much better further, then you have to increase the energy. So there is a plan to set up a facility based on 6 GeV electron accelerator. That will be called Advanced Synchrotron Radiation Facility. And that also very extensively, very seriously discussed. Then, of course, there will be heavy ion facility, as I mentioned earlier, at Tata Memorial Center. And at Calcutta, they have planned already, and a lot of work has been done, a lot of progress has been done on the radioactive ion beam source that is called ANURIB, and that system is in progress. Now, you will see, I think Mr. Chairman has talked about the AMS. So to do the AMS for environmental science, explicit pelletons with 6 million volt for explicitly for AMS is planned, and I think in a few years' time it will be operational. And that will be a good facility for explicitly for AMS thing. So the load on peloton there will be reduced. And then, of course, there is a proposal put from Northeast for a 5 million volt peloton. Now, as I said, that India is a lot of accelerators are required, and I understand that about 40 accelerators are added every year, mainly in hospitals and industry. And I think this is the now. If you really see that in the beginning itself, although in 1962, a quantum jump in the accelerator facility was done, and that by setting up a 5.5 million volt Van de Graaff at Trombay in BARC, and it was commissioned in 62. It worked up to 65, and a lot of good. And that time, that was the biggest accelerator till the cyclotron came. And here are some parameters given, and you can see here, which later on in 95 was converted into a folded tandem ion accelerator, and I was associated with it. And this 5.5 MeV Van de Graaff was very extensively used for nuclear physics and applied research. But of course, here the problem was that this was a single-ended machine, and therefore only proton and alpha beams could be accelerated. So if you want a heavy ion and a higher energy, then you have to go to a peloton type of thing. You can see that time it was such a big accelerator that you can see on the right-hand side, Dr. Raja Ramanna explaining to Dr. Homi Bhava when it is being commissioned first time. And there are several other dignitaries like Setna and so many other dignitaries who came. So you can see that in 95, we decided that we should have heavy ions available, and if possible, we should try to have a slightly higher energy also. And therefore, that 5.5 MeV Van de Graaff was updated and converted into a 6 million volt folded tandem ion accelerator. And configuration of that is seen here. You can see in the beginning, the beam which is going is blue, that is negative. And after that, the charge exchange takes place, and that becomes so this is a wonderful facility which is working very effectively 24 hours, even now 7 days. And you can see it on the right hand side. And I have privilege of saying that I was associated with this facility. So this was commissioned somewhere in 2004 or something, and even today it is working very well. And it is very effectively used, and it is all the time available. This can give not only proton and alpha particles, but also it can give heavy ions also. And beams of carbon, oxygen, fluorine, and several others have been very effectively used. Now, at this moment, I would like to say that when you want heavy ions to be accelerated, then the vacuum, actually the requirement on the vacuum becomes very stringent. So what was sufficient in the case of single Van de Graaff of vacuum of 10⁻⁻⁶, here because we are going to accelerate heavy ions also. So vacuum of 10⁻⁹ or 10⁻⁸ torr will be required. Otherwise, there will be beam loss or beam energy variation. Now, around the same time, in order to gain experience, we also built a 2 million volt tandem accelerator, because this is a much better option for heavy ions. And I was again associated with this. In fact, my thesis was on this project only, the physics as well as the technology of this accelerator. Now, up to this point, up to 60s or so, we were having only 60s or 70s, we were having only these one or two machines. And you know that nuclear physics requires more accelerators. And therefore, in mid-60s, it was felt that there is a need to have bigger accelerators. And if you want to do a competitive physics, then much bigger accelerators have to be, not only facilities have to be set up, but also we have to launch an accelerator development program, because we can't keep depending upon only on imports and things like that. So Professor Homi Jagir Bhabha, who was the chairman that time, he convened a meeting at IISc Bangalore on 3rd August 1964 to discuss the need of bigger accelerators and what kind of accelerators we should have. And it was decided in that committee, in that meeting, that we need two accelerators. One we need immediately, we should set up so that the nuclear physics or the physics doesn't suffer. We start using immediately. And of course, parallelly, we should also start designing and developing the accelerator. So accelerator technology has to be pick up. So they decided, the committee decided that we should have two accelerators, and one we can have a tandem accelerator and augmented by a superconducting LINAC, so that energy can be increased further. And another can be a cyclotron, and that we have to develop further. So in view of this, a 14 UD Peloton was purchased from NEC USA and set up at TFR for different regions. And it was commissioned in 1989. And Dr. Gupta has already talked about details of this, so I will not go in details of this. And AEC decided in 1968 to build a 88-inch diameter variable energy cyclotron at Calcutta. So what you see at Calcutta, the room temperature cyclotron is that 88-inch. And they said that, okay, it should also come quickly. And therefore, we can take design from cyclotron at Berkeley, which was working very well. And therefore, we will build ourselves, but we take the design, understand it, and then we will build it and commission it here. Now, this is called the energy of that cyclotron. It was developed and it was commissioned during 70s. And the energy is given as K times Q square by A. And K for that, for the parameters is about 130. That's why it's called K is equal to 130 cyclotron. Now, another accelerator, which, as I said, that it was purchased from NEC, and details you already know about it, is a 14 UD Peloton. And you can see the column section and the tower inside which it is. This has been discussed by Dr. A.K. Gupta in detail, but this is very difficult to get beam time. It's so busy, and this is a national facility, and it is occupied all the time. And it is augmented with a linear booster, linear accelerator, and that linear booster is a OFSE copper, and on that we have lead thickness plated of 2 micron, and you can increase the energy using this by about 3 MB per million volt per meter only at about 6 to 8 watts. That's the advantage of having a superconducting structure. And 28 lead-plated quarter wave resonators in 7 cryo modules were installed. And the energy gain in this case, additional energy gain, is about 14 MBB per charge state. So depending upon charge state, see that charge state means you can accelerate heavy ions. That's the advantage of Peloton. And as long as velocity is matched, the same thing will go through the LINAC also. Second big center, which is explicitly meant for accelerators, particularly for universities, and it's a electrostatic accelerator, and is called Inter-University. Earlier it was called Nuclear Science Center. Now it's called Inter-University Accelerator Center. And that has very large number of accelerators for various applications. And the main accelerator for them is 16 million volt. It's called 15 UD peloton, but that can go to 16 million volt. And a lot of other systems, facilities. For example, negative ion low energy facility, accelerator mass spectrometer facility. So that has almost like 10 accelerators for different, and of course the RF accelerators are also there, superconducting LINAC. And then their load is so much because that is catering to about 900 units, 900 centers. So it is right now the peloton injects into LINAC. So you can use only whenever you are using LINAC, peloton cannot be used independently. And therefore a separate facility called high current injector has been set up, and which has been commissioned only about 2 weeks back. I'm happy to inform that I'm associated with that also. And that will directly inject the beam to LINAC. And therefore, the peloton and LINAC both can be independently used, and the utilization will enhance like anything. They also are setting up a free electron laser facility, and they have a ECR ion source based low energy field. Several facilities are 10 to 15 such facilities are there, and you can see some of them here. And pictures, they are all operational for several years, and they have also right now they have also set up a 500 kilovolts AMS filter. In fact, for AMS you don't really need more than 500 kV. So they have set up a 500 kV accelerator mass facility, and that is effectively used all the time. Of course, for Rutherford battery scattering also, they have a 1.7 million volt peloton, and which is used continuously. Third accelerator is variable energy cyclotron, Calcutta, which has 3 cyclotrons. One is K30, room temperature. Other one is K500, that can go to much higher energy. And third cyclotron, which is a very nice facility, is a medical cyclotron facility. And you can see that these 3 accelerators is a very vibrant center for cyclotrons, and they are all used, and this completely fabrication of all the this K500 and K130 is done indigenously. And recently this K500 is also commissioned with very high energies. For example, nitrogen 4 plus, they have got about 252 MBV. This is about 18 MBV per nucleon. And nitrogen 2 plus is about 63 MV. So, this is used, I think this was commissioned somewhere around 1980, this room temperature thing, and is still working today very efficiently. Now, both these accelerators, both these cyclotrons are routinely available. And of course, 30 MBV medical cyclotron is used for creating or producing PET isotopes, SPECT isotope, and they are immediately supplied to various hospitals around in Calcutta and around, depending upon what is the lifetime of that. And it is doing a very good job for the people around. You can see some of the isotopes which can be produced for health purpose, and some of the imaging results are also shown here. And fluorine 18, which is used for cancer diagnostic purpose is routinely made and supplied to various hospitals. Now, a facility or this a cyclotron, medical cyclotron with 16.5 MBB was also set up long time back in Mumbai, in close to that TMC, Tata Memorial Hospital. And this is 80% of the time it is used to produce fluorine-18, and roughly all the hospitals using cancer treatment, they are supplied these isotopes from TMC and BRIT, and they are being used. So this is very effective. This runs almost round the clock, and 3 times the fluorine-18 is produced and is supplied even up to the hospitals up to the Pune or nearby places. Now this VEC with K is equal to 130 also plans to use it for the radioactive ion beam injector to that facility. And one of the beam lines you can see below on the right hand side, there are various beam lines, and one of the beam lines is being used for taking the beam to the RIB, which can be seen here, and that can be accelerated. RIB means the isotopes which are away from the beta stability line, and therefore very good nuclear physics can be done, and that can be done. Beam can be taken from cyclotron, and can be RIB can be produced here and can be accelerated in this RIB facility. There is also a plan to have an independent facility, and they have already started working on for quite some time. They will have a superconducting electron LINAC, about 50 MBB, 100 kilowatt. With this independently by photofission, you can generate a lot of RIB, and that can be accelerated using LINAC plus cyclotron combination, and ultimately it can be stored, and a lot of good nuclear physics can be used. And this ultimately idea is to have about 100 MV per nucleon acceleration in phase 2. And in phase 1, they have already started working on this electron LINAC in the collaboration with Triumph in Canada. And I have seen myself, and there is a good progress in this one. Third center, which is the biggest center for accelerator in DAE particularly, is Indus 2 and Indus 1 having on RRCAT. And you can see here a beam of about 20 MBV, 30 milliampere generated microton is accelerated, and then accelerated to up to can be accelerated to 700 in a booster, and then it can either be injected into Indus 1 or Indus 2, and they can be accelerated further. The beam can be stored in Indus 2, and this can accelerate up to 200 milliampere. I think they have already reached very close to it, about 150, 180. And some of the components you can see on the left-hand side in the figure. And this is a very good, is completely indigenous facility. And I think it has given so much of confidence to nuclear accelerator physics people in India that they can not only design the accelerators, but also build, and more than building, they can commission it to the specifications. That is the kind of and these facilities are working round the clock. You can see the performance, operational performance. And even during the Corona, you can see that 2021, the accelerator Indus 2 and Indus 2, both Indus 1 and Indus 2 have been operational. Beam was available to the users in so many hours, almost 6,000 hours in Indus 1 and roughly 4,400 hours in Indus 2. So that shows that how how efficiently they are working. They have also developed a center. In fact, they call ARPF, Agriculture for Agriculture Product Radiation Facility. And I think there was one paper also on this one. And they will be irradiating or these vegetables, as well as now they have got permission. They have got permission for sterilization of medical devices, and they are. We have seen ourselves that this is very efficiently working. In fact, they have they have put the redundancy also. They have put 2 Linux of 10 MBV in that one. So if suppose some problem develops with one, they can switch over to other one, and the work is not suffered. They are also developing one more Linux, which is much efficient, more efficient performance. And you can see this is the, so not only there in RRCAT, but a good facility is developed here in EVC Center, Kharghar here by BRC, and that has 3-4 accelerators. And you will see that very large number of utilization has been done. They have this 10 MBV, which recently, I think Saroj mentioned just a little ago, that this has been tested for 24 hours, 2-3 times in a month, and at 3 kilowatt. And I have seen at 5 kilowatt also working. In fact, as a chairman of safety committee, I also witnessed this working for 3 kilowatt continuously without any trip for more than 24 hours. So this performance is very nice. And of course, this all these facility, they also have a 1 MBV, 1 million volt, 100 kilowatt DC accelerator also. And you can see a very large number of applications can be done here. And they have done several, they have applied it, this irradiated for several cases, and with a good performance. Not only for you can see here that they have used for many applications, and you can see the results. For example, dye waters and textile effluent treatment using 1 MBV has been done. It was done with, they had a 3 MBV DC accelerator. With that also it was done, and several other. And I think Uma also mentioned that they have tested their some of the devices here using the electron beam for sending them for outer space and for in the satellites, etc. So these 2 facilities are doing a good job, both at RRCAT and EVC. And I have seen both of them, and they work very well. And in addition to that, these are societal ones, but there is another application at IGCAR Kalpakkam. They have a fast breeder reactors, and they would like to know the induced damage due to neutron irradiation. So they have accelerators which simulates the fast neutron irradiation damage, and they have 2 accelerators there. One is 1.7 MeV tendotron, that is tandem, and a 400 kV accelerator, and both are put together at one place, and they are used. See, 400 kV beam is used for heavy ion generation, and 1.7 MeV is for alpha particles, and they use it in dual mode, and they are doing this induced deviation simulation work and then analysis. And I think that whole data will be used not only to for the fast breeder reactors, but also to verify the codes which are being used for various. These are the facilities which have been used very effectively there. The defects produced due to implantation are characterized by means of depth resolved beam-based positron annihilation spectroscopic technique. So whatever damage takes place, that is analyzed, and that data will be very useful for improving the design for the faster breeder reactors. Now, these are the accelerators we have in India right now, and there may be many more I might have missed. I apologize for that. And I know there are many. And but life doesn't stop here. We would like to, if you want to compete with international science, then we have to go to higher energies. And that is why we have 5 mega projects, several mega projects also initiated. And I'm happy that government is supporting. And as I mentioned earlier, that there are two 1 GB accelerators planned, one at BRC and the other one is at RRCAT. And then we found that it will be better. Initially, we thought of using room temperature components, but then later on we found that the power requirements and the efficiencies are not that good in the room temperature. Therefore, we should go to superconducting structures. And it was felt that it would be nice to collaborate with somebody who is doing similar kind of work and using the superconducting technologies. We found that Fermilab, for example, is having a project. It's called Project X, which is having an 8 GB accelerator, linear accelerator. Out of that 8 GB, 3 GB part is somewhat similar to ours. And therefore, it was felt that we should have collaboration together. And the idea was that we should learn rather than just copying something. And therefore, it was decided that we will work in design together, but all the fabrication will be done here. And since the testing facilities are not available here, so initially all the testing will be done at Fermilab. And then those cavities can come, and that will validate our design, and that will validate our fabrication procedures and all that. So in view of this, a MOU was signed on February 10, 2009 between Director RRCAT and Director Fermilab in the presence of Chairman AEC, Dr. Anil Kakotkar, and many others. And then it was felt that we should go ahead. And later on, then we said that we can increase our collaboration in various other areas also. And therefore, roughly 7 more MOUs were signed, and depending upon, and not only in the cavity formation, but also in RF power and at various frequencies, 325 megahertz, 650 megahertz, and so on. And also we said that let us, they also offered that we can have the physics design also together for all the 3 accelerators. And you can see here another, these 4 or 5 MOUs being signed by Dr. late Sri Kumar Banerjee, then chairman of AEC, and the Fermilab team. So as a part of this development, a single cavity in the beginning at 1.3 gigahertz was fabricated at RRCAT and IUAC, and this was tested at Fermilab. And I'm so happy to tell that the accelerating gradient of 37.5 megavolts per meter was achieved with a Q value of 10 K at 2K. And this was almost very close to the design value and required value for the. Later on, we also built a 650 megahertz cavity, single cavity, and that was also fabricated here in India at RRCAT and IUAC. And then it was tested at Fermilab, and the accelerating gradient of 19.3 MV were achieved, and with a high gradient, a high Q value. So that only shows that we have understood understood quite well the design as well as the fabrication procedures, and of course the testing. And
Excuse me,
similarly,
sir.
parallel, yeah.
Excuse me, sir. You have 5 minutes left now. So maybe
Okay.
you can go ahead.
I was told that I will have 15 more minutes extra. So similarly, the another accelerator is being built at BRC, and I think yesterday the first injector part of LEPA was discussed. And I will say that all components of this LEPA are fabricated, they are ready. And you can see that once this 20 MeV accelerator is commissioned, then this can independently be also used to generate a very high flux of neutrons, which can be used for. You can see that 20 MeV, 30 milliampere current, you can get about 10 to 15 neutrons per second using beryllium target. You can see that all the components like RFQ, for example, this has been commissioned with the design value, and all the tanks for the DTL. For example, yesterday it was discussed the installation of 2 tanks. These are other 2 tanks from 10 MeV to 20 MeV. This slide is given by Sanjay Malhotra, who has got it fabricated, designed and fabricated. And their performance, low power performance is as good as specifications in there. Now, before that, we thought that this RFQ is a very difficult instrument. And therefore, in order to understand various things and validate our design portion, first we made a 400 kV D plus RFQ at BRC. And this was, we got about a 96% transmission. And it gave about 400 kV, more than 1 milliampere current. This itself can be used for various applications. Now, there is another facility, is a neutron generator at BRC for ADS experiments. It's a 400 kV machine. And this was commissioned and it was used for ADS experiments. This was a target material. This was a Brahma was made. And the neutrons produced by DT reaction in that generator was put inside the box, and where the neutrons were generated, and they validated almost all the design of this. Now, then I will just take 5 minutes more for some of the, because I was told that I should also say a few words about the international accelerator. So one is Tevatron accelerator at Fermilab, and I had chance to work with it. And it has almost 4 to 5 discoveries, and I found that I had chance to meet almost 5 to 6 Nobel laureates there. And you can see the structure. This can accelerate proton and antiproton to 1 GeV energies. And this is another accelerator which I'm showing because this was the only accelerator where the ADS related work is done really. And you can see that it's a 1 GeV accelerator, and using the target on Mercury, they simulated the ADS conditions, and lot of experiments were done. The third accelerator, which is greatly discussed, is the Large Hadron Collider, and that can accelerate the beams to 7 TeV by 7 TeV proton on photon. And this was the accelerator where in 2012-13, a God particle which is called Higgs boson was discovered. And of course, this can go to central mass energy of 14 TeV. But as I said in the beginning, that we always want to go to higher and higher energy, and therefore a future accelerator called future circular accelerator has been planned, which has a circumference of about 100 kilometer, and central mass energy will be about 100 TeV. and therefore we will be able to study the structure of the quarks also using these accelerators. This is another. Now, I would like to tell that this in all these accelerators which I am discussing, India is having is making a good contribution in all of that. For example, FAIR is another in Germany, in Darmstadt. There is a facility for anti-proton and ion research, and it has this will be the ultimate for heavy ions particularly. This will be for electron positron collisions, and you can see that this consists of two LINACs. In first phase, the total length will be 31 kilometer, and the second phase it will be 51 kilometer, and the cost is again about $15 billion or so. And this will ultimately this will give the best result because these are electron and positrons collisions, and both of them are fundamental particles. Therefore, the noise in the experiments will be much smaller. Now, let me just tell you that regarding ADS, this MIRA project at Belgium is the only one which has been sanctioned, and it has been progressing very well, and it has a about 600 MeV LINAC, superconductor LINAC with 4 to 5 milliampere proton beam, and lead bismuth target, which is the best target for the installation. And this will be the first LINAC, first accelerator for ADS system. Now, so in summary, I would like to say that there is a maturity now in science and technology of accelerators in India. I think we can now take up the jobs and we can do the good work. Electron, proton, and heavy ion accelerators are functioning very well for research and applications in India. High current accelerators have to be built for various applications like ADS and RIV and other applications. Now, in all these applications, vacuum is the most important part of any accelerator, and vacuum in the range of 10 power minus 10 torr is required, and it has to become self-reliant. Right now, we are importing most of the ion pumps, which go to -8, -3. But I think we have to pick up and we have to make ourselves self-reliant. Now, as I said that in India, 40 to 50 accelerators are added every year, mainly for therapy and industrial uses. So I think that also will require a lot of R&D also. Those accelerators also right now, they are imported, but we have to make them. Technology has to be. Now, one good part is for these technologies, whether it is an industrial use or is a medical applications, government is very supportive, and therefore it is time for us to pick up the thread and wake up and start making it. Now, in this one, what I have presented is basically the inputs received from in last 1 week or 15 days. I have received inputs from following colleagues: Professor Avinash Pandey, Director IUAC, Director Dr. S.V. Nake, Director RRK Indore, Dr. Sumit Som, Director VEC, Dr. B. Venkatraman, Director IGCAR, Dr. N.V. Chandrasekhar, Associate Director IGCAR, Dr. Archana Sharma, Director BTTG, Dr. Arup Bandyopadhyay, Head Accelerator Physics Group, Professor V.P. Singh, Department of Physics Head. He provided me with details of that 150 keV Cockroach Walton. Dr. A.K. Gupta, the chairman of this session, Head Nuclear Physics Division, provided me the details of 14 MV Peloton and other systems. Sanjay Malhotra gave me the detailed inputs for the DTL tanks from 10 MeV to 20 MeV. And Bakshing and Saroj, they provided me the details about electron beam center accelerators, which have been working well. I'm proud of that. And the technology has matured. So with this, I will close it, and thank you very much for your patience. And I once again thank Dr. Rachana Sharma and Bhakt Singh for giving me this opportunity. Thank you very much.
Thank you very much, sir, for a very comprehensive and talk with diverse flavors, right from starting from 1940, the birth of accelerators in the country, all along the full historical perspective, the local efforts, the facilities already functional, under development or being proposed. Everything is covered. It is really a comprehensive panorama of Indian Accelerator program. Thank you so much for, sir. Let me see whether there are any questions from the convention center. There will be one question allowed. Let's say, do you have any question from the convention center? Is there any question? Whatever, let us go to then online. Is there any question from online audience? Yeah. Okay. So since there are no questions, then let us show the, Dr. Singh, there will be a certificate as a token of love from the organizers, and that will, from IBS, it will be sent to you subsequently. And
Thank you very much.
Yes, sir. Thank you very much for an exciting talk. Thank you very much.
Thank you, sir. I request convener Vstaa 2022 to present a memento for chairing this evening talk session.
Dr. Pitambar Singh, I thank you for the overall view of Indian accelerators and abroad, the latest development. And we thank for all the audience who have been patiently hearing from the morning session to this night session. Overall, many invited speakers and contributed papers. Tomorrow we will be having further presentations on the accelerators, microwave devices, and the vacuum devices. Tomorrow morning, 9:30. Thank you, everyone. Good night.